In this demo, we're going to push a sample AI service container image to Azure Container Registry, or ACR, and then inspect its repository, tag, and digest information. Now, this walkthrough is going to show how a simple container push gives you the core metadata that you need to validate image ownership, confirm versioning, and prepare for downstream deployment into services like Azure Container Apps or Azure Container Instances. So imagine you're building a lightweight AI inference service, maybe a small text classification model packaged inside a container. Before you can deploy it anywhere, you need a trusted registry location to store the image. ACR gives you that secure home. So by pushing the image into ACR, you can gain a clear view of the repository structure, the tags that identify versions, and the immutable digest that proves exactly which image you're working with. All right, so let's get started. Now I have the Azure portal open in my browser. And what I want to do is create a new registry. So in the search bar at the top of the screen, what we're going to do is we're going to type registry. And then we're going to search for Azure Container Registry. If it doesn't pop up right away, then you can refine the search to say Container Registry. And then you can access that specific service. Now what we want to do is create one of those registries. So at the top of the screen, we're going to click the Create button. And now we can start the process of creating. Now the first thing we need to do is select a resource group. So I'm going to create a new one, and I'm going to call it SBDemo AI ACR. Click OK. And now we need to give our registry a name, and I'm going to call it the same thing, SBDemo AI ACR. Excellent. Now it is important to understand that the registry name needs to be globally unique. You'll notice that we get a registry domain name that is shown to us at the bottom of the screen. And because it creates a domain name for this, that's why we need to have a globally unique name. All right, for the pricing plan, I'm simply going to select Basic because I don't need much more than that. And I'm going to leave much of everything else as the defaults. Now we'll click Review and Create down at the bottom of the screen, and then Create once the validation is complete. And this will go off and create the ACR. Now the process doesn't take very long. So once it's completed, we'll navigate over to the resource. So let's just give it a second to complete. And perfect. All right, now we can click on the Go to Resource button in the middle of the screen. And now we're going to be on the ACR overview page. So this page shows us some important information. And the piece of information that I want the most is what's called the login server name. So at the very top of the screen, we can see that there is a login server name section that has our login server, and that's the same globally unique URL. So I'm going to copy that to the clipboard. All right, now the next thing that we want to do is deploy a container to this registry. So what I'm going to do is I'm going to flip over to VS Code, where I've got a couple of files prepared. And don't worry, I'll provide these files with the demo. Perfect. All right, so now I have two files that are readily available here. One is a Docker file, and the other one is a Python file. Now, what the Docker file is doing is it's telling us what we want to deploy. And what the Python file is our pretend application. So we're pretending that we're using an AI here. And then for the Docker file, we're saying what we want to deploy. So it's not really important what's inside the Docker file and the Python file, other than to say that we want to deploy something. The other thing that's important is that we're setting the port and the host, but that also isn't super important for the purposes of what we're going to do in this demo, but it's going to become important over time. So the next thing that we want to do is build the container image. So for that, we're going to open up PowerShell, and I've got the terminal already open in VS Code down at the bottom of the screen. And we want to navigate to our specific folder, which I'm already in. And now we want to run a Docker command to build our image. So I'm going to type docker space build space -t, and this is creating a tag, space, and then we want to name our service. So I'm just going to call it AI service, and then we'll give it a tag, and I'm just going to call it latest. And then we say space dot because we want to build what's currently in this folder. So we'll go ahead and execute that, and then we'll see the Docker command go off and do what it needs to do. It doesn't take particularly long because we don't have a huge image defined here, so we'll just give it a second to complete. Perfect. All right, just like that, it's done. All right, so now the next thing that we want to do is we want to deploy this to our ACR. But the first thing that we have to do in order to do that is log in to the ACR. So I'm going to clear the screen, and we're going to type AZ space ACR space login space, and then we have to give the name of our ACR. So we say dash dash name, and then we name our ACR, which for me was SBDemo AI ACR. So we'll go ahead and execute that. And this is going to go and log in. All right, now in order to log in, we'll type AZ space ACR space login space dash dash name, and then the name of our ACR, which we had already pasted into our clipboard. But we don't actually need the domain name. We only need the name. So we can remove that. And then we also need to apply the resource group. So for that, we can say space dash G space, and then the name of the resource group, which was the same name, AI ACR. So we'll go ahead and execute that. And now we're logged in. Okay, so now that we're logged in, now we can actually start to get ready to push. So the first thing we have to do is a Docker command. So we're going to say Docker space tag space AI service, because that's the name of the container we built, and its tag, so latest. And then we want to specify where it is that we're going to deploy it. So that's our URL. We can paste the whole thing, and then slash, and then what the service is going to be called up there, which is going to be the same thing, AI service, and then tag latest. So we'll execute that. Perfect, we've got our tag. All right, and now the next thing we can do is finally push. So we're going to type a command to do the push, which is docker space push space, and then once again, we're going to give our whole URL slash AI service, because that's the name of our image, and then we'll say :latest, because that's the tag we want to use. We'll execute that, and now we can see that it's currently pushing to ACR in the cloud. So as the push completes, we see layer uploads, and eventually we're going to see a final digest value. The digest is an immutable identifier that guarantees the exact image content. All right, now we can go back to ACR. So let's flip back over to the portal. Perfect. And in the left-hand menu, let's go ahead and click on repositories. Now in the repositories, we should see our AI service. Fantastic. And we can click on it. And now we're going to see our latest tag. We see its size, its creation time, and its digest is all in there. And now we can actually click on that tag as well, and we can see all the information that is associated with that specific revision. So there you have it. In this demo, we pushed a sample AI service container image into an Azure Container Registry and inspected its repository, tag, and digest information to understand exactly what was stored and how it was identified. Great job! In this demo, we're going to retag an existing image version in Azure Container Registry, or ACR, and verify how digest and tag information can help us make safe rollback decisions. This is a core operational workflow. When a deployment goes wrong or a new version behaves unexpectedly, you need a reliable way to identify a known good image and promote it back into service. And retagging gives you a clean, traceable way to do that. All right, so imagine you've deployed a new version of an AI inference service, and after rollout, you notice latency spikes or inconsistent predictions. So you want to quickly revert to the previous version, the one that you know was stable. So instead of rebuilding or guessing which tag corresponds to the correct image, you can use the digest to identify the exact content and apply a new promotion tag that your deployment system can reference. So let's get started. Now I have the Azure portal open in my browser, and I've already navigated to a container registry that we used in our previous demo. This allows us to inspect our registry. Now I'm going to click on Repositories in the left-hand menu, and then you'll notice that I have a single repository called AI Service. So I'm going to click on that repository. Now in that repository, we might see several different tags. Now in my case, I only have one tag, and it's called latest. So what we can do is we can actually deploy multiple different tags. So what I'm going to do is I'm going to flip over into Visual Studio Code, and we'll notice that we have a Docker file and a Python file. And we can pretend that these are different versions. So let's pretend that I have another version. And this time, instead of saying sample AI output, let's just say it says sample AI output 2. Now what I can do with that information is I can deploy another version. So with that, I can run the same commands that we ran in our previous demo, where I can make sure that I create tags and things like that. So in fact, I'm going to do that. So the first thing I want to do is build another image, and instead of calling it latest, let's pretend that this was a version 1 that I had one time in the past, or version 2 that I want to deploy now. It doesn't really matter as long as it has a different tag than the one that we're using. So I'm going to go ahead and build that, and that's going to take a moment to build, and then once it's complete, then we can create a tag that's going to be used for ACR. So we're going to create a local tag first, and we can use the same command that we did last time, except instead of latest, once again, we're going to say v2. We'll run that command, and this creates a local tag, and now we want to push that into ACR. So we can use that same command, where we're going to push to our ACR in the cloud, and again, we're going to say instead of latest, we're going to run version 2. Now this is going to go ahead and push out into the cloud. It doesn't take very long because there's not a huge change between what we did last time and what we have now. So now let's go back into the cloud, and we'll refresh our repository, and we'll see that we have latest and that we have version 2. So now let's say what we want to do is we want to deploy version 2, but we want to make sure that latest is our rollback. So obviously that's a little silly. Typically you'd have version 1 and version 2, and this is why tags are super important. But let's pretend that latest was called version 1, and we now want to deploy version 2. So we're going to go back to PowerShell. We're going to clear the screen, and we're going to run a simple command. First thing we want to do is make sure that we pull the known good image using its tag. So we're going to type docker space pull space, and then what we want to do is we want to give the entire URL. So this is going to be sbdemo AI ACR.azure ACR, or rather azurecr.io, then slash AI service, because that's the name of our repository, and then the tag. So in our case, we're going to say latest, or this would have been our version 1. So we're going to run that command, and we have now pulled the last known good image. And now we want to promote it. So we're going to say docker space tag space, and then once again, that entire URL, sbdemo AI ACR.azurecr.io slash AI service, and then colon, then our tag, which is latest, then space, and then once again, our entire URL, sbdemo AI ACR.azurecr.io slash AI service, and then this time we're going to provide another tag. Now this would be what we want to roll back to. So let's say we want to roll back to version 2. Now obviously that's a little bit silly in our case, but let's pretend that that's what we want to do. So now we can go ahead and execute that. Make sure that we spell Docker correctly. So we'll go ahead and do that. And presto, now we have our path defined. So now we can push that new tag to ACR. So we're going to clear the screen, and we're going to type docker space push space sbdemo aiacr.azurecr.io slash AI service, and then what we want to roll back to, which was v2. So we're pushing our new tag to ACR. So let's go ahead and do that. Now this is going to push, and obviously we had already pushed it before, so it says good, it's already there. Now during this push, Docker is uploading only the tag reference because the content already exists in the registry. The digest printed at the end should match the digest for version 1, or latest, proving that both tags point to the same image. So we can actually verify that. So we're going to return to the AI service repository in the cloud. Good. And what we want to do is we want to click refresh. And now notice that the digest for both latest and v2 are precisely identical. So what does that mean? So what this means is that now both of those tags are pointing to the same thing. And that's what we want. If there was an issue while we were deploying version 1 or latest or v2, whatever it is, we can re-tag the one that was poor and point it to the last known good image. That means that if there are any entities out there that are using the latest tag or the v2 tag, they won't get that poor version anymore. They're going to get the appropriate version that is the last known good version. So we're not deleting the tag. We're just pointing it to a different image altogether. And this is allowing us to do a very, very quick rollback. So let's say we deployed version 2 into latest, or we had a version 1 and a version 2, and latest is pointing to version 2. That would be fantastic. But now let's say we found a problem with version 2, so we need our latest tag to point back to version 1. Well, that's effectively what we've done here. That retagging is taking latest and pointing it to a completely different image. So if anybody out there is using latest, they're going to get the image that we tell it to. So they won't get version 2 anymore, they're going to get version 1. So this allows for a very, very quick rollback strategy. So there you have it. In this demo, we retagged an image version and verified how digest and tag information supports safe and confident rollback decisions. Great job. In this demo, we're going to run an ACR quick task from a local source context and verify that the resulting container image is successfully built and pushed into the registry. ACR quick tasks are one of the simplest ways to build images directly in Azure without needing Docker installed locally. They take your source files, run a cloud-hosted build, and automatically store the output image in your registry. And this makes them perfect for lightweight CI scenarios, rapid prototyping, and validating Docker file correctness before wiring up full automation. So imagine you're developing a small AI inference service, and you've written a Docker file and a simple Python app. But you want to confirm that the image builds cleanly in Azure before you integrate it into a deployment pipeline. ACR quick tasks let you do exactly that. You point the task at your source folder, Azure builds the image, and you immediately see the repository, tag, and digest in your registry. So let's get started. Now the first thing that we want to do is navigate to the Azure portal in your browser, which I have, and then we want to create a new Azure Container Registry or use an existing one. So for that, I'm going to click on Container Registries, and what I can do is I can click to create a new registry, or what I can do is I can use an existing registry. So I have an existing registry called SBDemo AI ACR. I'm going to click on that. And then what I can do is I can click on repositories in the left-hand menu, and I can see the list of all of my repositories. Now I have a repository called AI Service already. And what I want to do now is I want to use a quick task. All right, now let's say I want to create another repository that has some images in it, and that those images are built entirely within the cloud. Now what I'm going to do is I'm going to flip over to Visual Studio Code. Now in Visual Studio Code, I've got a couple of files defined already. Now it doesn't really matter what these files are, but I will provide them with the demo. The first file is a Docker file, and all it's doing is defining what the build should look like. And then we have a Python file that represents our actual app. And this is what our Docker file wants to deploy. Now, typically what would happen is that we would use a local instance of Docker, and we would build and tag the local image. Then what we would do is we would invoke ACR and push that image into ACR. But what we want to do with a quick task is we want to get Azure to do that whole thing for us. So let's get started. Now what I'm going to do is I'm going to navigate down into the terminal at the bottom of the window. And what you need to do, of course, is make sure that you're logged into Azure using the AZ CLI. Now I've already done that, and it's a bit out of the scope of this, but you do need to make sure that you're logged into Azure. Now what we can do is we can invoke the Azure CLI to actually perform a quick task. So what we can do is we can type AZ space and then ACR and then space build. Now that's telling Azure that we want ACR to perform a build for us. Now we need to specify the registry. So we're going to say -- registry, and then we're going to specify the registry name. So my registry is called SBDemo AI ACR. Perfect. Then we want to specify the image that we want it to build. So we're going to say space -- image space, and now we need to give our repository name. So I'm going to call it SBDemo QT for quick task. And then we can say colon, and let's say latest. So we want the tag to be latest. Then we have to say space dot because we have to specify what we want it to build. So that's everything that's in our current directory. So that's the Docker file and the app Python. So registry tells Azure which registry is going to store the image, and the image flag defines the repository, which in my case is sbdemoqt, and the tag, which in my case is latest. And that final dot tells ACR to use the current folder as the source context. So let's go ahead and execute this. Now notice that we've gotten an error, and the error is because in most cases we have to specify the resource group. So that command is not actually complete yet. What we also have to do is add another command or another flag that says -g for the resource group, and then we have to specify the resource group that all of this is running in, which in my case is sbdemo AI ACR. So now we can go ahead and execute this, and it's going to go off and execute. Now as this task executes, we're going to see logs showing each build step, pulling the base image, installing packages, copying files, running the final command, etc. But by the end, ACR is going to print the digest of the newly built image in the same way that Docker would have. And this digest uniquely identifies the image content. So let's give it a second to complete. Perfect, all done. Now let's verify it. Now for that, we can head back over to the Azure portal, and we can see our list of repositories as we looked at before. And now if I click on refresh, we should have a new repository, and we do, called sbdemoqt. Now if I click on that, we should see our latest tag listed, and we do. But we also see its size, its creation time, and digest. In fact, we can click on latest, and we can review the digest information and confirm that it matches what was printed out. So here we see that our digest is SHA-256 567.3D. So let's go and take a look at the output, and we can see our digest is SHA-256 567.3DC, and we can of course verify the entire thing, but that already looks like we've got a good confirmation. Basically, this proves that the image was successfully built and pushed by the quick task. Now, quick tasks validate your Docker file without requiring a local Docker. They ensure that builds run consistently in Azure's environment. They provide immediate visibility into repository, tag, and digest information, and they help you confirm that your image is ready for deployment into Azure Container Apps, ACI, or Kubernetes. So there you have it. In this demo, we ran an ACR quick task from a source context and verified that the resulting image was successfully built and pushed into the registry. Great job. In this demo, we're going to go over ACR tasks that automatically build an image whenever source changes occur. ACR tasks give you a lightweight, cloud-hosted automation for container builds, and they're especially useful when you want to make sure that every update to your source code produces a fresh image without needing a full CI/CD pipeline. So by wiring a task into a GitHub repository or a DevOps repository, you can let Azure handle the build and push operations whenever commits land in a particular branch. So imagine you're maintaining a small AI inference service, and you want every code change, maybe a model update or a new API route, to automatically produce a new container image. So instead of manually rebuilding or relying on local Docker, you can configure an ACR task that listens for changes and rebuilds the image directly in Azure. This gives you predictable builds, consistent environments, and automatic versioning through tags and digests. All right, so let's get started. Now I have the Azure portal open in my browser, and I've already navigated directly to a container registry that I have called sbdemo AI ACR. Now in the left-hand menu, I can expand the Services section, and I can click on Repositories. Now if I do that, I can see a list of all the repositories that I have. And in my case, I have two repositories, one called AI Service and one called sbdemoqt, which we worked on in our previous demo. But what I want to do is I want to create a task that will automatically build one of the images in my repositories anytime there's been a code change. So what we can do is in the left-hand menu, under the same Services section, you'll notice an option called Tasks. So let's go ahead and click on that. Now, this is going to list all of the tasks that we have in the system. Now, I don't have any defined yet, so of course the list is empty. And what we want to do is we want to be able to create tasks. Now, what we would typically do is at the top of the screen, there'll be a toolbar that allows you to create a task. Now, the reason that doesn't appear for me is because it does require a specific version of Azure. So you're going to need to have Azure Premium turned on. Once you have that, you have access to some additional features, including the ability to create these tasks. But that's okay. We can actually talk through this fairly simply anyways. When you click to create a task, you're going to be asked what kind of task do you want to create. And there's a variety of them, but one of them is simply to build on change. And when you do that, you have to specify the source. Where is this change going to be detected from? And at that point, you simply select GitHub. And assuming that's where your code is, you select GitHub, you would select which repository and which branch you're interested in. And at that point, ACR simply monitors that particular branch in that particular repository of GitHub, or Azure DevOps, and that would work exactly the same way. Then, whenever a commit happens in that specific branch, whether it's main or some other branch, that will trigger the task to run. So all tasks have two conditions. One is what do you want to monitor, and the other is what do you want to do. So in the build settings, you would specify what you want to do. And of course, what you want to do is build an image. And so you would select that you want to go to a specific repository, let's say AI service, and you want to use a specific tag. Now, because this would be building all the time, you have a couple of different options. You can have every build go to a latest tag so that it's always using exactly the same tag, or you can use tags that are build number specific, which is the recommended approach. That way, every new build does create an image with a specific version, but you don't necessarily push that into production just yet. You can verify that specific version. So if we go to SBDemoQt from our previous build, you'll notice, of course, that we have a tag called latest. But if we go to AI service, you'll notice that we have one called latest and another called v2. They can point to the same digest. That's completely acceptable. But what you would do is you would create these specific version tags. Then you can test that specific version, make sure that it's all good, and then you can rename it to latest or redirect latest to that specific digest. Now let's go back to that tasks area. Now let's imagine that you have a developer that has committed some code and there's been a pull request and everything has now merged into main. What we would expect is the tasks that we define to run. Now you notice at the top of the screen that there's another tab called Runs. Now we can click on that Runs tab and we would see all the different tasks that have run. Now in our previous demo, we actually executed a quick task directly from the command line. And we can see that that quick task has been recorded as a run. So the same thing would happen that every single time somebody commits code to that main branch and it executes a task, we would have a history of all of those task runs. And we can click on it, and we're going to see all the details associated with that run. So we can see the full log of everything that transpired, how it worked, if there were any issues, etc., etc. And at the very end, we should eventually see our digest that is pushed out. So tasks like this are very good. Source triggers can make sure that every commit produces a fresh image. Digests, of course, let you confirm exactly which version was built as a result. And tags, if you use latest or a specific build version tag, can help deployment systems pull the correct image. And then ACR tasks give you CI-like behavior without needing a full pipeline. So there you have it. In this demo, we went over how ACR tasks can automatically build an image when source changes happen, giving you a simple and reliable way to automate container builds directly in Azure. Great job! In this demo, we're going to talk about a multi-step Azure Container Registry task that builds and tests an image before publishing the final artifact. Now, multi-step tasks are powerful because they let you chain build, test, scan, and publish operations into a single workflow. So instead of manually running each step or relying on external CI systems, ACR can orchestrate the entire sequence for you. And this helps to make sure that only validated images, those that passed your test step, get published to the registry. So imagine you're maintaining a small AI inference service, And you want to build the image, but also run a quick containerized test to confirm that the API responds correctly, and only then publish the final artifact. Well, a multi-step task lets you define each stage clearly. Build the image, run a test container, check the exit code, and publish the image only if everything passes. So let's get started. Now I have the Azure portal open in my browser, and I've specifically navigated to a container registry called SBDemo AI ACR. Now in the left-hand menu, underneath the Services section, let's go ahead and click on Tasks. Now in our previous demo, we talked about tasks and how they operate and how you can create tasks using the user interface, assuming that you have the correct tier of Azure. Now when you create a task, you can define all kinds of different tasks. And one of the tasks that you can create is a multi-step task. And when you do that, you can specify a YAML file that defines the tasks to run. So what I'm going to do is I'm going to flip over to Visual Studio Code and show you what a multi-step task definition would typically look like. So let's flip over to Visual Studio Code, and now we'll see that we have a build and test.yaml file. Now this is a demonstration YAML file. We don't really have to worry about what it's saying in here, but I will still give this file with this demo. All right, so now in this particular file, we can see at the very top on line number 1 that we're defining that there's a series of steps. Then what we can do is define each step. So this is an array in YAML. So we have 3 steps. One on line number 2 defines build. Another on line number 7 defines a command of some kind, and we'll talk about what that is. And then on line 13, we have a push. All right, so let's start with the first command. The first command is build. And what it's going to do is it's going to build an image that's called AI service with a tag called build. Then it's going to use as its context everything that's in the current directory, which in this case has a simple Docker file and a Python file, but we don't need to worry about that. We saw those files a little bit earlier on in this course. Then we specify the name of our Docker file, which is of course Dockerfile as is the standard. Okay, so what that task will do is it's going to build an image called AI service with a tag called build based on whatever we have in this directory. Fantastic, pretty normal stuff. Then on line 7, we have a command. Well, what does this command do? Well, this command runs our brand new image. So it's going to run it, and then after waiting 5 seconds, it's going to run a curl command. And that curl command is going to attempt to call our image on the local host with port 8000. And it's going to use a route called hello. So of course, we're just assuming that our AI service, the actual image that we're building, has an HTTP endpoint with a route called hello, and we're expecting to get a success back from that command. All right, then the next thing that we're going to do is a push. So having reached the point where we've built from line number 2 and we've tested from line number 7, now we're ready to push. Now keep in mind that if any one of these specific tasks fail, then it will not continue. So we know that by getting to line 13, we have successfully completed the build and the test. So the push takes our image, which is AI Service Latest, and it pushes it to a registry. And the registry is called multi-step acr.azurecr.io. Okay, perfect. So now we have the build and test YAML defined with the 3 steps, which is to build, test, and push. So now how would we actually execute this task? Well, there's lots of different ways that we can execute this task. One, we can do it from the command line ourselves, and another is to actually attach it to a repository, just like we talked about in our previous demo, where we can have a GitHub trigger that actually performs this multi-step task anytime someone actually makes a change. So let's review what the command would look like if we wanted to do it ourselves. Now what we can do is I'll expand the terminal down at the bottom of the screen, and let me show you that command. The first part of it would be AZ space ACR, so that's using the Azure CLI, and we're saying that we want to communicate with ACR. Then space task, saying that we want to execute a task, space run. And actually in this case we're saying we want to run a task. We can do other things with tasks, but obviously in our case we're most interested in running a task. Then we would say space -g, and we would specify our resource group name, whatever that would be. Let's just say it's resource group for right now. And then --registry, and now we specify our registry. So now we can see in our actual YAML file that the registry that we were going to use is multi-step acr.azurecr.io, and then space --name. And now what is the name of the task that we want to run? Now in our case, the name is build-and test. Perfect. Now in that particular case, what we would do is we would execute our task, and it would perform all three of those things. The command triggers the multi-step workflow. And during that triggering, we would see the logs for each stage, the build logs, the test logs, and the publish logs. And the end result would be the same as any of the other things that we've been doing so far in this course. We could go and take a look at the list of repositories in ACR, and we would see the AI service repository with the latest tag, and that's exactly what we want to see. Now, all of this means that multi-step tasks can ensure that only tested images get published. They provide predictable build and test environments. They reduce risk by preventing untested images from entering production, and they simplify automation by keeping build, test, and publish logic all in one place, that one YAML file. So there you have it. In this demo, we walked through how a multi-step task can build and test an image before publishing a final artifact, giving you a safe and predictable workflow for promoting validated container images. Great job! In this demo, we're going to deploy a sample containerized AI API from Azure Container Registry to Azure App Service and confirm that the app starts successfully. Now, this workflow is one of the simplest ways to run a containerized workload in Azure without needing Kubernetes or container apps. App Service handles the hosting, networking, logging, and scaling, while ACR provides the trusted image source. Now imagine you've built a small AI inference container, maybe a fast API app that returns a prediction or a simple message. And you've already pushed that image to ACR, and now you want to run it as a web app. App Service for Containers lets you do exactly that with minimal configuration. You point App Service at your registry, provide some credentials, and Azure handles the rest. All right, so let's get started. Now I have the Azure portal open in my browser. And what I'm going to do first is navigate to Azure Container Registry. So I'm going to click on Container Registries at the top of my screen, and we'll notice that I have a container registry called SBDemo AI ACR. If I click on that, then what I can do is in the left-hand menu, I can expand Services and click on Repositories. When I do that, you'll notice that I have a number of repositories already, and one of them is called AI Service. So if I click on that, we'll notice that we have several tags, and one of the tags I have is latest. So I'm going to make the assumption that this particular tag and image in this registry is actually an AI API. Now, what we want to do is we want to create an app service that points to that specific image and tag. So let's get started. Now, what I want to do is at the top of the screen, I'm going to click on the search, and I'm going to select App Service for Containers. And then we're going to select the App Services. And now that's going to show me all the app services that we have in the system. So what I want to do is create a new app service. So we'll click on the Create button, and then we can click on Web App. Perfect. Now this opens the Create Web App wizard, and it's going to guide me through the process of creating an app service. Now what we need to do is select a resource group to put this in, or create a new resource group. Now I'm going to select a resource group that I already have called SBDemo AI ACR. Perfect. Now we can give our instance a name, and this does have to be globally unique. So I'm going to call mine SBDemo AI ACR. Good. And I'll unselect the unique default host name, and we're just going to leave it as SBDemo AI ACR. And now we can select how we want this to deploy. And we can either use code, or we can use a container. So I'm going to select container. Now it's going to say, what operating system do you want? And I'm going to leave all the defaults as they are. Now we can scroll down, we can select a plan, and there's defaults that are provided. For the SKU, however, I'm going to use a very simple plan. I'm going to use a basic B1. That's going to keep my pricing low. It's the simplest tier that supports custom containers. Now we can scroll to the bottom and we can click on the Next button. That'll bring us to database configurations. We don't need one, so we're going to click Next, which is going to bring us to the container configuration. Now here we can select what image source we want. So for our image source, we're going to select Azure Container Registry because that's where our stuff is. Then we can select a name if we want to, but I'm going to leave it as the defaults. Now we can select our registry, and then we can select our specific image and so on. But first we have to select an identity because we need to make sure that this app service is going to be able to talk to that registry. So we're going to say we want to create a managed identity, and it's going to be called this, and we want it to be able to access that ACR. Now we scroll down and we select our image. And remember, our image was called AI Service. And our tag was called Latest. Perfect. These fields tell the app service exactly which container image to run in that registry. If there's a startup command, we can also provide that. Now at this point, that's all the information we need to provide. So we're going to click on Review and Create at the bottom of the screen. This will go off and perform some validation to make sure we've configured the web app correctly. And once it's validated, then we can click on the Create button down at the bottom of the screen. Now, deployment does take some time to perform. So let's give it a second to complete. Perfect, it's done. So now we can click on the Go to Resource button, and this will take us to our brand new app service. Perfect. So now what we want to do is verify that it actually can talk to our container. Now, the default domain that's provided at the top is actually the website as well. So what we can do is we can click on that and it's going to open up another tab. So let's go ahead and give that a try. Perfect. And now we have a result. So that's exactly what we want. Our container is now being hosted by the app service. So now let's flip back to the app service. And now one of the things that we can do is we can start taking a look at all the things that the app service provides us. Now in the left-hand menu, we can expand lots of different things, and one of the items we can expand is monitoring. What we can do here is we can click on metrics, and we can see metrics about our app service. We can click on logs, a health check if you provided one. There's even a log stream. If you click on log stream, you might have to wait a while, but you can look for messages that indicate that the container started successfully or failed, and this will help you to diagnose any issues that might be found. So we can see that during the startup process, it wasn't able to find a robots file or a fave icon, and this is typical for an app service because it's trying to host a website. So now that we can browse to our container and we have an app service, we have a full path. We have the container creation and we have the hosting capability. Now the other thing that we can do is in the left-hand menu, we can expand the deployment section and we can click on Deployment Center. Now in Deployment Center, this is where we can confirm that the registry and repository and tag all match what we selected earlier. We can click on the main container and we can see all the configurations that we provided. So if over time we want to change anything, like which tag we're using or even which image, we can easily do that. So this workflow is useful. It provides a simple hosting environment for containerized APIs. It avoids the complexity of Kubernetes or container apps, and it integrates directly with ACR for secure image pulls. It gives you built-in logging, scaling, and HTTPS, all without any extra setup. So there you have it. In this demo, we deployed a sample containerized AI API from Azure Container Registry to Azure App Service. Great job! In this demo, we're going to configure runtime settings and a key vault reference for an app service custom container. And this is a super important workflow when you want your containerized application to run with environment-specific configuration while keeping sensitive values like API keys or connection strings securely stored in Azure Key Vault. App Service supports both plain runtime settings and key vault references, allowing your container to receive configuration at startup without embedding secrets directly in the image. So let's imagine you're running a small AI inference API inside a container, and the model endpoint or API key must stay secret, but the app also needs runtime settings like logging mode or feature flags. App Service lets you configure both. Simple settings as environment variables and sensitive values as key vault references that resolve securely at runtime. So let's get started. Now I have the Azure portal open in my browser and I've navigated to a app service. And this is the app service that we created in our previous demo, so it's already connected to a container registry. Now what I want to do is I want to apply some app settings, and I want one of them to be secure using a key vault. So in the left-hand menu, what I can do is I can scroll down to the settings section and expand that, and then click on environment variables. Now when I do that, I'm going to get a list of all of my app settings. So what I'm going to do is I'm going to create two settings. I'm going to click on the Add button, and I'm going to provide a name for my new app setting, and I'm going to call it something like logging_level. And then I'm going to give it a value of warning. Now, notice by default the value isn't displayed to me, but it isn't secure, it's just not displayed. I can click the Show and I can see that the value is warning. Now I can click Apply, and now I'll click another Add, and this time what I'll do is I'll provide another name, and this one's going to be something like API_key. And let's pretend that this value was a secure value, like ABC123. It doesn't really matter what it is, but notice that I can still see that value. But the API key is supposed to be a sensitive value. If I click Apply here and then ultimately save these two settings, then you'll notice that I'm going to get these two settings now in the system. And if I show the values, I can see plainly what those values are. So my API key is not secure. It is plain text. Anybody with access to my web app can see it, and if that information is logged by my container, it's going to be displayed in the logs. So this clearly isn't what we want. The logging level is okay, but the API key is not. So what I want to do is I want to change that to be a secure value. So for that, what we need to do is create a key vault. So what I'm going to do is I'm going to click on Overview at the top of the screen and navigate to my resource group. Now I'm going to click Create at the top of the screen, and I'm going to search for Key Vault. Then we're going to select to create a key vault, and that brings us to the Create a Key Vault wizard, which is going to guide us through the process. So let's give our key vault a name. I'm going to call mine SBDemo AI ACR, just because that's the name of everything else in this resource group, but of course we can call it anything we want. We're going to leave most everything as the defaults, other than I'm going to set the soft delete to something like 7 days, which is the minimum. Then we're going to click on Review and Create down at the bottom of the screen. We're going to click Create once again after verification, and this will go off and create the key vault. Now the process doesn't take very long because the key vault is effectively just a container. So let's give it a second to complete. And presto, just like that, it's done. So now we can navigate to that resource, so we're in the key vault. Now what we want to do is we want to create a new key. So we're going to expand the Objects section in the left-hand menu, and notice that we have keys, secrets, and certificates. Now keys are actual keys, and certificates are actual certificates. So generally when we're talking about key value pairs, we're actually talking about creating secrets. So let's click on Secrets. Perfect. Now notice that it says I'm actually not allowed to do this. Now that might seem strange because I created it. Why can't I create any content? Well, that's because being the owner doesn't necessarily mean that you have access to the data. And that's the same thing for our app service. Our app service will also need permissions to view and read secrets. So what we're going to do is we're going to click on Access Control in the left-hand menu, and then we're going to click Add at the top and select Add Role Assignment. Perfect. Now the first thing we need to do is select what role we want to provide to whatever entity we want. So in the search, what we're going to do is we're going to type Key Vault so that we can filter the search down. And then we can see all of the Key Vault roles. If we scroll down, you'll notice that there's two that we care about. One is Key Vault Secret Officer, and the other one is Key Vault Secrets User. Now the first permission I'm going to give is to myself so that I can create secrets. So I'm going to select Key Vault Secrets Officer, then we'll click Next, and now we can select a user to assign this to. So I'm going to click Select Members, and I'm going to search for myself. And I'm going to select myself and click Select, then Review and Assign, and Review and Assign one more time. And now I will have the permission to create those secrets. Now what I can do is perform that same action again, search for Key Vault, and we're going to scroll down until we get to the Key Vault Secrets user. Now this person can only read secrets. So we'll click Next, we'll select a managed identity, and this time we need to select the managed identity of the app service. Now my app service managed identity is actually something that's associated with that app service, and it's called UAID. So we're going to select that, click Select, click Review and Assign, and Review and Assign one more time. And now what that means is that I personally have the ability to create secrets and even read them and so on, and the app service now has the ability to read secrets from this key vault. So now we can click on Secrets. That message has gone away. I can click to generate a secret, and I'm going to give it a name. So I'm going to call it something simple, something like API_key, the same as we had before. Now notice that it is not allowed to have that underscore, so I'm going to remove that underscore. Now we can give the secret value, whatever that is, ABC123, and that's all we need to do. Now we click Create at the bottom of the screen, and this will create the secret. Now if I click on that secret, you'll notice that there's a current version. I can click on that, and now we have a secret identifier. So I'm going to click that. Now we can go back to the actual app service. So I'm going to click on Home at the top of the screen, and I'm going to navigate to the app service because that's a recent thing that I went to. We'll click on Environment Variables, and there are my environment variables, including the API key, which is currently not secure. Well, I want to make it secure, so let's go ahead and edit it. Click on it, and for the value, which I'm going to show so that we can see what we can do, there's a special syntax, and that syntax is @ then Microsoft.keyvault, and then in open brackets and close brackets, or regular brackets, secret URI equals, and then we simply paste that value. And that is now a key vault reference. If I click Apply at the bottom of the screen, and I click Apply one more time, and confirm that this is going to restart our app, then we'll notice that it has changed to be a key vault source. Now it's giving me an issue here, but that's actually unsurprising because it does take time sometimes for permissions to propagate. So it currently is unable to read that secret. But after a little while, it will be able to read that secret because the permissions that we added will propagate. But the important part is that we have regular app service settings and we have key vault reference settings. If we show all the values, we can see that the API key value is no longer a plain text value, but rather a reference. So now when my container starts up, it's going to read these environment variables just like any other environment variable, but one of them will be sourced from Key Vault rather than from the app service itself, meaning that it's completely secure end to end. So there you have it. In this demo, we configured runtime settings and a Key Vault reference for an app service custom container. Great job. In this demo, we're going to inspect container settings and logs to diagnose any app service startup failure. That scenario is extremely common when deploying custom containers. The app might start locally and the image builds successfully, but then once it's deployed to app service, the container fails to boot. So what you can do is you can inspect lots of different surfaces of app service and identify the root cause. That could be a port mismatch, a missing environment variable, or an incorrect startup command. So imagine you've deployed a small AI inference API container. Locally, it runs perfectly, but in app service, the container never reaches a healthy state. So instead of guessing, app service gives you multiple diagnostic surfaces: container settings, log streams, events, and deployment logs. So let's get started. Now I have the Azure portal open in my browser, and I've navigated to an app service that we've been using throughout this course. Now what I want to do is I want to pretend that my app isn't working, that every time I try to access it, I just get a failure. I don't know what's happening. So what I need to do is be able to diagnose what might be happening. And like I said, there's a few different places that you can look to see if it's working. The first port of call generally is to validate your container settings. So in the left-hand menu underneath Deployment, we can expand that and select Deployment Center. In Deployment Center, we're going to see our list of containers. There should only really be one container, but we can see that container and we can make sure that it is configured correctly. So we can click on that container, and this is going to show us the settings of that container. And this is where we would validate that we have the settings properly. And one of the most common failures is that we actually are pointing to the wrong image tag. So at the bottom of the pop-out on the right-hand side of the screen, we can see which image we're using, which image tag we're using, and which port we're connecting to. So the image we're using is AI Service, and the tag name is latest. So imagine that tag name was version 1, and we have since released a version 2. Then we're accessing the system, and for some reason it's just not showing us version 2. Well, obviously that's because we have the wrong tag. Now that isn't a failure per se, it's just not giving us the output that we want. But another common setting is the port. Generally, a container is going to run on its own port. So this is internal inside the system. Commonly, it listens on port 8080, but perhaps we have a configuration of port 8000. So maybe we had an expectation of 8080 and we had configured our port as 8080, in which case that would have been wrong, and that is the source of our issue. So we can verify that the port settings are correct, and then we can try again. Now let's say that all seems correct, but it's still not working properly. Now the next thing that we can do is verify all of our configurations. So we can collapse the deployment section, and we can expand the settings section, and we can click on environment variables. Now when we click on environment variables, it's going to show us all of the configurations that we have applied in the system. And so in our case, we have a couple of app settings, and we created those app settings in our previous demo. We have API key and we have logging level. Now API key is actually using a key vault as its source. And notice on my screen that it actually does have a red X indicating that it is not configured properly, or perhaps that we don't have access to it. So right away, this is giving us an idea of what could be wrong. Now, in my case, there actually isn't an issue here because it just takes time for that key vault reference to know that it actually does have permissions. But let's pretend that I didn't have the permissions. Now, this would be obviously a key indicator that I've set this up wrong. So what I can do is I can click on the API key and I can take a look at the reference and make sure that I have typed the reference correctly. And if I have typed the reference correctly, make sure that I've actually got the permissions that I need to key vault. Perfect. Now let's say that's all working correctly and everything's good there. And it's still not working. Well, what's the next thing that I can do? Well, the next thing I can do is I can actually scroll down to the monitoring section and I can expand that. In the monitoring section, I can take a look at health checks if we have health checks configured. I can take a look at application insights if I have application insights configured, and those will provide some details about what might be going on. But another thing that you can do is you can actually take a look at a log stream. Now, generally this will appear underneath the monitoring as specifically log stream, but sometimes it won't appear. If it doesn't appear, then you can enable it using diagnostic settings, but it does take some time for it to appear. But you can still nevertheless click on logs, and when you click on logs, you can inspect some past logs. It's just not going to be a log stream. And what you would do is click on the tables in the left-hand side, and that will allow us to view all of the tables that we have in the system. But again, you have to turn on the diagnostic settings to do that. But there is another way to access that log information. So what we're going to do is we're going to open up the deployment section once again, click on Deployment Center, and at the top of the screen you'll notice that there's a Logs tab. Well, we can click on that, and this is going to go off and fetch all the logs associated to the container that is attached to this app service. When we look at that, we can see quite a lot of logs that tell us precisely what it's doing, the ports that it's listening to, the actual download of the container, what it's mounting, etc., etc. So you can see it can be pretty verbose, and it can provide us all the information. This is very valuable because it's going to tell you specifically which image was downloaded. It's going to provide us information about the versions that were downloaded, and this is going to tell us if there's any issue at all. Basically, this helps us to confirm that the image was pulled successfully and that there were no errors in trying to run it. Now, all these logs and details are of course going to be specific to your container and what it does and the configuration of your app service itself, but these are the areas that you can check anytime that there might be an issue. So there you have it. In this demo, we inspected various container settings and logs that would help us diagnose an app service startup failure. And this is all being done using App Services diagnostic surfaces to identify an issue and ultimately confirm a fix. Great job! In this demo, we're going to look at how to deploy a sample AI service image from an Azure Container Registry to Azure Container Apps and verify both ingress and runtime settings. Container Apps is a great fit for lightweight AI APIs because it gives you serverless scaling, simple networking, and built-in environment management without requiring Kubernetes expertise. So imagine you've built a small, fast API-based AI inference service, maybe a simple predict endpoint, and you've already pushed the image to ACR, and now you want to run it in a managed environment that handles scaling and ingress automatically. Container Apps makes that easy. You select your image, you configure ingress, you set environment variables, and Azure handles the rest. So let's get started. Now I have the Azure portal open in my browser, and what I want to do is I want to create a container app. So what we're going to do is we're going to click the Create Resource button in the top left corner of the screen, and we're going to search for Container App. Perfect. Now we'll select to create the container app. Perfect. Now this brings us to the Create Container App wizard, which will walk us through the process. The first thing we have to do is select a resource group, and I'm going to use a resource group that I've already got called SBDemo AI ACR. So we'll click that. Now we can name our container app, and I'm going to call mine SBDemo AI ACR just because that's the name of everything else in this resource group. Perfect. Now we can scroll down and we can select our deployment source. And in this case, we're going to use a container image. Then we'll scroll down and there's the container apps environment selection. And we're just going to leave everything as the defaults right now. Now we can click on Next, which will bring us to the container configuration. Now at this point, we can select our container information. So our image source is Azure Container Registry. Now we can select a registry, and I have a registry that we looked at a little bit earlier called SBDemo AI ACR. Then we can select an image. So let's say it's AI Service is the name of my image, and then we can select a tag. And in my case, I'm going to select latest. So just through some simple selections, we already have our container selected for our container app. Now we can scroll down, and if there's any command overrides or arguments or anything like that, we can select it. But again, I'm going to leave everything as the defaults. Now we can click on Next to get to ingress. And let's say we do want to be able to access this for HTTP, so we're going to turn on ingress. And then we can select the information that we need for it. So what's the target port? Well, the target port in my case is port 8000. So we're going to select that. And everything else is just fine the way that it is. With the exception of where the traffic comes from. We can either have it be limited to the container apps environment, or we can allow traffic from anywhere. And we're going to select that because we want to be able to access it from external sources. Now we can click Next to get to tags, which we're going to leave alone. We're going to click Review and Create, wait for the validation. Once that's passed, then we can click Create again. Now this will go off and create our brand new container app pointed at our specific image that is in ACR, which is precisely what we want. So the deployment doesn't take very long, but let's give it a second to complete. And perfect, just like that, the deployment is complete. So now we can click on Go to Resource in the middle of the screen, and this will take us to our brand new container app. Now from here, we can do all kinds of different things. We can provide some settings and we can inspect any issues that might be going on. But what we want to know is whether or not we can actually talk to our container. So at the top of the screen, there's an application URL. And you'll notice that it has a crazy name on it like lemon mushroom or whatever yours might be. But regardless, that is the URL that we have. So what we can do is we can actually access that. So we can click on it and it'll take us to another screen. So let's go ahead and do that. And presto, we actually get our sample output. So fantastic. That means that our container app is successfully talking to our container in ACR with very, very simple configuration. Now this workflow matters because container apps provide serverless hosting for containerized APIs. Ingress gives you a secure public endpoint without extra networking setup. Runtime settings let you configure behavior without rebuilding the image. And integration with ACR makes sure that everything is secure and you're using trusted image pulls. So there you have it. In this demo, we deployed a sample AI service image to Azure Container Apps and verified both the ingress and runtime settings to make sure that the containerized API was running successfully. Great job! In this demo, we're going to look at how we can update images or change settings in Azure Container Apps. And revisions are one of the most powerful features in container apps because they let you introduce changes gradually, test new versions without impacting users, and roll back instantly if something goes wrong. So imagine you're running a small AI inference API and you've pushed an updated image. Maybe it's a new model version, or you want to change a runtime setting like a feature flag. So instead of replacing the running version outright, container apps can create a new revision automatically. You can test it, compare behavior, and then gradually move traffic to the new version. So let's get started. Now I have the Azure portal open in my browser, and I've navigated to the container app we created in our previous demo. Now in the left-hand menu, there's a section called Applications. And underneath that, there's an option called Revisions and Replicas. So we can go ahead and click on that. And this will give us a list of all of the revisions and replicas that we have. And notice that we only have one active revision. And this makes sense because we only have the one container that we've deployed so far. So now let's say that we have a new version that we want to deploy. So at the top of the screen, we can click Create New Revision. And if I select on that, then I'm going to be able to select another container to use. But before I do that, I need to make sure I have the right deployment mode. So I'm going to close out of that. And at the top of the screen in the toolbar, there's another button called Deployment Mode. And if I click on that, then we can see that we have single deployment and we have multiple revisions. Now this is exceptionally important because if we have single deployment turned on, then the second I add another revision, it will become immediately available. So what I want to do is select multiple revisions. So we're going to select that option and then click Apply at the bottom of the screen. This will then go and update the app, and we'll wait for that to complete. And presto, we're updated. So now let's go click to create a new revision. So now we can give it a name. So let's just give it something simple like version 2. Then we have the current container image that is currently being deployed. Now, this isn't going to change what's actually being deployed. It's just saying that what is this revision pointed to? And by default, it points to what it's already pointed to. So we're going to select the checkbox next to the name. We'll click Edit. And now what we can do is we can select which tag we want to use. So now we're going to select version 2. Everything else stays the same. And now what we can do is click Save at the bottom of the screen. Now what this means is that we now have a new revision that is pointing at a specific tag. Now we can click Next, which will bring us to Scale. And this allows us to change the scaling just like we would any other revision. But I'm going to leave it alone, and we're going to click Create down at the bottom of the screen. And with that, it's going to go off and create another revision, which means that now both latest and version 2 are going to be available. Now we'll see that there's one active revision and there's some inactive revisions. So we can click on that, and this is going to show us all the inactive revisions, of which there's none. We can also click on replicas, which is going to show us all of the replicas. And again, if we click on active revisions, we're going to see our 2 revisions because it has since updated. So we can see that everything is currently going to the previous container that we have, and no traffic is going to version 2. So what we could do is we could label version 2 so that it's accessible to other people, and let's just call it label 2 just so that it looks like the other one. And now what we can do is we can say, okay, we're going to have 10% of traffic go to version 2, and 90% of traffic continue to go on the version that we want. This will give us a bit of a canary. Now we can click Save, and what that means is that as traffic accesses our container, it's going to go to version 2 10% of the time, and to our regular one 90% of the time. Now we can view the details and the logs for that new version, and we can know that if everything is working correctly, then we can increase that percentage over time and eventually get to 100%. And in fact, we can go ahead and click on the Show Logs, and if we click that link, it's going to show us all the current logs associated with that container. So we can see that it started up and that there isn't any issues. And of course, if there are issues, they're all going to appear here. And this is going to give us the ability to detect if there's any problems. And if there are problems, then of course we can change the traffic and simply set it back down to 0 and set the other one back to 100%. Click Save, and with that, the new version 2 is no longer accessible to anyone. However, over time, if it works well, we can change the traffic to something like 50-50. And that means that 50% of traffic goes to the new version and 50% of traffic comes to the original version. And again, we continue to do some validation, and if everything is working correctly and we're feeling more and more confident, eventually, like I said, we get to the point where traffic is 100% to the new version and 0% to the old. And with that, we would now be completely going to the new version. Now, the old one remains an active revision. We can keep it there. It becomes the last known good version. So if somewhere down the line that version 2 is actually not working well, or we have started to encounter a problem, we can come back into this system, switch the 100 and the 0 so that all the traffic immediately goes to the old version, and everything is good from there. So there you have it. In this demo, we deployed an updated image and created a new revision. Then we showed how to safely shift traffic between revisions to complete a controlled rollout. Great job! In this demo, we're going to look at how to configure an event-driven scale rule in Azure Container Apps that responds to queue or message pressure. Event-driven scaling is one of the most powerful features of container apps because it lets your application scale based on real workload signals instead of CPU or HTTP traffic alone. So by connecting your app to a queue, like Azure Storage Queues or Service Bus, you can scale replicas automatically as messages accumulate, making sure that your AI service keeps up with demand. So imagine you're running an AI inference worker that processes messages from a queue. And when the queue is empty, you want minimal replicas. But when the queue grows, you want more workers. Well, event-driven scaling lets you define exactly how many messages should trigger additional replicas. So let's get started. Now I have the Azure portal open in my browser, and I've navigated to a container app that we've been using so far in this course. Now what I want to do is I want to manage scale. So in the left-hand menu underneath the Applications section, there's an option called Scale. So let's go ahead and click on that. Perfect. So now what we're going to see is we're going to see the rules that are already configured. And I have an HTTP scaler configured with min and max replicas of 0 to 10. Now what that means is that I have a minimum number of replicas of 0, meaning I can have absolutely no replicas running at all because there's no traffic coming to my container. And I also have a maximum number of replicas of 10, which means that if I suddenly get inundated with a lot of traffic, I will scale up to be able to handle it, but I won't go beyond 10. So now let's say I want to create a scale rule that is based on queue messages. So rather than my container being based on HTTP traffic, let's say it's based on queue traffic, where messages go into an Azure queue storage, and then my app responds to that. So what I'd want to do is create a scale rule in case I suddenly get inundated with messages, or in fact have no messages at all. So let's do that. Now at the top of the screen, there's a button called Edit and Deploy, so I'm going to click on that. Now this is going to bring me to where I can configure my container. Now I don't want to configure my container, I want to configure the scale rules. So there's a tab called Scale at the top of the screen, so I'm going to click on that. And from here is where I can configure my scale rules. So let's say I don't want my minimum replicas to be 0. I want it to be 1. Because if it is 0, then it can do nothing at all, which is great for cost, but it means that there's going to be a cold start consequence. So generally for HTTP scaling, I want the minimum number of replicas to be 1. So I would set that. Now, in a queue-based system where it isn't a user that's necessarily interacting with it, then 0 is actually a good option because it means that when there's no work to do, there's no replicas that you're paying for. So this is completely up to you. But now what I want to do is I want to create a scale rule based on queue pressure, not based on HTTP scaling. So at the bottom of the screen, there's a Scale Rules section and an Add button. So I'm going to click on Add. Now this will bring me to the Add Scale Rule section, and here I can provide a name for my scale rule. So let's say it's something like queue pressure rule. Perfect. Now we need to select the type of our rule. And if I hit that pull down, you'll notice I have 3 options. HTTP scaling, which is what I have already, Azure Queue, and a custom preset. Now we care about queues, so let's go ahead and click on Azure Queue. Perfect. So now it's going to ask us for details about our queue. So we would have to name our queue, and we would have to give it a queue length. The queue length is when the queue has a certain number of messages. So let's say that we have a queue out there, and its name is sbdemo queue. And then we can provide our queue length. And let's say I set that value to 5. Now that means when the queue has 5 or more messages, then we need to scale out. So keep in mind that our number of replicas is 0 to 10, and 5 messages really isn't a lot. If we had all 5 messages, then there would be 5 replicas working on it. So maybe we want to expand when we have more messages than we have the available replicas. So maybe we set something to 50, or we can set it to 500, whatever we would want. Basically, all these values define the operating boundary for the worker. Now, down at the bottom of the screen, we need to provide a link between our container app and that queue. It isn't a free lunch to simply talk to the queue and gather messages. You need to be able to connect to that queue and have the permissions to do so. So what we can do is we can select to authenticate with a managed identity, which is typically the best option. It means that your container app, which runs with a managed identity, will communicate with the queue using that managed identity, which means that you can give your app, the container app, permission to the queue. Now you also need to specify your account. And this is just details of the queue some more. Now I'm not actually going to proceed with this because I don't have a queue at the moment. But once I have all that, then what we would have is we would have another scalar rule down at the bottom of the screen. We would have an HTTP scalar, and we would have a queue pressure scalar. And keep in mind that you can have both of these things. You can have your container app respond to standard manual HTTP requests, but you can also have it respond to batch jobs that are happening behind the scenes based on queues. And now what we can do is we can scale based on that HTTP traffic, and we can scale based on queue pressure. And all the rules for how to spin up and spin down the number of replicas is joined together. So your HTTP scalar defines when to scale, and so does your queue pressure rule. It just defines when to scale up and when to scale down. And then your scale rule settings at the top of the screen are specifying your minimum and maximum number of replicas that you can scale up and down to. Now, all of this is great because event-driven scaling helps to make sure that workers respond to real demand. And queue pressure is a reliable signal for asynchronous workloads. And scaling rules can prevent over-provisioning and reduce your costs. So when you're doing a lot of work, you can make sure that you don't go beyond a certain point. And if you're doing no work at all, you can make sure your number of replicas is really low to keep your cost low. Basically, Container Apps makes the configuration simple and secure. So there you have it. In this demo, we went over how event scaling works within a container app. Great job! In this demo, we're going to use logs and replica information to diagnose Azure Container App deployment and scaling issues. Now, Container Apps provide several diagnostic surfaces, revision details, replica status, console logs, and event logs that can help you understand why a deployment isn't behaving as expected. So imagine you've deployed an AI inference API to container apps, and you expect it to scale based on HTTP traffic, but instead replicas remain stuck at 1, or a new revision fails to start. Well, rather than guessing, Container Apps gives you clear signals, which includes replica states, startup logs, scaling events, and revision level details. So let's get started. Now I have the Azure portal open in my browser, and I've specifically navigated to a container app that we've been using so far in this course. Now what we want to do is we want to take a look at scaling. So let's imagine that we are having a scaling issue. Lots of traffic is coming in, but we seem to be stuck at one replica no matter what. So in the left-hand menu underneath Application, we can click on Scale. And we can click on that and see what our configurations are. So we can see that our min and max replicas are 0 to 10, and that's good. That means that we have it configured properly. We also have an HTTP scaler, and that's good as well. It means that we have a scaling rule defined that says that we should scale up or down. Now, if our min and max replicas were something weird, like 1 to 1, then that would explain why you're not getting any scaling, because both your min and max replica counts are the same, so it's not going to scale up or down. But in our case, it is 0 to 10, which means that there is a range there. So what we could do is click on the scale rule, the HTTP scaler, and we could take a look at the rule itself to see what the rules are. Now, in this particular case, we're seeing that the concurrent request is set to 10, meaning if there's up to 10 concurrent requests going on, then that's going to require a scale up. Now, if we had set it to some crazy number, like 1,000 or 1,000,000, then that would explain why we're not getting any new replicas, because we simply aren't getting the volume that we've configured. So, assuming that everything is set correctly, then everything should work correctly. Now, let's say that scaling is working correctly, but we're not getting a proper revision. Nothing is working the way that I expect it to. Well, for that, what we can do is we can click on Revisions and Replicas in the left-hand menu underneath Application. When we do that, we can see what our current revision deployment looks like. So I might have multiple revisions that are out there, and one of the things that we'll see on the Active Revisions tab is which revisions are currently active. If the expected revision that you want is not listed there, then immediately that tells you, oh, it's because I haven't deployed my revision, or at least it's not set to active, and you can make the adjustment. If, on the other hand, it is listed, then the next thing you can do is actually take a look at the traffic column. And the traffic column will tell you how much traffic is going to which revision, or at least how much is configured to go there. And in our particular case, we have some traffic going to v2 and no traffic going to the original version, which is this 6EXX. So what that means is that if we had actually expected traffic to be going to that original revision, then we can see that our traffic simply isn't configured properly, and that's why it's not going to that revision. So then we would change our traffic, and at that point everything should be resolved. Now, let's say that we actually do want traffic to be going to version 2, and in fact, we can see that 100% of traffic is going to version 2. So at that point, we might wonder, okay, what's going on? Is my revision working or not working? Well, to determine that, we can click on the Show Logs link underneath the View Logs column. And if I click on that, it's going to show me all of the logs that are currently running. Now, this requires that the container is being accessed. So right now, there's no active replica running. And that makes sense because if we go back to our scale, we do allow our scaling to go down to 0. So I'd actually have to change that scaling to allow 1. But what I can also do is I can simply connect to that specific revision and traffic will start to flow. In fact, just as I'm talking, traffic must have started to flow, so we can see that it is now running. So once again, we can click on Show Logs, and this time we should actually see some logs for whatever it is that somebody tried to do just now. And so we can see that there was a successful connect, it started up, and it's starting to give back a response. Now, if there's a problem connecting to this specific revision, or this revision isn't working correctly, then it will appear in the logs. Now, in this case, of course, everything is successful, but if something wasn't working, then we would be able to see all of it and display that information. This gives us the ability to figure out what might be going wrong and then resolve the issue. And each time we dig, we're getting to different layers of the application. So is the problem in the container app? Is the problem in the scaling in the container app? Is the problem with the rules in the container app? And eventually, once we get to the logs portion, we're actually saying, is there a problem in the app itself, our container? Perhaps there's something wrong with ACR, or perhaps there's something wrong with the configuration that we have pointing to ACR, or maybe ultimately there's a problem with our image inside that container. So, why does this all matter? Well, obviously, replica information can show whether scaling is happening. Logs can reveal both container behavior and platform decisions. Scaling events explain why replicas were and were not created. And revision details can help to confirm the configuration changes. Together, all these surfaces make diagnosing deployment and scaling issues predictable and repeatable. So there you have it. In this demo, we went over how to diagnose container app failures. Great job! In this demo, we're going to apply a Kubernetes manifest for a sample AI worker and then verify the deployment, the pod, and service status inside the cluster. Now, let's imagine you have a lightweight AI worker that processes tasks from a queue or API, and you want to deploy it quickly, confirm it's running, and make sure the service endpoint is reachable. By applying a manifest, Kubernetes takes care of creating the deployment, spinning up pods, and exposing the worker through a service. All right, so let's get started. Now, on my screen, I have VS Code, and specifically, I'm looking at a manifest file. And don't worry, I'll provide the file with the demo. Now, the file is named aiworker.yaml, and what I can do with this file is I can define a deployment with one replica and a cluster IP service. The service uses port 80 externally and forwards traffic to port 8080 inside the container. Now, the cluster IP is the simplest service type because it exposes the worker internally without requiring any load balancer or ingress. Now, the actual content of our manifest isn't super important other than to say that I am defining a deployment on line number 2, and if I scroll down, we can see on line 22 that I'm creating a service, and that service is the cluster IP. Now, what we want to do is we want to apply this manifest to our cluster. So down at the bottom of the screen, I have the terminal open in VS Code, and I'm going to run some kubectl commands that is going to deploy this manifest to my local Kubernetes. Now, I have Docker Windows turned on with Kubernetes enabled, but of course, you can connect to any Kubernetes instance, including Azure Kubernetes or AKS if you'd like to. All right, now let's issue a command to apply this manifest. Now, to do that, we can type kubectl space apply space -f space and then our file. So that would be aiworker.yaml. So I'm going to execute that. Now, when we apply the manifest, Kubernetes creates the deployment and the service automatically. And we can see on the screen that's what it says it did. Now, after the manifest is applied, we can verify the deployment status. And we can do that by typing the command kubectl space get space deployment and then the name of the deployment. And if we scroll all the way to the top of our manifest, we can see that the deployment name is AI-worker. So AI-worker. We'll execute that. And this is going to show us how many replicas are desired, how many are updated, and how many are available. Good. Now, the next thing that we can do is we can actually check the pod status. So let's do that. I'm going to clear the screen again. And now we can run another Kubernetes command. And this is kubectl space get space pods space -l space app equals AI-worker. Now, using a label selector like this makes sure that we only see pods that are belonging to this specific worker. We'll go ahead and execute that, and now we can see a message. Now, the message we're seeing is that the status is an image pull back off, and that just means that the actual container that we're trying to load, the image that we're trying to load, is incorrect. And that's fine. That's not really important for the purposes of this demo. What we want to see is the status of deployments and of pods. So now let's say we want to describe that specific pod. Maybe we don't understand why that status is image pull back off. Well, we can gather more intelligence by issuing some more kubectl commands. So we're going to type kubectl space describe space pod, and then what we need to do is we need to give the pod name. So now that we've did the get pod command, we can copy that name and paste it. And we can go ahead and execute this, and this is going to give us events, container status, readiness information, and we can scroll through all of that information to determine what might be going wrong or just to get information about that pod. So we can see lots of information, its IP address, the various labels, etc., etc. And if I scroll all the way down, we're going to see the events. And in the events is where we're going to see that it was unable to pull certain images. Now, the other thing we can do is we can confirm the service itself. That's the cluster IP. So we're going to go ahead and clear the screen once again, and we're going to type kubectl space get space service space and then the name of the service, which again, if we look at the manifest and scroll all the way down to the bottom where we define the service, the name was AI worker. So we're going to type AI-worker, and we're going to go ahead and execute that command. Now this is going to confirm whether or not the service exists and then show the cluster IP that's assigned by Kubernetes. So in this case, we can see that the service does exist and that its IP is 10.108.122.58. And we can also see that it's using port 80. Now, services also create endpoints, so we can validate the service endpoints by issuing another command. And that would be kubectl space get space endpoints space AI-worker. And now we can see the endpoints, and we only have one, and it has the name of AI worker. So this tells us whether the service is correctly routing to the pod. Now, because our pod isn't working, because we have the wrong container image in there, no endpoint is actually being provided yet. So at this point, we can see that we have issues and we can resolve those issues. And we're able to detect those issues by running all of these various kubectl commands. And with those kubectl commands, we're able to narrow down where the issue might be, and we were able to very quickly diagnose that there's an issue with the container image that we're providing. So we could scroll up, we can find the container image, and we can determine, oh wait, this is the wrong image. We don't want to use this one. Let's use a different one. So let's go ahead and change that image to something that works. Now, we have a simple HashiCorp HTTP echo, and if we use that command, it's going to echo whatever arguments we give it. And in fact, I can provide some arguments simply by typing args on the next line, and then in an array, I can provide all the different arguments. So maybe what I want to do is I want it to echo some text. So I'm going to say the text equals something like hello world. And then we need to provide which port we want to listen to. So that might be something like -listen, and then the port number, which of course we know is already written down at the bottom, which is 8080. So we're going to provide that. We're going to save it. And then what we can do is we can go down to the bottom of the screen, and we can simply run that command again to apply the YAML file. And this is going to apply the updated manifest. And then we could run through all the various commands again, and this time we would see that everything is working. But we don't have to issue all the commands because we know that the final command that we wanted to run was to get the endpoint. So if everything is working, then the endpoint should be available. So we can go ahead and execute that command, kubectl get endpoints, execute that, and if we have an endpoint, which we do, then we know that everything worked. And we were able to do that simply by applying manifests to Kubernetes. So there you have it. In this demo, we applied a Kubernetes manifest for a sample AI worker and verified the deployment, the pod, and service status to make sure that everything was running as expected. And if it wasn't, we were able to diagnose what was wrong and resolve that issue quickly. Great job. In this demo, we're going to change a Kubernetes manifest's image tag, apply the update, and observe how Kubernetes performs a rollout and replaces pods during the update. Now, this is one of the most important behaviors to understand when working with containerized AI workloads because image updates are the most common trigger for new deployments. So imagine you have an AI worker that's running in production, and you've just published a new version of the container. And you want to update the cluster, confirm that Kubernetes replaces the old pod safely, and verify that the rollout progresses without errors. By changing the image tag in the manifest, Kubernetes automatically handles the rollout and ensures that the new version becomes active. All right, So let's get started. Now I have Visual Studio Code open on my screen, and I have a manifest that's actually open at the moment. It defines a simple deployment, and in that deployment there is one replica, and if we scroll down through, it actually uses a simple container from Google, which is a Hello app. Now notice that it's using a tag of 1.0. Now that means that with 1.0, what we're actually getting is version 1 of that image. So let's deploy this. Now to do that, we can go to the terminal at the bottom of the screen, and we can type kubectl space apply space -f, and then the name of our file, which in this case is aiworker.yaml. And don't worry, I'll provide this file with the demo. Now if I execute this, it's going to say that it's applied. Now what we can do is we can search for all of our pod. And we can do that using the command kubectl space get space pods space -l app equals AI-worker. Now we go ahead and run this, and we can see our pod. Fantastic. Now that's good news. Now what we want to do is confirm which image version it's using. Now to do that, we can type a simple command of kubectl space describe pod, and then we can copy and paste the name of that pod. So let's go ahead and do that. Now if we paste it and run, we're going to get a lot of information. And right down at the bottom, we can see that it has pulled version 1.0 of the pod. So that's an easy way to see that in the events. If we scroll up, we can see a whole bunch more information about the pod itself. And that's great news because it helps us to understand what's going on. But one of the things it also gives us is the image that it pulled down. So we can see that it's using Hello App 1.0, which is precisely what we've asked it to do. So now let's say, as we said in our example, we have a new version. And what we want to do is we want to apply that new version. So what I'm going to do is I'm going to go ahead and clear the screen. Now what I'm going to do is in the AI worker YAML file at the top of the screen, instead of version 1.0, I'm going to change that to version 2.0. Then I'm going to save the file, and then I can apply it. Now, before I apply it, what I actually want to do is I want to watch the transition of version 1 to version 2 in real time. So what I can do is I can type kubectl space get space pods space -w. The W flag lets us watch pods being created and terminated in real time. So I'm going to go ahead and execute that command, and we can see all the pods that are currently running. Now, in a separate window, I can actually execute that same apply command that we ran before. So it's going to apply the exact same manifest, but now it's going to see that the image that we're using is version 2.0 instead of version 1.0. Now, when that happens, it's going to determine that a new pod is required to host version 2.0 and that the old pod of version 1.0 is no longer needed. So what we should see on the screen is that the AI worker that we're using should eventually be spun down and goes away, and that we should see a new AI worker become available. Now, because this is watching in real time, it's not going to replace what we see. We're going to see several lines being added. So I'm going to go ahead and execute that command on another screen, and now we can see what's happening. Now, at this point, we're seeing all the actions that are being taken. And in the end, it should stop, which it already has, and we can see what it's done. So let's review what it has done. Now, at the top of the screen, when we started, we had AI Worker 5F4. Then we had some demo app, which we can ignore for the purposes of this demo. Now we can see that a new AI worker, because it has a different ID, was spinning up. So we can see that it was pending, it was still pending, and then it says the container was creating, and then it says it was running. Now we can see our original AI worker started terminating, and now it's just gone. Now this is important. Notice that the new worker spun up before the old worker came down. That first worker had to be in a running state before the other one was terminated. So now what we can do is we can break out of this, and we can clear the screen, and we can issue some additional commands. So at this point, we can perform a kubectl space get space deployment, and we pass in our AI worker name, and we can see that it's healthy, it's up to date, everything is running just the way that it should. And then what we can also do is we can run another command, which is kubectl space rollout space history space deployment space AI-worker. Now this is going to give us rollout history for that deployment. And we can see that we do have one piece of history, which is that there was a change. So in other words, we had revision 1 and then we had revision 2. Doesn't really give us a change cause, but that's not really super important. But we do see that there have been, in fact, 2 revisions, which is exactly what we expect. Now, by following steps like this, we can change the image tag, we can apply various updates, and then we can watch Kubernetes replace the old pod with the new one. And this is the simplest and most common workflow for updating containerized workloads. So there you have it. In this demo, we changed a manifest image tag, we applied the update, and we observed Kubernetes performing a rollout and replacing pods with a new version. Great job! In this demo, we're going to inspect a pod failure using kubectl describe, Kubernetes events, and container logs so we can understand exactly why a pod is failing and how Kubernetes reports that failure. Now, this is one of the most important troubleshooting skills for anyone working with containerized AI or application workloads because failures often begin with subtle signs that appear in pod status, events, and logs. So let's imagine you deploy a worker or an API container and it immediately starts or never reaches the running state. Now you need to quickly determine whether the issue is related to scheduling, image pulling, startup behavior, or application logic. And Kubernetes provides all the signals that you need, but you need to know where to look and how to interpret them. All right, so let's get started. Now I have VS Code open in my browser and I have a manifest file open. Now this is the exact same manifest that we used in our previous demo, except I've made one alteration. Now what we can see is that we have a deployment and I've named it AI Worker. In this deployment we have a simple container, and it's a Google sample container called Hello App. But notice that I have a label of bad tag. Now you and I both know that that's not going to be a real tag, so it's not going to work. But these types of labels can often be an issue. So imagine you have a label that gives a version number of something like 1.0.1. Now those version numbers are very important. It tells you things, a major, a minor, and a patch. But let's say that you put a typo in there. You meant to say version 1.1.0, but you wrote 1.0.1. Now that happens all the time, but you don't necessarily notice that right away. You try to deploy the manifest and it doesn't work, and you don't know why. So what we need to do is we need to be able to investigate why it isn't working. So let's go ahead and try to perform this deployment. So what we're going to do is at the bottom of the screen in the terminal, we're going to deploy our manifest. So we're going to type kubectl space and then apply space -f for the file, and then we're going to give our aiworker.yaml file. Now if I execute this, everything seems normal. We can see the deployment was configured, everything is great, oh we're super happy. But meanwhile, nothing's working, and we don't know why. So we need to figure out why it's not working. So the first thing we're going to do is get information about our pod. So we can type kubectl space get space pods -l for label, and then app equals AI worker. So this will allow us to get our specific pod. So if we go ahead and execute this command, we're going to see information about our pod. Now notice that I happen to have 2. Well, that's because I had a pre-existing AI worker, and now I have a new AI worker that I'm trying to spin up with a new version. Now this is really good news. Now what this is telling me is 2 things. One, that I have an existing AI worker that was using a particular version and it continues to run. So it hasn't been shut down yet because the new one isn't working. And we can see the new one isn't working, and we're getting a status of image pull back off. Now that is usually our first sign. It's telling us that there's something wrong with our image. Now there could be lots of different things that is wrong with our image, In our case, we know it's the image tag, but let's say there's something wrong with the image itself. It's having problems starting up. Or perhaps we have the wrong repository. There's lots of different reasons why image pull back off can happen, but it does point us at the image being the issue. So now the next thing that we would ask is, okay, what's going on specifically? So what we can do is we can run another command, which is kubectl space describe space pod, and then we can copy and paste our worker. So let's go ahead and copy and paste its name, and then we'll execute that command. And now we can see all kinds of information about the pod, which is fantastic, including that its state currently is image pull back off. Now we can see the image that we're using, and we can see bad tag that's in there, but maybe it doesn't stand out to us. That's actually the issue. Again, we saw 1.0.1 versus 1.1.0, and we're just not seeing it very clearly. So we can scroll down, and we can see the list of events. And the events will tell us what it's trying to do and when it failed. So again, we can see that it's definitely having a problem pulling that specific image. So this is telling us there's got to be something wrong with that image. It simply can't find it. Now that's either a bad repository or a bad tag. So now at this point we would know, oh, we must have a bad tag or something. Now let's say we still don't really see that. Maybe we want to see that maybe there's something wrong with the app itself inside that image. Well, what we can do is we can go ahead and issue a command to get the logs. So we can say kubectl space logs space, and then we can give our worker name. So in this case, it'd be AI-worker, and then we'll just use a simple command, which is -- previous. Now, if we go ahead and run that, it might sometimes fail depending on the configuration of your container. So we can see that it's not necessarily going to work as a direct pull. Sometimes we have to apply the labels like we did in our previous command to go and get the pods. So we can say -l space app equals AI worker. If we go ahead and run that, it's going to go and find us some information. Now, at this point, we don't have any logs, and that's actually expected. And the reason we don't have any logs is because we never got that image. So there was no startup. We didn't get logs from the image because there was no image to get logs from. So at this point, we would know, oh, okay, so we have the wrong tag. So we can go ahead and fix that tag. So let's use version 2.0. We'll go ahead and save that. And then we can apply the command once more. And it's going to tell us that everything is great again. So we'll go ahead and clear. And then we're going to issue the command to go and get the list of pods again. And this time we can see that it is currently running, but that the other one is in a state of image pull back off, which again, we sort of expect. And we might have to run it a few times until eventually it's just going to go away. Now, the other thing that can happen as well is effectively what we've just done is we've performed what's called a rollback. So we decided, oh, we don't want that one tag anymore. Let's go back to version 2. So what we can do is we can change that tag to a different number. But it has to be a number that works. So we either have to fix the tag or we have to change the version. Now in my case, I actually still have an error in here. Rather than version 2.0, it should just be 2.0. So I actually gave it my own problem again. So now if I go ahead and apply one more time, then I can go and see the list of pods. Now we can see that we only have one running, and it's the one that we expect to be running. So those two types of things can happen. You have to be aware of what you're rolling back to. You have to be aware of what your image tags are. And if at any problem you have, then you can take a look at the logs. You can take a look at the pod description. You can take a look at events. And every single one of those things is going to give you a hint as to what might be going wrong. So in our case, we had the wrong image label, and we actually did it twice. And then once we had the right image label in there, all the errors went away. So there you have it. In this demo, we inspected a controlled pod failure using kubectl describe, events, and even container logs to understand exactly how Kubernetes reports and explains pod issues. Great job! In this demo, we're going to review AKS workload health and diagnostic signals. This helps us to understand how Kubernetes workloads behave, how to spot issues quickly, and how Azure surfaces the most important operational data. And this is one of the most valuable skills for anyone running containerized applications or AI workers in AKS because the platform provides rich, curated dashboards that help you to troubleshoot without needing deep Kubernetes expertise. So imagine you deploy an application and want to confirm that the nodes, pods, controllers, and containers are all behaving correctly. Maybe a workload is running slowly, maybe a pod is restarting, or maybe you just want to validate that everything is healthy after a new deployment. Well, Azure Monitor and Container Insights give you a single place to see performance, health, logs, and events. Now, in this demo, I'm assuming you already have AKS deployed. Now, we don't want to modify the cluster. Instead, we just want to explore the monitoring experience and interpret the signals that it provides. Now, I have the Azure portal open in my browser, and I've navigated to an AKS cluster. Now, what we want to do is, in the left-hand menu, we want to expand the monitoring section. Then, as we scroll down, notice that we have access to alerts, metrics, diagnostic settings, and more. Sometimes you'll also see dashboards with Grafana. Now, what we want to do is we want to access Container Insights. In most cases, it's going to appear under Monitoring simply as Container Insights. In other cases, it might appear somewhere else in the menu. But you can always access it from the Overview tab. Now, if you scroll down on the Overview tab, you'll notice that there's some sub-tabs: Get Started, Properties, and Monitoring. Now, under the monitoring section, if you scroll down, you're going to see all kinds of information about your specific cluster. But if you scroll all the way down to the bottom, you'll notice an item called Container Insights. Now, we can see that my Container Insights is configured. So if I go ahead and click on that, it's going to take me to Container Insights. Now, Container Insights provides curated dashboards for nodes, controllers, and containers. Now, right away on the overview screen, we can see all kinds of information about how many nodes we have, how many pods we have running, namespace, CPU, etc. So we can see all kinds of information right away on the overview screen, which can give us an overall feeling of how our system is running. And we can take a look at these charts and decide whether or not anything requires our attention. We can also cycle through the various tabs at the top of the screen so that we can get information about specific items that we care about. So for example, if we click on Nodes, we're going to see information about our individual nodes. In my case, I have 2 nodes, and so we can see information in terms of how many containers are running on each of the nodes, what uptime we're looking at for each of the nodes. Maybe one of the nodes is giving us problems and it's time to replace it or scale it up. The other thing that we can do is we can click on Controllers at the top of the screen, and this is going to show us all the controllers that we have running, and we can just cycle through all of that. Now, one of the things that we've been doing throughout this demo, of course, is that we've been creating some dummy containers. So now let's go ahead and click on the Containers tab, and this is going to show us all the containers that are running. Now, this includes the containers that run in Kubernetes in order to support Kubernetes. So in order to have our Container Insights, we need to have Prometheus running and so on, so we can see a Prometheus collector. And if we scroll through, we can see all the various other containers which are just built into Kubernetes or required for the various monitoring that we have. And we can keep scrolling and scrolling, and we can eventually find what it is that we're looking for. And once we find one of those things, then we can simply click on an item and see what it is that it's doing. So let's go ahead and click on this manager as an example, and then we can see information about its controller. We can expand it, and we can see more and more information about what that specific controller and that specific container is doing. Now, if we go back to containers, we can even search for a container. Now, I could search for the AI-worker that we've been using so far in this course, and I'm not going to find it because what we're looking at here is a cloud-based Kubernetes, or AKS, whereas I was running Kubernetes locally. But if I had deployed it to AKS, I could simply search for that container, and I would find it and be able to take a look at its specific health. We can also take a look at networking and see how traffic is flowing between the various systems and nodes. And we can click on dashboards so that we can see some already curated dashboards. So there are some featured dashboards, or there are some dashboards that we can create ourselves. Now, the better interface for doing that is to click on Dashboards with Grafana in the left-hand menu, and you're going to get a similar screen to what we just looked at, including some featured dashboards. And in fact, if we click on one of them, we're going to see that dashboard. But like I said, you can create your own dashboard, but oftentimes the curated Grafana dashboards are all that you really need. Now, another thing that you can do, of course, is you can peruse your individual logs. So we can click on Monitor and we can see all the various dashboards. That's fantastic. But the other thing that you can do is in the left-hand menu, you can click on Logs. And if you click on Logs, this is going to allow you to peruse various logs associated with your Kubernetes implementation. Now, we're not going to go into that detail, but you can understand how looking at individual logs might give you even more information than just the dashboards. The dashboards will give you an overview. They'll let you know what's going on, or at least where to look for something that's going on. The logs will allow you to go a little bit deeper to see precisely which errors are happening if that's something that you're looking for. So there you have it. In this demo, we reviewed AKS workload health and diagnostic signals using Azure Monitor and Container Insights to understand how Kubernetes workloads behave and how Azure surfaces operational data for troubleshooting. Great job! In this demo, we're going to connect to a Cosmos DB for NoSQL container by using Python and then run both a point read and a query so you can see exactly how the SDK reaches data, handles identity, and returns structured results. Now, this is one of the most common workflows for developers building AI workers, APIs, or background processors that need fast, predictable access to documents. So imagine you have an application that needs to retrieve a specific item, like a user profile, a job request, or a configuration document, and also run a broader query to filter items by a property. Now, Cosmos DB for NoSQL is optimized for these patterns, and the Python SDK makes the process pretty straightforward. Now, this demo assumes you already have a Cosmos DB account, a database, and a container created. And we're going to focus entirely on connecting and performing reads. We'll also create a small Python file so that you can run locally on Windows. All right, now let's get started. Now, I have Cosmos DB open on my screen, and what I've done is I've created some containers. So I have a simple database called DemoDB, and I have one container called Demo Container, and I could have many other containers in that database, as well as I could have many databases. Now, within this single container, I'm taking a look at all the items in that container. Now, I've created 5 items, and they're very simple. They have 3 properties that we care about: the ID, the primary key, and a value called type. Now, for each of these items, we can see that they have a simple ID, ID1, ID2, ID3, 4, 5. And they all belong to a specific primary key, meaning that they're belonging to a partition. So this partition key, or primary key, depending on how you like to call it, but typically it's called a partition key. For these 5 items, I have 3 of them in the first partition called PK1, and 2 of them in another partition called PK2. Now, if we were to inspect each of these items, we would see the third value, which is the type, is either sample or widget. So if I look at ID1, we can see that it has ID1, PK1, and sample. If I click on item 2, it has ID2, PK1, and sample. So ID1 and ID2 are actually virtually the same other than their ID. Now, if we look at ID3, it also belongs to the first partition, but it's a type of widget. ID4 is in a different partition. It's also a widget. And ID5 is still in that same second partition, but its type is sample. Okay, so now we have various types of data in our Cosmos DB container. So now we're going to turn our attention to a Python script. So I'm going to head over to Visual Studio Code. And in Visual Studio Code, what I've done is I've created a simple Python script. And don't worry, I'll provide it with the demo. Now, at the very top of the Python script, we're importing the Azure Cosmos SDK. So this is going to allow us to talk with Cosmos DB. Then at the top, we're defining certain variables that we're going to use throughout the process. We provide the endpoint to our Cosmos DB. We provide the key so that we can talk to that Cosmos DB. And then we provide the database name and the container name. Once we have all that information, then on line 9, we're able to create a client. Once we have the client, we're able to connect to the database within that client. And once we have the database, we can connect to the container within that database. So you can see the hierarchy of information there. Now what we're going to do is we're going to perform two operations. One is a point read, and the other one is a query. So let's start with the point read. Now on line number 14, we provide the ID of the item that we want to read, and we provide the partition key, or the primary key, again, depending on your preference in naming. Again, I prefer partition key. Once we have those two bits of information, then we can talk to the container object and say that we want to read a specific item. We provide that ID, we provide the partition key, and it should give us back the item. Then we're just going to print that item to the screen. Now, at the bottom, we're going to also perform a query. Now, the query is a simple SQL query. So we're going to say select star from C, which is our container, where the type is sample. So we have a type field, as we saw, and we had two different types that we had, a sample and a widget. So what we're saying is we want to select all of the ones that are a specific type of sample. Then we use container.queryItems, meaning we want to perform a query. We provided the query, and then what we can do is we can also enable cross-partition querying, which means that we can say, I don't know where these are. I don't know which partition these samples are in, so just give me all of the items that have a type of sample. Then we get that in results, and we print it to the screen. So let's go ahead and execute that command. Now what we can do is we can type Python space cosmos-demo.py, which is of course the name of my file. We'll go ahead and execute that command, and we should get a result on the screen. Now that result is pretty gross because of course it's the raw JSON that we get from Cosmos DB. But we can see point read result. We can see that the ID is ID1, which is what we asked for, that the partition key is PK1, and the sample is the type. Then, of course, we see all the other information associated that Cosmos DB provides with all of the items, but we can ignore that for the purposes of this demo. Then we have the query results, and we can see that this is coming back as an array as denoted by these square brackets. And we can see ID1 is in there because it has type sample. We can also keep looking and we see ID2 is in there because it has the type sample. And then we see ID5 is in there because it has the type of sample. But we don't see ID3 and we don't see ID4. So if we go back to Cosmos DB and click on ID3, we can see that its type is widget. So of course it wasn't returned. And ID4 also has a type of widget, and of course it wasn't returned. And ID5 was returned even though it's in a different partition because we said we wanted to do a cross-partition query. So there you have it. In this demo, we connected to Cosmos DB for NoSQL container using Python and performed both a point read and a query to understand how the SDK retrieves data. Great job. In this demo, we're going to run 3 query variants against a Cosmos DB for NoSQL container and compare their RU charges and returned results so you can see how query shape directly affects cost and behavior. Now, this is one of the most important skills for anyone building AI workers or APIs because RU charges reveal how efficiently your queries are accessing data. A simple use case for this scenario is when you're tuning a workload that performs frequent reads. Maybe you want to reduce cost, maybe you want to improve latency, or maybe you're trying to understand why two similar queries behave so differently. By running multiple variants side by side, you get a clear picture of how filters, projections, and partition keys influence RU consumption. So for this demo, we're going to create a small Python script that runs 3 queries and prints both the results and the RU charges returned by Cosmos DB. All right, so let's get started. Now I have that script that I just talked about on my screen. Now I'm using Visual Studio Code to do this, but it's a simple Python script. We use the Azure Cosmos SDK, and then at the top of the screen we're providing the endpoint to my Cosmos DB instance, the key, the database that I want to use, and the container name that I want to use. Then on line number 9, we create a client, which is the connection to Cosmos DB. On line 10, we create a database, which is the connection to the database called DemoDB in this case, but within that Cosmos DB. And then we have a container, which is a container in that database, which is in that Cosmos DB. Now on line 13, what we're doing is we're defining a function. This function is called runQuery. We're going to give it a label, and then we're going to give it the query. So the idea with this function is that we're going to give it a query to execute. And when it does that, it's going to print out the list of returned items, the results that it got from whatever query we provided. Then it's going to print out the RU charge, which is how many RUs did we use to execute that query. Now this allows us to have a reusable query runner. We can execute the exact same function every single time. It'll tell us which query you're running, what items were returned, and what was the RU charge. Then we can scroll down to the bottom and we're going to see the 3 queries that we want to run. One is very simple. It's the same query that we ran in our previous demo. Select star from the container where the type is sample. Now this is the simplest query. It simply says get me everything in the entire system that has a type of sample. For query 2, what we're doing is very, very similar. We're saying the same where clause, get me everything that has a type of sample, but we're saying I only want the ID and the type. I don't want anything else. Then for query 3, we're going to run the same query as query 1 once again, but what we're going to do is we're going to say this time, only give it to me from partition key 1. Now what we can do is we could actually create a query 4 if we want to. Now let's do that. We're going to say, we're going to put both of those things together, both the projection in terms of what we specifically want and the limitation of the primary key. So we're going to say c.id, c.type from c, where ctype equals sample and cpk equals pk1. So whether you call this primary key or partition key is totally up to you. It's interchangeable. Generally speaking, in Cosmos DB, we call it a partition key, but sometimes it's called a primary key as well. Okay, then what we can do is we can run those queries. So let's go ahead and add another query down at the bottom. We're going to say we're going to run query 4, which is a filter which includes the partition key and projected fields. And then we're going to say we want to pass query number 4. So now we can save that, and now we can go ahead and execute the command. So let's go ahead and do that. What we can do at the bottom of the screen is type Python space, and then the Cosmos demo py, which is of course our file. So we're going to go ahead and execute that. It's going to go off and perform the connection and perform those various queries. So now let's scroll up. Now what we're seeing is we're seeing a query that says go get everything. So that was of course our first query, which we can see at the top of the screen, and I'll allow us to see us a little bit more there. And this is select star where type is sample. So we saw that in our previous demo as well. It gives us everything. And it says the total RU charge is 2.87. Then for our next query, we said I just want specific fields where the type is sample. And it has given us precisely what we're looking for, just those particular fields. But we can see that the RU charge is about the same. Now, what's a little tricky here is that it also depends on how much is in your system anyway. If I had 1,000,000 items, then in that particular case, I would expect that my projected field query would actually be quite a few less RUs than the full document query, because it's simply returning less information. But because there's only 5 items in my container, the number of RU changes is actually not that much different, but we can still see it anyways. In our next query, we're saying select star from the container where the type is sample and the partition key is pk1. In this case, it actually didn't return anything. Now, the reason for that is simply a typo. Now, what we can do is we can actually change the pk from pk to pk1. And if we do that, then we can save and run the command again. And this time, we're going to get different results, but we also get different RUs. And this is important to understand that it's not just the queries that can affect your RUs, but also the data that you get back or that is in the system. So obviously in our particular case, we don't have a lot of data in the system, so the number of RUs doesn't change a lot, but it is going to change things. So now in our third query where we said let's get everything from that specific partition key, we did get back some data. Now, interestingly, it was more RUs than the first one, which actually returned more data. And the reason for this is actually pretty straightforward. The reason that this is happening is not just because our query has changed, but because the number of conditions in our query has changed. And because we have less data being returned, this should mean less RUs, and generally speaking, that's exactly what would happen. But because we don't have a lot of items in our container, it's actually resulting in a larger query, and that's returning the same amount of data. So now, interestingly, what we would need to do is we would need to scroll up and take a look at our actual query execution, and perhaps if we know specifically which partition we are looking at, we can state that we don't want this to be a cross-partition query. At any rate, then we come down to our fourth query where we combine both of the options and we still get an RU charge. And that extra RU charge is once again because we have that extra condition. But if you scale out the amount of data that you have, this would ultimately be the cheapest type of query that you can run, where you know the partition and you can provide specifically the type of data that you want returned. Each of these types of changes is going to result in an effect on your RU cost. And that's precisely what we want. So by being able to print out the RU charges that you're incurring, you're able to determine which query is most efficient for what it is that you're trying to do in your particular case. So there you have it. In this demo, we ran multiple query variants against Cosmos DB for NoSQL, and we compared their RU charges and returned results to understand how query shape influences cost and efficiency. Great job! In this demo, we're going to look at indexing policies and consistency settings in Cosmos DB for NoSQL, and then we're going to explain how each one affects a known query pattern. Understanding these two features is really important because they directly influence query performance, RU cost, and the freshness of the data your application reads. So imagine you have a query that filters on a few fields and returns a small set of documents. You want to know whether the indexing policy supports that query efficiently and whether the consistency setting ensures that the data is fresh enough for your workload. By reviewing both settings, you can determine whether the query is optimized or whether adjustments are needed. Now, this demo assumes you already have Cosmos DB accounts, a database, and a container. We're going to focus on reviewing the indexing policy and consistency setting in the Azure portal and explain how they affect a specific query pattern. So let's get started. Now I have the Azure portal open in my browser already, and I've navigated to a specific Azure Cosmos DB account. Now what I want to do is I want to take a look at the scale and settings. Now these settings are actually different for every individual database and container. So what we want to do is we want to click on Scale and Settings, or just Settings, for the container. So we can see underneath the container, when I go to the Data Explorer, that there's an item called Settings. So I can click on that, and this is going to show me all of my settings for that specific container. The first thing we want to look at is the indexing policy. So there's a tab called Indexing Policy, so I'm going to click on that, and it's going to show me the policy in a JSON format. This is where Cosmos DB defines which paths are indexed and how they're indexed. So we actually have two items here, the included paths and the excluded paths. Included paths tell Cosmos DB which fields need to be indexed. And if our query filters on fields like type or category, then those fields need to appear in the list of included paths. Now in my particular case, I have the default included path, which is simply /star, which means that every single property is indexed. Then we have the excluded paths. Now the excluded paths removes fields from indexing. So large or unused or internal fields are often excluded to reduce write cost and storage overhead. Now in my particular case, I have the default excluded path, which is the e-tag property that is associated with every item, and Cosmos DB puts that in there by itself. Now, if I go and click on items again and take a look at any one of my items, you'll see that in fact it does have an E tag, and every single one of them has an E tag, and all the ones that are underscored are the ones that Cosmos DB is adding. Most of them are in fact useful for querying, but E tag is not. So if I go back to settings, click on the index policy, I will notice that of course Cosmos DB by default says let's remove E tag from the list of paths that are indexed. And then there's the indexing mode, and that's right at the top of the JSON. In my case, the indexing mode is called consistent. Consistent indexing means that documents are indexed synchronously as they're written, and this makes sure that queries always use up-to-date indexes. Now, of course, for a container, there's lots of different settings. We already went through all those, where we can set the time to live, geospatial configuration. There's container policies. We already looked at the indexing policies, partition keys, and various computed properties as well. Now, the next thing that we want to take a look at is the consistency setting for the account. Now, that's the important part, is that consistency settings are applied at the account level. So in the left-hand menu, let's expand the settings section, and then we can click on default consistency. And at the top of the screen, we're going to see what the possible consistency values are. We have strong all the way through to eventual. Now, strong consistency ensures the freshest data but can increase the latency. So if we click on that, we're going to see that it's ready to make those changes. Session consistency, which is the default, is the most common choice because it guarantees read your own writes behavior. And then eventual consistency provides the lowest latency but might return slightly stale data. Now, I'm going to leave it as the session consistency, but it's useful to understand how it works. And notice that there is a visualization that's happening down at the bottom of the screen that shows what this type of consistency means. And just to hammer that home, what we're going to do is we're going to go back to the Data Explorer in the left-hand menu. We're going to navigate to our container, and then what we actually want to do is we want to create a query. So at the top of the screen, let's go ahead and click on New SQL Query, and this is going to allow us to now run a query. So let's run a simple query. We're going to say select star from C, which is our container, where space c.type equals sample, which is something that we've done multiple times throughout this course. So we'll go ahead and execute that query, and then we get results down at the bottom of the screen. Now, why is this important? Well, let's talk about consistency, and specifically, let's talk about strong, session, and eventual. With strong consistency, this query will always return the latest committed data. With session consistency, the query will always return whatever data I've written, but otherwise it's going to return fresh data for the current session, which means that somebody else might be doing some writes, and I might not get it right away, but I certainly will get my writes right away. And with eventual consistency, the query might return slightly older data, and that's acceptable for background processing, but obviously not ideal for real-time reads. So whichever consistency you choose has to match whatever your query patterns or application requirements are. So there you have it. In this demo, we reviewed an indexing policy and consistency settings in Cosmos DB for NoSQL. We explained how each one affects a known query pattern, so you can understand how to optimize both performance and data freshness. Great job! In this demo, we're going to review some vector policies in Cosmos DB for NoSQL and then execute a vector search against sample documents so you can see exactly how the database stores embeddings, indexes them, and retrieves nearest neighbor results. Now, vector search is becoming a core pattern for AI applications, and Cosmos DB native vector support makes it easy to combine structured queries with semantic retrieval. So imagine you have documents that are enriched with embeddings, maybe product descriptions, knowledge base entries, or AI-generated summaries, and you want to retrieve the most semantically similar items to a user query. By configuring a vector policy, Cosmos DB knows which fields contain embeddings and how to index them. Once the policy is in place, you can run vector searches directly through the SDK. All right, so let's get started. Now, I have the Azure portal open in my browser, and I've navigated specifically to an Azure Cosmos DB account. Within that account, I have a database called DemoDB and a container called DemoContainer inside that database. In the container, I have three simple items. If I take a look at each item, we can see that it has an ID1, ID2, and ID3, and that they all belong to a different partition. So partition 1, partition 2, and partition 3. So each are in their own partition, and each have their own unique ID. Now, if we look at each one of those items, we can see that it has text. And that text is just some random text. We don't really need to care too much about that text for the purposes of this demo, but it also has an embedding. And the embedding is an array of numbers that provides us some information about that text that models can use. If I look at each of the individual items, they all have their own text and they all have their own embedding that describes the semantic meaning of that text. Okay, perfect. So we have our data. Now the next thing that we're going to need is we're going to need to have a query that actually queries for this data. Now what's important here is we need to make sure that we have vector policies turned on. So what we need to do is go to the settings for our container and then click on Container Policies. Once we do that, you'll notice a tab called Vector Policy. So we can click on Add Vector Embedding. So we'll click on that. Now what it's going to ask for is, well, where is the embedding? So if we go back to our item, we'll see that we had embedding was actually the name of the property. So we'll go back to settings and we'll type /embedding. Perfect. The data type is a float32. It is an array of those types of numbers. And then we need to select how many dimensions. So now if we go back once again to our list, we can see that we have 4 dimensions for embedding. So what we need to do is set that the dimensions is 4. Perfect. Now we're going to leave all the rest of the defaults as they are, and we'll make sure that we save the changes by clicking Save at the top of the screen. This will save the embedding changes, and presto, we will now have a vector policy, which is exactly what we want. So now that we have the policy and we have our sample documents, now we can actually perform the queries that we want to. All right, now I have Visual Studio Code open in my screen, and I happen to have a Python script, and don't worry, I'll provide this Python script with the demo. Now, the purposes of this script is to run an embedding style query against our Cosmos DB instance. So what I have is I actually have 2 imports. I have the Azure Cosmos SDK and NumPy. These 2 are going to allow me to talk to Cosmos DB and to talk to it in a specific way as relates to the numbers that I'm going to pass in, which is the embedding. Now right away, what we have on line 10, 11, and 12 is our connection to Cosmos DB. Line 10 provides a client, which allows me to connect to Cosmos, and I pass in the endpoint and a key. Then on line 11 and 12, I connect to the database, DemoDB, and then on 12, I connect to the container within that database, which is called DemoContainer. Now on line 14, I create an embedding. Now this embedding is actually the numeric equivalent of the user's query. So the user is going to ask for certain bits of information. And from that, we can create what's called an embedding. What is it that they mean to ask for? Now this is important. What we need is for that embedding to be created in the same way as the data that we have in our database. Meaning in our database, we have embeddings for all the data that we already have in there, and it has 4 dimensions. So when we create our embedding for the query itself, it also needs to have 4 dimensions, which is exactly what we see here. So we're using NumPy to create that array. Then we can create a query, and the query says, let's go get some information. And what we do is we say, only get me 2 values. The thing I care about is the ID of the item in the database, and then we need the vector distance. So tell me what the actual distance was from the query to what is in the database. We can then use that information for 2 different things. One, in the same query, we can see that we're doing an ordering. So we want to get the items in the order that their embedding distance actually gives us. So what we're seeing here is we're going to get 2 values. It's ordered by that vector distance, and we're going to get the top 2 values, which basically means we're going to get the 2 closest matches. Now, the other reason that this is important is because even though we're going to get two values, getting back the vector distance will allow us to determine whether or not it's still too close or too far away. So for example, let's say you were asking about cars, and then it gave you back something about peanut butter sandwiches. Those things might be close in terms of the vector distance, but they're still not related, and so you might still decide that you don't actually have any good responses. Then we create our query spec. The query spec has the actual query in it, and it has parameters. So we're going to pass in that query embedding. And then the last thing we're going to do is actually perform the query, get the results, and display the results on the screen. So let's go ahead and do it. So what I'm going to do is I'm going to type Python space and then the name of the file, which in this case is Cosmos demo. We'll go ahead and run that. It will perform the execution, and we get back our results. So we get back two results. One is ID1, the other is ID2, so that matches our top two. And then we see the similarity score of 0.04 for the first one and 0.05 for the second one. And because item 3 ranks lower, its embedding is further away, and so it's not included in the result. So there you have it. In this demo, we reviewed and configured a vector policy and executed a vector search against sample documents to understand how Cosmos DB performs semantic retrieval. Great job! In this demo, we're going to run a similarity search with and without metadata filters and compare the returned context so you can see how filters shape retrieval behavior in Cosmos DB for NoSQL. Now, this pattern is really important for AI applications that need precise grounding. Sometimes you want broad semantic searches, and other times you want semantic matches restricted to a specific category, partition, or document type. So imagine you have documents that are enriched with embeddings and metadata, like category, source, or timestamp. Your application might need to retrieve semantically similar items, but only for a certain subset, like only items from category A, or only items created this month. By comparing filtered and unfiltered similarity search results, you can understand how metadata constraints can refine context. Now in this demo, we've created a small Python script that performs two searches. One, a pure similarity search using only the vector, and two, a filtered similarity search that adds some metadata constraints. Now don't worry, I'll provide this script with the demo. So let's get started. Now at the top of the screen, we are importing some needed SDKs, the Azure Cosmos SDK and NumPy, which allows us to create some arrays. On lines 10, 11, and 12, we connect to Cosmos DB, we connect to the database within that Cosmos DB, and then we connect to the container within that database within Cosmos DB. On line 14, we create a query embedding. Basically, what we're doing here is we're saying there's a request from a user, we've converted that request into an embedding, and then we want to search all of the items in Cosmos DB against that embedding. We basically want to perform a similarity search, find all of the items that are similar to what it is that the user is asking for. Now, if we scroll down, on line 16, we have an unfiltered query. Now, this query doesn't really do anything in terms of filtering, hence unfiltered, but what it does is it says, get me the top 3 documents ordered by vector distance, and the two values I want to get back are the ID of that document and the category of that document. And then we're just going to simply order by the similarity score. So this is saying, get me the top 3 most similar items, which is a pretty normal query to run. Then we create an unfiltered query spec, which takes that text and creates a query, and then we have parameters that we pass in. In this case, we pass in the query embedding. So what we're saying is, get me all the values that are close to this embedding. Then we create a filtered query. So if we scroll down, we can see on line 29 that we create another query, which looks pretty much identical, with the exception of we've added a where clause. So in this particular case, we're saying, get me all of the items that have a specific category. So this is metadata now that we are querying against. So get me all the most similar ones of this specific category. Then we create another spec, and we pass in the embedding again, and we pass in the actual category that we want to constrain to, which in this case is AI. Now, if I flip over into Azure and take a look at my actual database in Cosmos DB, I can see that I have 3 items in my container, ID1, ID2, and ID3. Now, if I take a look at them all, you'll notice that there is a category. And for ID1, we have a category of General. For ID2, we have a category of AI. And for ID3, we have a category of General again. So if ID2 is the only one with a category of AI, then the filtered query that we just looked at should only return ID2. Now we can scroll down and we can see the actual execution of those 2 queries. So we'll execute the unfiltered similarity search, and then we'll execute the filtered similarity search, and we will output the results for both on the screen. So let's go ahead and run this command. To do that, we can type Python space and then cosmos demo.py, which is the name of my file. And once again, don't worry, I'll provide it with the demo. Now we can go ahead and execute that command. It's going to go off and perform the searches. So now we can see at the bottom of the screen the results of those 2 searches, the unfiltered search and the filtered search. So the unfiltered search returned me 3 items because I asked for the top 3, and it's ordered by the similarity. So we can see that ID1 has a similarity score of 0.04, ID2 had a score of 0.05, and ID3 had a score of 1.13. So it's ordered it by 1, then 2, then 3. Then we have the filtered search. And remember, the filtered search said only give me the ones that have a category of AI. So it's giving me back the same types of results, but it's filtered. It's only going to give me what I'm actually asking for. Both searches behave as expected. Unfiltered similarity search retrieves the closest semantic results. Metadata filters restrict results to a subset of documents. Combining vector search with metadata filters produces more precise context for AI applications. So there you have it. In this demo, we ran similarity searches with and without metadata filters, and then we compared the returned context to understand how filters can refine semantic retrieval in Cosmos DB. Great job! In this demo, we're going to go over how to implement a small change feed processor that detects updates in Cosmos DB for NoSQL containers and records the item IDs that need embedding refresh. This pattern is really important for AI applications that maintain up-to-date embeddings, because any change to a document's text or metadata could make its stored vector stale. A lightweight change feed processor lets you automatically track which items need refresh work. So imagine you have a vector-enriched container and you want to regenerate embeddings whenever a document changes. So instead of scanning the entire container, the change feed gives you a stream of updates, and your processor can record items into a queue, a log file, or a tracking container. Now for this demo, we're going to implement a small Python-based change feed processor using the Cosmos DB SDK. And this processor is going to detect updated items and record their IDs into a simple log file. All right, so let's get started. Now, I have on my screen Visual Studio Code, and in Visual Studio Code, of course, I have a Python file. And don't worry, I'll provide this file with the demo. Now, importantly, what we have at the very top is we have some libraries that we're importing. So we're importing the Azure Cosmos SDK, and that's the most important one. This is what's going to allow us to actually talk to Cosmos DB. And in fact, that's the very first thing that we do on line 11, 12, and 13. We actually make that connection. So on line 11, we connect to the Cosmos account using the endpoint and the key that are on line 6 and 7, which of course you can replace with your own values. Then on line 12, we use the client to gather a database reference. And then on line 13, we use that database reference to get a container reference within that database. So with that, we have the entire hierarchy of connection. Then on line 15, we just print to the screen that we're going to start our change feed processor. So at this point, we're going to see on the screen that we're starting, and then we're going to actually see all the changes as they come in. So how do we do that? Well, that starts on line 20. So as I scroll down, you're going to see on line 20 that we have a while true. Now this is just an infinite loop. It's going to sit there and continue to run forever and ever and ever. on line 22, what we're doing is we're actually connecting to the change feed processor. Now you'll notice that we also do this on line 27, and the reason is because we have or don't have a token. So in certain cases, we might need to continue to collect information. So imagine there were a huge number of changes. In that particular case, we won't necessarily get all the changes all in one shot. In both cases, we say, let's go get the last 10 changes. And so what if there's more than 10 changes? So in that particular case, I can go and get the rest of the changes that happened. And that's through the use of a continuation token. But otherwise, it looks exactly the same. One, we're starting from the beginning. The other, we're continuing from the last call until we get them all. But in both cases, we simply go and get the list of changes from the container. Now we scroll down, and in fact, on line 34, we take those changes that were given to us and convert it into a usable list. This is going to allow us to iterate a lot easier. Then, if there's anything in that list, because it's possible that there were no changes, then we display all of it on the screen. So we're going to print, we found a certain number of changes, and then we are going to iterate over them using a for loop. So for all the changes that we see, we're going to actually show the change and the ID of the item that was found. Then, like I said, there's a continuation token if there are more changes than 10, and then we continue with the loop forever and ever. If there's any exceptions during that time, then it will end the loop. And then, of course, we loop. Okay, so now what we're going to do is we're going to actually run this script. So to do that, we're going to go down to the terminal at the bottom of the screen, and we're going to type Python space, and then the name of our file, which is cosmosdemo.py. And again, I will provide this file with the demo. If I execute that, now what I should see is a list of all the changes that have happened so far. And then we simply sit and wait for any new changes. So let's go ahead and see if that's what happens. So we'll execute the Python script. It says it's starting the feed reader, and in fact, it has found 3 updates, and it gives the IDs. There was an update to number 1, number 2, and number 3. So now, if I head over to the Azure portal, and in fact go straight to my Cosmos DB instance, then we can see our 3 items in the middle of the screen. And what I'm going to do is I'm going to take one of my items, and I'm going to change something about it. Now, generally, the thing that's going to affect the embedding is going to be the text. So what I'm going to do is I'm going to change the text. Now, that won't actually change the embedding, but it's something that we care about. It would be a signal that says to us, hey, we probably should change the embedding. So if I just add a v2 on the end of this, just so that we know, I can then click Update at the top of the page, which is going to save that change. And great, now we have a new change in Cosmos DB. But if I go back to our script, we should now see that there was one update, and in fact, we can see that it was ID1 that changed. And I can do that for any number of them. I can go change ID3, and I'll put a v2 on the end of that as well. Click Update, go back, and now we can see that it was ID3 that changed. And just like that, we've created our own very simple change feed processor. Now, a change feed processor is extremely valuable, of course. It delivers item updates in the order that we got them. A simple processor can detect changes, record the item IDs, and help you with your workflows. But there you have it. In this demo, we implemented a small change feed processor that detects updates and records item IDs for embedding refresh. And this gives you a lightweight way to keep AI workloads synchronized with document changes. Great job! In this demo, we're going to connect to an Azure database for PostgreSQL from Python and run create, insert, and query operations so you can see exactly how a simple application interacts with a managed PostgreSQL service. This workflow is very common for AI workers, APIs, and background processors that need structured relational storage alongside Cosmos DB or other NoSQL systems. Now, a simple use case for this scenario is when you have an application that needs to store metadata, relational references, or configuration records in PostgreSQL. And you want to connect securely, create a table, insert a few rows, and run a query to confirm that everything works. Python's psycopg2 library provides a straightforward way to do all of that. So with this demo, we're going to create a small Python script and run it locally on Windows. You'll need your PostgreSQL server name, database name, username, and password from the Azure portal. In fact, this demo assumes that you've already got an installation of PostgreSQL in Azure. Now on my screen, I actually have the Azure portal open, and I've navigated to an Azure database for PostgreSQL that I already have. Now what I have in this PostgreSQL instance is a single database called DemoDB. The rest of the databases that are there are the ones that come with PostgreSQL when you first install it. So we're going to focus on DemoDB. Okay, so now that we have that database and we can see it plainly there, what we want to do is we want to interact with that database. Now that interaction with the database is going to be done using a Python script. So I'm going to flip over to Visual Studio. Perfect. Now in Visual Studio, what I have now is a Python script that I will provide with this demo. On line number 4, 5, 6, and 7, I provide some variables, and these variables are going to allow us to connect to a database. Then on line 10, we actually perform that connection. We use the psycopg2 import to perform a connect operation. We pass in the host, the database, the user, and the password, and we make sure to set SSL mode to require. This makes sure that our connection is actually encrypted. Now the next thing we do as we scroll down is we can see that on line 18 we create a cursor. Basically this is our connection to the connection. It's allowing us to execute certain commands. So it might even be better to refer to it as a command interface. So as we scroll down, we can see the various commands that we want to execute. Our first command is going to be to create a table called items inside that database. So our database is called, as we scroll back up, DemoDB, and we saw that we actually had that in PostgreSQL. Now what we're going to do is we're going to create a table inside that database, and it has 3 simple properties: ID, name, and category. Then we're going to commit that, which means that it's going to go off and create that table, but only if it doesn't exist. And this is good because it means it's idempotent. It means I could run that command over and over and over again, and it will create it if it doesn't exist, but if it does exist, nothing's going to happen. Then we can scroll down and we're going to insert a few sample rows into that database. We're going to insert widget A with a category of general and widget B with a category of premium. But notice that we don't provide an ID. And that's because our ID is a serial primary key, which means the ID is going to be created for us. Once we've inserted those sample rows, then we're going to perform a query to get them all back and just make sure that they're in fact all there. Then for each of the results that we get, we're going to output them to the screen. So let's see this all in action and make sure that it works. All right. So down at the bottom of the screen, I have a terminal open in Visual Studio Code, and now I can go ahead and execute the command. So what I'm going to do is I'm going to type Python space and then the name of the file, which is PostgreSQL demo. So let's make sure that we type that correct. PostgreSQL demo. And again, don't worry, I will provide this file with the demo. So now I can go ahead and execute that. Now this should go off and create that table. It should insert those 2 values, and then it should return the data that's in the database, and then output all of that to the screen. So let's give it a second to complete. Now notice that we have a failure. It's actually failing to perform the connection. Now this is very strange. Why should it fail to perform the connection if I've provided all the appropriate connection details? Well, the answer is it's a protection mechanism from Azure. Azure actually will not allow the connection because it doesn't allow public connections. You have to actually allow your own IP address. So what we need to do is we need to go back to Azure. And then what we need to do is click on the networking option in the left-hand menu of our database. And then what we need to do is we need to add a firewall rule that allows my client IP address access to the database. Now, sometimes it won't pull the right IP address, so it's useful to look at the error message and see that it's trying to use a specific IP. And we can copy that, or if the address up at the top is correct back in here, then we can use that too. Now, this is the right IP for me, so I'm going to go ahead and click that. That creates that IP rule that now allows me to have access. So I'm going to go ahead and click Save at the top of the screen. It's best to obviously name the firewall rule, something like your home or whatever it is that you might want to use, your office. It doesn't matter, it's up to you. Now in this case, I'm going to leave it as the default name. Now I can go back to the code. I will clear the screen so that we can see, hopefully, an appropriate output. So let's go ahead and run it again. And this time we do in fact see the query results. So there you have it. In this demo, we connected to an Azure database for PostgreSQL from Python. We ran a create table command, we ran some inserts, and we ran some query operations to understand how applications interact with managed relational storage. Great job! In this demo, we're going to enable the vector extension in Azure Database for PostgreSQL and then create a table designed to store embeddings and metadata so you can support vector search workloads. This pattern is becoming increasingly important for AI applications that need to store embeddings in a relational database and then later retrieve them for similarity search or hybrid queries. So imagine you have an AI worker that generates embeddings for documents, products, or messages. You need a place to store those embeddings along with metadata like category, timestamp, or source. And PostgreSQL with the vector extension provides a clean and structured way to store embeddings and then later run similarity queries using SQL. Now for this demo, we're going to use Python to connect to Azure Database for PostgreSQL. We're going to enable the extension and then create a table. And we'll keep everything simple and Windows friendly. All right, so let's get started. Now I have the Azure portal open on my screen, and I've navigated directly to an Azure database for PostgreSQL. Now I've navigated here just to show that we do in fact have a PostgreSQL database already, and we've called it DemoDB. Now we used this database in our previous demo, and we're going to use it again this time, and we're going to enable what's called vector extensions. And we're going to do all that using Python. So what I'm going to do now is I'm going to flip over to VS Code. Now in VS Code, I have a script written in Python that we're going to use to walk through this demo. And don't worry, I'm going to provide this script with the demo. Now this script basically does two things. One, it enables that vector extension, and two, it creates a table with an embedding column with 4 dimensions. All right, so let's walk through what this looks like. Now at the top of the code, we have our information for how it is that we're going to connect to PostgreSQL. We have the host, the database, the username, and the password. Then on line 10, we establish the connection. We use that information, and then we pass that into psychopg2, the host, the database, the user, and the password, so that we can connect. We also require SSL mode, which means that all of the information is going to be encrypted in transit. Now if we scroll down on line 18, we effectively turn on the connection and create a command prompt or cursor. Then on line 21, we actually enable the vector extension, and we do that using a SQL command. We run create extension if not exists, and we call the extension vector. The vector is the extension. And it's idempotent, which means that if the extension is already created, then there's no need to do it again. It already exists. Then, if we scroll down, we run another command. Now, in our previous demo, we created a simple items table. And we used the simple SQL command of create table if not exists. In this demo, we're doing that again, except this time we're calling this new table embeddings. Now, the important part of it is just like the previous demo, it has an ID and it has a category, but now it has another field called embedding. And notice that the data type is vector. And this is important. It's not a text field, it's not a number field, it's a special vector field, which is only available if you have the vector extension turned on. Then it requires a number of dimensions, and in this case we've said the number of dimensions is 4. So that's good. Then we commit that, which should result in the creation of our table. Now if we scroll down, we print out to the screen that we've done the vector extension and that the table's been created. We don't really do anything more than that, and it's not super important for the purposes of this demo. All we care about in this particular case is that we have created the table. Now that being said, if you did want to insert into the table, well, we could show you what that looks like. It would be a simple insert command using the cursor. So we would type cursor.execute, and then we would provide a SQL command. Now that SQL command could be a simple insert, but it has to be an insert that works with the vectors. So that means that we need to do an insert like insert into, and then you provide the table name, which in our case is embeddings, and then which values you want to import. So we're going to say we want to import category, and we want to import embedding. Now notice I'm not adding ID. I could add ID, and in fact in this case I should, but sometimes ID being a primary key, if you have serial turned on, means that it's going to automatically create an ID for you. Now in this case, because we don't have serial turned on, we actually have to type ID because that's a variable we do need to provide. Now we would provide the actual values, and then we can provide them as simple quoted strings. So the first is the ID, and we can say the ID is 1. The second is the category, so let's just say it's demo for now. And then we provide the embedding. Now an embedding is an array of values, so we have to give square brackets inside the quotes, and then we give the values. So let's say it's something like 0.1, 0.2, 0.3, 0.4. Now at that point, we would complete the actual command, and don't forget to put the semicolon at the end. And of course, then we have to say cursor.commit. Perfect. Now we can save that, and then what we can do is execute the command. So let's go ahead and execute it and see what happens. Now to execute it, I'm going to go down to the terminal at the bottom of the screen, and I'm going to type Python space and then PostgreSQL demo.py, because that's the name of my file. And once again, I will provide it with the demo. So let's go ahead and execute it. And presto, just like that, the extension is enabled and the table has been created, and we've inserted something into the embeddings. Now everything works. So PostgreSQL supports vector search through the vector extension. Enabling that extension is a simple SQL command. Creating a table with a vector column lets you store embeddings and metadata cleanly, and this pattern is super ideal for AI workloads that need structured vector storage. So there you have it. In this demo, we enabled the vector extension in Azure Database for PostgreSQL and created a table designed to store embeddings and metadata for AI workloads. Great job! In this demo, we're going to insert some sample vector rows into Azure Database for PostgreSQL and then run a nearest neighbor query using pgvector operators so you can see exactly how Similarity search works inside PostgreSQL. This pattern is really important for AI applications that store embeddings in a relational database and need fast vector comparisons using SQL. So let's imagine that you have some embeddings generated by an AI worker and you want to retrieve the most similar items to a query embedding. Maybe that's for recommendations, semantic lookup, or a hybrid search. PostgreSQL with pgvector makes this super easy by providing the vector type and operators like less than, dash, greater than for distance. Now, this demo assumes that the vector extension is already enabled, which we did in our previous demo, and that there's an embeddings table that already exists, which we also did in our previous demo. What we're going to do in this demo is we're going to insert a few sample rows and then run a nearest neighbor query. Now, let's get started. Now, I have Visual Studio Code open in my screen already, and I will provide this file with the demo. So let's start at the top. Now at the start, on lines 4, 5, 6, and 7, we have our connection details for PostgreSQL. This includes the host, the database, the user, and a password. Then on line 10, we actually establish that connection to PostgreSQL We pass in that host, database, user, and password, but we also give it an SSL mode of require, which means that all of the data transactions that we're going to do are going to be encrypted, so we can be sure that all the data that we have will not be snoopable. All right, now we can scroll down and we get to line 21. Now on line 21, we actually perform an insert command. We are providing the actual insert command in text form, and we are inserting into the embeddings table that we created in our previous demo 3 fields. We're actually also inserting 3 rows. So each of these 3 rows will have the 3 fields. We're going to insert a value of 1 for an ID, a value of 2 for an ID, and a value of 3 for ID. So we're going to have 3 different rows. Now this is actually something that I need to change. I kind of did this on purpose. One of the things that we have to be aware of when we're performing inserts is that there may be other pieces of data in the system that already have certain IDs. Now in our previous demo, we actually inserted a demo value that has an ID of 1, which means that our first insert here would fail, and therefore the entire insert would fail. We can see that on line 27 we have on conflict do nothing. This is really important because the failure would be silent. We wouldn't insert any of the 3 values because the ID conflicts with another one. So what I'm going to do is I'm actually going to up all of the IDs by 1. So we're going to say the ID is 2, then 3, then 4. Now for the categories, we have a mix of general and AI, and then we have some embeddings. So after this, we will have 4 values in the database, our original demo value, and then 3 new rows that are our embeddings. Now with the embeddings in the database, now we're ready to do our various similarity queries. So for that, we're going to scroll down, and we can see that we have a query embedding. Now, this is important as well. Understand that when a user is making a request, that request can be itself turned into an embedding value. It becomes a numeric representation of the request, which allows us to go look for the data that we want using only the embedding values rather than the text. The embedding includes information like what it's about and the intent and all that type of stuff. So we're not actually demonstrating how to create this embedding, but it is also important that it is the same number of dimensions as the embeddings that is in the database already, and that ideally it's the same model that creates this query embedding as created the embeddings in our database. That way everything is going to match. All right, then we actually create the query to perform our similarity. We have select ID, category, and embedding. So this is a standard SQL statement of what data do I want to project. We get it from the embeddings table, and then we order by an embedding. Now notice the syntax of the less than dash greater than. This is very important. This is a Euclidean distance operator. So basically the lower distance means higher similarity, and that's what we want. Then we're going to order by that value, which means that the lowest value, which is the closest neighbor, is going to be at the top. If we wanted to use a cosine similarity, then we could change the operator from less than dash greater than to less than equals greater than. But we're going to leave it as the Euclidean for right now. Then we limit the number of results to 2. So even though there are 4 items in the database, we only want to get 2 back. Then we fetch all the data and we print it to the screen. So let's see this in action. So down at the bottom of the screen, I have the terminal open, and now what I can do is I can execute the script. And I can type Python space and then PostgreSQL-demo.py. Again, I will provide this file with the demo. So let's go ahead and execute the operation and see what happens. Perfect. So now we're seeing the nearest operators, and we're seeing item number 2 and item number 3. We don't see item number 1, which is our demo from our previous demo, and we don't see item number 4, which was one of the other embeddings that we created in this case. We are seeing the closest neighbors. Now once all of this stuff works, pgvector can be seen to support vector storage and similarity searches. The operator that we use performs nearest neighbor ranking, but we could use other operators like cosine as well. PostgreSQL can efficiently return the closest embeddings for AI workloads without having to use any of the text or any of the other fields. So there you have it. In this demo, we inserted some sample vector rows and ran a nearest neighbor query using pgvector operators to understand how PostgreSQL performs similarity searches. Great job! In this demo, we're going to review some index options for a vector-enabled PostgreSQL table and examine a simple query plan so you can understand how pgvector uses indexes to accelerate similarity searches. Now, this is an important skill for AI workloads because vector queries can become expensive without the right index strategy, and PostgreSQL gives you multiple index types to choose from depending on your performance goals. So let's say you have a table that's storing embeddings and metadata. Maybe it's product descriptions, knowledge base entries, or AI-generated summaries, and you want to ensure that the nearest neighbor queries can run efficiently. By reviewing index options and looking at a query plan, you can see whether PostgreSQL is using an index or falling back to a sequential scan. Now, this demo assumes that you already have a table named Embeddings with a vector column, and we created that earlier on in this course, so we're confident that we do. What we're going to do is we're going to create a few index variants and run an explain command to see how PostgreSQL chooses a plan. Now on my screen, I have Visual Studio Code and I have a Python script that we're going to use for the purposes of this demo. And don't worry, I'll provide this file with the demo. Now what this script is going to do is it's going to create an IVFFlat index and print the query plan for a nearest neighbor search. So let's walk through this script and what it does. Now at the very top of the script, we establish our connection to PostgreSQL just like we did in our previous few demos. We have our variables that include our host, our database, our user, and our password. And then on line 10, we establish a connection to PostgreSQL by passing in the host, database, user, and password. And as always, we have the SSL mode turned on. It is required, which ensures that all of the traffic to and from the database is encrypted in transit. Okay, now we can scroll down. And on line 21, we execute a command. Now what this command does is it creates an index, but it creates an index only if it doesn't already exist. So we're not going to just blindly create indexes over and over and over again. We're going to create one only if it doesn't exist. And we're naming it idx_embedding_IVFFlat. Now this is our name. We can name it anything that we want. But we're going to tell it how to do this index. So we're saying that we want to do it on the embeddings table, and we want to use IVFFlat, and then we pass in information about how we want that index to work. So we're going to say we want it on the embedding field inside the embeddings table, and then we're saying that we want it to be a vector L2 ops. Then we provide some additional information with lists equals 10. Now, IVFFlat is a common pgvector index type, and the list's parameter, a value of 10, controls how the index partitions vectors internally. We're not going to go into a tremendous amount of detail in terms of how that particular index works below the hood, but at the end of the day, we are creating a specific index on the embedding field in the embeddings table, specifically designed to ensure that our queries are as optimal as possible. Now we can scroll down and we get into some actual queries. So first we're creating a query embedding, which is very similar to what we did in our previous demo. We're basically saying, let's pretend this is the request from our user. They're asking for certain information, and we want to make sure that we're performing an efficient query. So how do we do that? Well, on line 31, we're actually explaining a query. So on line 33, we have some text, and it actually performs a query, or at least defines what that query would be. We're saying, select ID and category from the embeddings table, order by the embedding field, the one that is Euclidean closest to the query embedding value that we've provided, and let's limit only 2. So we're going to order by the ones that are closest, and we only want the top 2. So there might be thousands of items in our database, but we only want the 2 closest. But importantly, we say explain at the top. So rather than performing the query, What we want Postgres to do is to give us an explanation of the query. This explanation is going to tell us whether or not that query is efficient. So we want it to use our index, but it could be falling back to a sequential scan. If it uses a sequential scan, that's not great because it means that it's going to be scanning the entire table, and we don't want it to do that. We want it to scan just the items that are actually relevant to this particular query, and that's where an index comes in. So it knows where in the table to go, and it's going to give us our data a lot faster. So let's go ahead and execute this to see what happens. At the bottom of the screen, we're going to get the query plan printed out. So this is fantastic. So now I'm going to go to the terminal at the very bottom of my screen, and I'm going to type Python space and then PostgreSQL demo.py, and again, I will provide this file with the demo. If I execute that, I'm going to be able to see the information about that query. So let's go ahead and run it. Perfect. So the first thing that we know it did is to create the index. It didn't fail, so it must have created it. Then the next thing it should do is execute the explain command. And in fact, that's what we're seeing at the bottom of the screen. We're seeing the query plan, and then it's telling us what it's going to do. Now, when we read and explain, you typically read it from the bottom to the top. So let's read it at the bottom. What is this trying to tell us? Well, the sequential scan on embeddings is actually telling us something very important. It's telling us that PostgreSQL is performing a sequential scan, a full table scan on my embeddings table. Then we can scroll up and it says the sort key and the sort. Once it scans all the rows, then it sorts them. And the sort key is our embedding value, and it's that Euclidean value specifically. And then the limit is the top, which means that it's only going to take the top 2 rows. Now, what all these numbers mean is also important. The cost, the first number, 109, is the startup cost, the work done before the first row can even be returned. And the second number, 1.10, is the total estimated cost to complete the operation. These are arbitrary units used by PostgreSQL Optimizer. It's not a value in seconds or anything. You're just trying to keep the value low. Rows equal 2 means the estimated number of rows that this specific node will output, and width of 72 is the estimated average width of the rows returned in bytes. Okay, so now this query is fine because my database is tiny. It only has 4 rows. However, if the table grows to millions of rows, then that sequential scan means PostgreSQL will have to calculate that Euclidean distance for every single row, and that's why that index matters. But the reason it says it does a full sequential scan is simply because the index isn't there yet. It does take a second to actually calculate the index, and it's going to take a moment to apply. So what I'm going to do is I'm going to clear my screen. I'm going to execute the command once again just to see if it gives us a new output. Now it's still showing that it's going to perform a sequential scan, which means that the index is not yet applied. And that can happen. Like I said, it can take some time for the index to apply, and sometimes it takes time for PostgreSQL to know that it's there for the purposes of the explain. Regardless, it is there, and it means that any subsequent command is going to use that index. So pgvector supports multiple index types, and we used an IVFFlat. IVFFlat is a common choice for nearest neighbor searches. And our query plan can reveal whether PostgreSQL uses that index or a sequential scan. You want it to use the index. Index selection affects performance and scalability for AI workloads. But there you have it. In this demo, we reviewed index options for a vector-enabled PostgreSQL table, and we examined a simple query plan to understand how pgvector accelerates similarity searches. Great job! In this demo, we're going to run and review vector queries using different index configurations and compare how each one affects latency and query plan behavior. Now, this is a really good way to understand how pgvector chooses execution paths and how index selection can dramatically influence performance for AI-style similarity search. So imagine you have a table that's storing embeddings. Maybe it's product descriptions or knowledge base entries, and you want to tune your similarity search so it responds quickly. By running the same query against different index types, you can see how PostgreSQL behaves and choose the right configuration for your workload. So to keep our demo nice and simple, we're going to create a small table, we're going to insert a few sample vectors, build multiple index types, and then run identical nearest neighbor queries while observing the latency and query plans. And everything's going to be done with Python and PowerShell on Windows. All right, so let's get started. Now I have VS Code open on my screen, and I have a Python script. Don't worry, I'll provide this Python script with the demo. So let's go over what it is that this script does. Now, first of all, right at the top, we're importing the psychopg2 library. This allows us to interact with the PostgreSQL database. On lines 5, 6, 7, and 8, we are creating a few variables that is going to be used for connecting to our PostgreSQL database. And on line 11, we actually perform that connection. And we use the host, the database, the user, and the password to connect. Now, of course, this means that you do need to replace the values with your own values. But again, don't worry, I'll provide this file with the demo, and you can make that adjustment. Now, as we scroll down, on line 19, we're going to create a connection. And on line 21, we're going to start the process of running a few scripts. Now, the first thing we're going to do is create a table called Embeddings. And we're going to drop the table if it already exists. That is going to allow us to be a little bit safer as part of this demo. So we're going to drop any existing table called Embeddings, and then we're going to create a table. And that table really only has two fields in it. An ID, which has a simple integer in it, and it's going to automatically count, and a vector. And the vector is called embedding. Then on line 30, we're going to create some sample embeddings. These are our sample vectors, and you'll notice that it has a dimension of 4. And in fact, on line 25, you can see that our embedding has a dimension of 4. Then on line 37, we're going to go through a loop and insert each of those vectors as the embedding into the embeddings table. Then on line 41, what we're going to do is we're going to perform the creation of an index. And the first index we're going to create is an IVFFlat index. Then on line 48, we're going to create another index on the same table, and in fact, even on the same field, the embedding field. And this is an HNSW index. Then on line 55, we're going to create a query embedding. And then on line 57, we're defining a method called runQuery. And what we're going to do is we're going to perform a few queries based on that query embedding. And we're going to print out the results. Now, the query that we're actually going to run is an explain analyze. This means that we're not actually performing the query. We want to get an explanation of the query if we ran it. So this is an important thing to take a look at, because what we want to see is how our indexes are going to work. All right, and then on line 73, we perform the run query using the IVFFlat strategy. And on line 74, we're going to run that same query, but using the HNSW index. Then we're going to close out our connection, and we're all done. All right, so let's go ahead and execute this query and see what's going to happen. Now, just so we understand the indexes and what they mean, the IVFFlat index partitions vectors into lists, which speeds up approximate nearest neighbor searches. HNSW builds a hierarchical graph structure, which can provide faster recall for lots of different workloads. We should also pay attention to the operator that we're using, which is the less than dash greater than. And what that specific operator does is it's computing a Euclidean distance. But notice that we're going to perform these queries the same way every single time. So what we're going to be looking for is we're going to be looking to see if the queries are going to give us an index scan or a sequential scan. A sequential scan means it's not using an index. All right, so let's go ahead and run the query. Now to do that, I have the terminal down at the bottom of the screen, which I'm going to expand so we can see more details. I'm going to type Python and then the name of the file, which is PostgreSQL-demo. Let's go ahead and run that, and then we can take a look at the output. All right, so we're going to scroll up at the results. Now the first thing that we're going to see is the IVFFlat index, and it's telling us how it's working. Okay, now PostgreSQL query plans are read from the bottom up and inside out. So let's see what this means. So starting at the bottom, what we're seeing is a sequential scan on embeddings. So PostgreSQL is scanning the entire table sequentially, and you might wonder, why isn't it using an index scan? Well, the main reason here is simply because the amount of data that's in the database is only 4 rows. So the result is that it doesn't feel like it needs to use an index scan because there isn't enough data to really warrant it. However, if I had thousands and thousands and thousands of records in the database, it absolutely would be using an index scan because we've created that index. So we would see, instead of sequential scan, we would see index scan on embeddings. The next thing we see is the sort that was performed, which is the order by embeddings. And then we see finally the limit, which is to say that we're only going to take 2 items. So we are seeing how the query is working, and we're seeing what that means in terms of performance, and we're seeing which index might be better in certain situations. We can scroll down and see the HNSW index, which is doing the same sequential scan instead of index, but again, that's simply because of the number of records in the database. It does the same sorting, it does the same limit, and then down at the bottom we can see how much time it's taking for planning and execution, and of course it's taking substantially less time. Now, it is important to understand that doesn't mean that HNSW is always faster than IVFFlat. You have to understand your specific data, how much data is in the database, and the type of queries that you're performing. Then, based on the performance and the planning and your own requirements, you would choose whichever index works best for you. So, there you have it. In this demo, we ran vector queries using different index configurations and compared their latency and query plan behavior to understand how pgvector chooses execution paths. Great job! In this demo, we're going to add metadata filters to a vector query and explain how the result set and query path change when PostgreSQL combines semantic similarity with structured filtering. This is an important skill because real-world retrieval almost always involves both embeddings and metadata, things like category, author, region, or permission labels. By seeing how filters affect the query plan, you're going to understand how pgvector decides whether to use an index, perform a sequential scan, or prune the search space before computing distances. So imagine you have a table of product embeddings, and you only want results from a specific category. Well, without metadata filters, the query might return items that are semantically close, but irrelevant to the user's intent. Adding filters helps to ensure that the result set is both meaningful and constrained to the correct subset of data. So for this demo, we're going to create a small table with embeddings and metadata, build an index, and then run 2 queries, one without filters and one with filters. And we'll compare the result set and the query plans to see how PostgreSQL behaves. All right, so let's get started. Now I have Visual Studio Code open on my screen, and I have a demo Python file. And don't worry, I'll provide this file with the demo. Now let's take a look at what it does. Now right away at the top of the file, we define a few variables that allows us to connect with our PostgreSQL database. And in fact, on line 11, we are performing that connection. To perform the connection, we pass in the host, the database, the user, and the password. So of course, you'll have to change those variables to match your specific variables. Now, if I scroll down on line 21, we create a cursor which actually uses that connection so that we can run commands against PostgreSQL. That brings us to line 21. On line 21, we're creating a table that we're going to use for this demo. We call this table items. If the table already exists, we're going to drop it and then create it again so that we can be sure that it matches our needs for this demo. The table has 3 specific fields. One is called an ID, which is a simple numeric and automatically incrementing value. Next is category, which is a simple text field. And then we have our embedding. Now you'll recall in our previous demo that we had a simple embeddings table that had an ID and embedding. It only had the embeddings. So in this case, we're adding a category field, which is going to act as our metadata. Then we can scroll down and we get to line 31 and we're defining some information. This is going to be the content of our new table. So we're going to say that we have a category of books and another category of electronics, and we're creating 4 rows two using one category and two using the other category, and then we have some simple four-dimensional embeddings that we're going to attach to each of those rows. And on line 38, we use a simple for loop to insert those values into the database. So now that we have a table in the database and we've populated that database, now we can perform our actual demo and start working on how this is going to work. All right, so that actually brings us to some indexing. So the first thing we're going to do is on line 43, we're going to create an index. And it's a simple IVFFlat index, and we're applying it to our items table and also the embedding field. Then on line 49, we're going to create a query embedding. This is going to act as the user's request. So it doesn't really matter what all these numbers mean. We're just using it as a similarity query. And then what we do is on line 52, we're going to run a query to explain a query. So we're going to pretend that we want to perform a very, very simple query without any metadata filters. We're simply saying select everything from that items table, or at least just the ID and the category, where the embedding is Euclideanly close to the query that we're providing it, and only give us the two items. So what we're doing here with that where, I called it a where, but it's really an order by, but it is important to understand the usage of the query embedding, is we're saying get all of the items, order them by that closest embedding value, and then only get the top two. So it's sort of like a where. You're basically saying get me the two closest. Then we're going to output that to the screen so we can see what the analysis looks like. But then we're going to perform the same query again, and this time we're going to do it with a metadata filter. And specifically, we're going to say, let's find the ones where we have the category equaling books. And this time we actually are using a real where clause. So everything about the query is exactly the same, except this time we're going to say, but filter the results to only the ones that are using the books category. We're still going to analyze, and we're still going to see the values output to the screen. Then we're going to be all done, and we're going to close the connection. So let's go ahead and run this query and see what we get. So to run the query, all we have to do is type the command Python and then the name of our file. And once again, don't worry, I'll provide this file with the demo. So let's go ahead and execute the command. And then what I'm going to do is I'm going to expand the terminal section so we can see a little bit more of what happened. So once again, we're going to see the query without metadata and then the query with metadata filter. So the first query that we see is performing a sequential scan, which makes sense because we have very few rows in the database, so it's not needing to use the index, but you can imagine that if we had thousands of rows, it would use the index. Then it sorts the results, which we expect, and then it limits to 2 rows. So we can see that it's going to take about 0.23 milliseconds, and that's the time for the plan, and the actual execution is 0.06 milliseconds. We can see that the buffer used a shared hit of 43, and we don't really need to worry about some of these numbers that we see in terms of cost because these are sort of arbitrary numbers that are created by PostgreSQL. What you're looking for is lower numbers, and you're looking at comparisons. Now we can look at the query with metadata filters. So once again, it's doing the same thing, a sequential scan, but this time we can see that it's removing 2 rows from the buffer. Now this is extremely important. It's saying of all the data that I'm going to look at, well, I'm not going to be looking at these 2 rows, which makes sense because we're saying only get us the ones that have books, and we know from our code that there are 2 rows that are not books, so it's removing those 2. Then we do the same sort, and then we do the same limit. Now we can scroll down and we can see that the planning time takes a little bit less, and we can say the execution time takes a little bit less, and we can see that the number of buffers that were hit is also quite a bit less. So in that sense, we know right away that anything that includes a where clause, especially on metadata, is going to take less time, and even less time if we were to index that field as well. But there you have it. In this demo, we added metadata filters to a vector query and explored how they change both the result set and the query path inside PostgreSQL. Great job! In this demo, we're going to review pgbouncer configuration and explain how applications connect through the pooler to stabilize database workloads. Now, pgbouncer is one of the simplest and most effective tools for managing connection pressure, especially when applications create short-lived connections or when AI fan-out patterns generate bursts of traffic. So, understanding how pgbouncer is configured and how clients connect through it helps to ensure predictable performance and safe database operations. So imagine an application that opens many connections during peak usage. Without a pooler, the database might hit connection limits, causing slowdowns or failures. pgbouncer sits between the application and the database, reusing server connections and smoothing out bursts. So by reviewing its configuration, you'll be able to confirm how pooling works and how applications should connect to it. All right, so let's get started. Now I have Visual Studio Code open in my browser. And so what I want to do in this demo is I want to review a pgbouncer.ini file. This is the configuration for pgbouncer that would be running on your system, whether it's a virtual machine, whether it's an app service in Azure, whatever it is, wherever it's running, you would need configuration, and that's what we're going to review. Now, the other thing that we also need to take a look at is an actual connection to PostgreSQL. Now, in our previous demo, we had a Python script file, which I've kept for the purposes of this demo. And I have it as a different tab. Now, what we have been doing in terms of our demos in this course is we've been using a connection to PostgreSQL. So we can see that on line 11, we've been using a psychopg connect. We pass in the host, the database, the user, and the password. And the host is actually our PostgreSQL server name. So you can see that it's sbdemo psql.postgresdatabaseazure.com. Now, that's great. But what we want to do is we actually want to use a pooler, and that's where pgbouncer comes in. So now we can imagine that we've installed pgbouncer on whatever system this script is running on. Again, that's a virtual machine or an Azure App Service or whatever it might be. Now, what we would need to do is we'd need to configure pgbouncer. So now if we go back over to the ini file, the first thing that we define in the ini file is the actual connection to PostgreSQL. So you'll notice that we have a demo DB, which is our database. So that's going to match our database name that we had in the Python file. So our database name was demo DB on line 6. Then we define the host, which is the sbdemo psql postgresdatabaseazure.com. Then we, of course, establish a port, which is a standard PostgreSQL port, the username, and the password. So this is effectively the exact same connection details that we were using in our Python script, and that's on purpose. Then we can define some information about how pgbouncer is going to work. So what we have is a listen address and a listen port. Now the listen address, you'll notice, is 0.0.0.0. Now that basically tells pgbouncer to accept connections from any network interface. The port 6432 is the port that applications will connect to instead of 5432. That'll come in a moment. We'll talk about that. The authentication type of MD5 means that pgbouncer validates client credentials using MD5 hashes. Then we have a user list text file, which tells pgbouncer where to find those credentials, and we're going to ignore that for the purposes of this demo. Our pool mode is transaction, and this is the most common mode for high concurrency workloads. Basically, transaction pooling assigns a server connection only for the duration of a single transaction. And this mode increases concurrency, but it doesn't support session-level features like temporary tables if you needed to create some. Then we can start setting some of our limits. So the max client connection of 200 limits how many client connections pgbouncer is going to accept overall. Our default pool size defines how many server connections pgbouncer can maintain for the database. So we're setting that as 20. And this number is usually much smaller than the number of clients, which is the whole point of pooling. Then we have our reserve pool size, which provides extra server connections during bursts. And then we have log connections and log disconnections, which helps to track client behavior. All right, so great. So this is now configuring PG Bouncer. It's going to work a certain way. It accepts all of the connections from everywhere using that 0.0.0.0 syntax. All right, so now how would that impact my Python script? So for that, we would need to go back to Python. And this time, the host would no longer be this sbdemo PSQL Postgres database.azure.com. It would actually be a configuration to PG Bouncer instead. So when you install PG Bouncer, it's going to give you a host name to use. And you would use that specific host name. So we would now change the host to the PG Bouncer host, whatever that might be. The database would remain the same because that's how it's going to tie to the INI file. The username would stay the same and the password would stay the same. But now the other thing we'd need to do is we need to define a port. And that port would now have to equal 6432 instead of the 5432. And then when we're establishing our connection, we would have to provide that port as well. Now, this is the one major change. We have to provide the new host, which is to PG Bouncer, and we'd have to define the new port of 6432 instead of 5432. At that point, all the rest of the code works exactly the same way, except instead of establishing a connection directly to PostgreSQL, we're now establishing a connection through PG Bouncer, and PG Bouncer is going to create pools of connections so that you can reuse an existing connection and benefit from that, which includes things like performance benefits and so on. So there you have it. In this demo, we reviewed PG Bouncer configuration details and explained how applications can connect through the pooler to stabilize database workloads. Great job! In this demo, we're going to inspect Azure Database for PostgreSQL metrics that indicate connection pressure, CPU pressure, memory pressure, and storage pressure. These metrics are super important for understanding how your server behaves under load and for spotting early signs of bottlenecks before they impact your applications. By reviewing signals like this in Azure Monitor, you can quickly determine whether your workload is healthy or if you need to scale, tune, or adjust connection behavior. So imagine you have an application that's suddenly slowing down. You're not sure whether the issue is too many connections or high CPU usage, memory saturation, or storage latency. By inspecting the built-in metrics, you can pinpoint the exact resource under stress and then take corrective action. All right, so let's get started. Now I have the Azure portal open on my screen, and specifically I've navigated to an Azure database for PostgreSQL that we created for use in our demos. Now what we want to do is we want to inspect some metrics. So in the left-hand menu, what we want to do is expand the monitoring section and then click on the metrics option. Now this is going to open up the metrics workspace where we can inspect performance signals. Now at the top, we need to make sure that the metric namespace is set for Azure Database for PostgreSQL. And so what we can do is expand the metric namespace section and just make sure that we have the PostgreSQL option selected. Now for the metric, we can expand that metric pull down and we can see all kinds of different metrics that exist in the system. And we can scroll through and just take a look at everything that exists. Now what we want to do, of course, is we want to select the connections. So without scrolling through absolutely everything, what we can do is we can either type for active connections, or if we find it under traffic, we can simply select active connections. Then we're going to see a graph, and that graph is going to tell us how many connections have been happening on a relatively consistent basis. We can change the time frame at the top of the screen so that we can see it over a longer time frame. So let's say we want to look at the last 7 days and then click Apply. Then we can see the chart. Now generally what we want to see is a nice and flat chart. If you have sudden spikes, that might indicate application fanout or some inefficient connection handling. And if active connections start to approach a server's limit, then connection failures or throttling might start to happen. Now in our case, we have a nice and flat level, and if that happens to be near our threshold, that would be bad, but in our case, It's a very low number, which makes sense because it's a demo system. But the next thing we want to look at is CPU pressure. So what we would do is change the filter, and instead of selecting active connections, we're going to look for a different metric. We're going to look for CPU percent. So I'm going to select CPU percent as the metric. We're still using the last 7 days, and we're now taking a look at the chart. Now in this case, the chart is hovering around 7%, give or take. So what we want to do is we want to make sure that CPU is nice and flat, and just like our active connections, doesn't have any unusual spikes. CPU usage often comes from heavy queries, parallel workers, or large sorts. And sustained CPU pressure that's really close to 100% might require query tuning or scaling to a higher compute tier. Now in our case, once again, our CPU percentage is pretty low and pretty normal, which once again is pretty normal for a demo system. Now the next thing we want to look at is memory pressure. So this time we'll change the metric from CPU percent to memory percent. So we'll go ahead and select that. And now once again, we'll take a look, and once again, we're seeing a nice and flat line. So we're seeing how much of the available memory is being consumed. In our case, it's around 35%, give or take. High memory usage can come from caching or large hash joins, or insufficient memory for workloads. Memory pressure can cause query plan changes or slower performance if PostgreSQL spills to disk. Now speaking of disk, we can actually take a look at that too. So now we can take a look at storage pressure. So once again, we can change the metric from CPU percent or memory percent to storage percent. And this will show us how much of our storage is being used at the moment. So when you're approaching 100% storage, usage can cause failures or prevent new writes. We can also select IOPS to understand read-write intensity. So instead of a storage percent, we can look for IOPS. And if we select that, we can see how many IOPS we have in the system, and that might indicate heavy query activity or index scans. Another thing we can do with storage is we can look for storage latency. Now, storage latency is a little bit tricky to actually query for. So let me just talk about storage latency because it's sort of a mixture of the reading and the writing and all of that. It also has to do with how the workload might be exceeding the storage tier's performance envelope. So if you're doing long reads and long writes, that might mean that there is a problem with the actual storage type that you have, and you might need to expand or improve upon the tier of your storage. Now that doesn't happen very often, and it kind of depends on the types of queries you have and the type of data that you have. If you have good memory and if you have good CPU, your storage ends up not being a real key to your typical query patterns. Now once you have all of this information, then you can make adjustments. You can decide what this data means and what you can do about it. CPU spikes that align with connection spikes can tell you that there's something wrong with your connection strategies. Memory pressure typically aligns with slow queries. Storage latency, like we said, aligns with large scans or heavy writes. And all this correlation can help to identify root causes rather than symptoms. The other thing that you can do is once you have all of these metrics understood and you can see them on charts, is you can create alerts. With these alerts, you can be notified as your CPU, memory, or storage start to get close to thresholds. So you can be told before your CPU pins at 100%. You can be told if your memory starts to get higher and higher, and then you can take corrective actions before they become real problems. So there you have it. In this demo, we inspected Azure Database for PostgreSQL metrics that indicate things like connection, CPU, memory, or storage pressure, and then learned how to interpret each signal to understand workload behavior. Great job! In this demo, we're going to connect to Azure Managed Redis and store, retrieve, and update sample cached values. Now, Redis is a high-performance, in-memory key value store that's perfect for caching frequently accessed data, reducing database load, and improving application responsiveness. By walking through some of the basic operations, you'll see exactly how applications interact with Redis and how simple it is to use cached values to accelerate workloads. So, a simple use case for this demo is when an application repeatedly queries the same data, like user profiles, product details, or session information. And instead of hitting the database every single time, the application can store the value in Redis and retrieve it instantly. Updating the cached value keeps the data fresh without sacrificing performance. Alright, so let's get started. Now I have Visual Studio Code open on my screen, and I have a simple Python script that we're going to use for this demo. And don't worry, I'll provide this script with the demo. Now behind the scenes, I also have an Azure Managed Redis that has been implemented. So on lines 4, 5, and 6 of my code, I provide the host, the password, which is an access key, and the port to use when talking to that Azure Managed Redis. Then on line 9, we establish a connection to that Redis instance, and we make sure that we have the SSL turned on. So we pass in the host, the port, and the password, and then we can establish the connection. Now after that, we can start performing our various operations with Redis. So as I said before, that means to store and retrieve and update some cached values. So let's scroll through the code and see what it is that we're doing here. Now on lines 16 and 17, what we're doing is we're actually storing a value in Redis. So you can see that we call r.set. Now if I scroll back up to where we're establishing a connection, you'll see that we have a variable named r that is the connection to Redis. So every time we say r dot, we're actually talking with Redis. So we're saying r.set, which is a method on that Redis connection, and we're going to set a value, which means that we're going to upload a key. So what we're doing is we're providing a key name. So in this case, it's demo:_key. So this is going to be a unique key. Then we're providing a value, which is hello Redis. So the demo key has a value of hello Redis. Great. So now we've uploaded something to our Azure Redis. Then on line 19, 20, and 21, we retrieve the value. So this all mainly happens on line 20. So on line 20, we say value equals r.get. So value is a new variable that we're creating, and r.get is redis.get. So we're going to retrieve a value from Redis, and we need to pass in the key. So once again, it's demo:_key. So we're going to say, now that we've written a value to demo key, now I want to retrieve the value demo key. And then on line 21, we're going to output that value to the screen. Now notice that we're calling .decode. Now that's because the value that we're getting back from Redis has been encrypted because we turned on SSL. So we're going to use the .decode to make sure that we get it back in a human readable format. The next thing that we're going to do is we're going to update the value. So on line 23 and 24, we perform that update. So on line 24, we say r.set, and we pass in the key, and we provide a value. Now notice the key difference here. On line 17, we said r.set, and on line 24, we also say r.set. So what does this mean? It means there is no difference. So what happens is every time we call r.set, we're going to be setting a specific key to a specific value. So whether the key exists or not is completely irrelevant to your code. You're going to set the value either way. So if the key doesn't exist, like it didn't when we had line 17 called the first time, it's going to create that key and apply the value of hello Redis. Then by the time we hit line 24 where the key does exist, it's going to set its value to a new value of updated Redis value. So that means that we're going to always have a value set to that key, whether that key existed or not. So we don't really care whether we're adding or updating. We're just setting. So now that we've set it, well, we can get it again just to prove that it in fact did update. So on line 26, 27, and 28, we perform another command to go and get the key. And once again, we're going to get the updated value. And once again, we're calling .decode. So we're going to be able to see the decoded value. Now, there are, of course, other commands that you can perform with Redis, but we're focused primarily on storing, retrieving, and updating our cached values. So now that we have this value, let's go ahead and actually execute this script. So down at the bottom of the screen, we have the terminal in VS Code. So I'm going to expand that a little bit. And to run this command, we're going to type Python space and then the file name, which is Redis demo in this case. And once again, don't worry, I'm going to provide this file with the demo. So now we can go ahead and execute the command, and then we can look at the output. So we can see it's storing a value, then it's retrieving the value, and then it displays the value, which is hello Redis, which is exactly what we expect. Then it's going to update the value again and retrieve the updated value, and the updated value is updated Redis value, which is again exactly what we expect. So this workflow is the simplest and most common pattern. Redis is often used for session storage, feature flags, and AI retrieval acceleration. Very simple key value pairs, and it means that it's very, very fast to go get data, and you don't have to go all the way to a SQL database, let's say, and actually perform more expensive queries. So there you have it. In this demo, we connected to Azure Managed Redis and stored, retrieved, and updated some sample cached values to demonstrate how applications use Redis for fast, in-memory caching. Great job! In this demo, we're going to set expiration on cached values and invalidate some selected keys to demonstrate freshness control in Azure Managed Redis. Expiration and invalidation are two of the most important caching techniques because they make sure that applications don't serve stale data. So by walking through both patterns, you're going to see exactly how Redis manages time-based freshness and how applications can explicitly remove outdated entries when business rules change. So imagine an application that's caching some product details. The product information might change from time to time, so you want Redis to automatically expire old values. But sometimes a product is updated immediately, like maybe its price changes, and you need to invalidate the cached value right away. So this demo is going to show you both approaches. All right, so let's get started. Now I have Visual Studio Code open on my screen, and I have a simple Python file that's going to interact with my Redis system. And don't worry, I'll provide this file with the demo. Now at the top of the file, we're establishing a connection to Redis. So we have our host, our password, and our port. The password in this particular case is a simple access key. Then on line 9, we establish our actual connection to Redis, and we pass in the host, port, and password. And then we make sure that we're putting the entire connection into a variable that we call R. So anytime we want to interact with Redis for the rest of this demo, we're going to use the R variable. All right, so let's get started with what we're actually doing with this demo. So what we're going to do is we're going to scroll down and we're going to get to line 16 and 17. Now in this particular case, what we want to do is we want to create a value in Redis that is going to expire. So what we have is r.set, so that's our Redis connection, and .set, which is the same thing that we did in our previous demo. So we can give it a key and a value. So in this case, we're giving a key of demo:expiring and a value of this value will expire. Doesn't really matter what's in it. All we're saying is that there is going to be a key in Redis called demo:expiring with some kind of value. Then you'll notice that there is a third variable. And that parameter that we're passing into r.set is x equals 5. And that means that we're setting an expiry. Now, the x equals 5 means that the key is going to expire after 5 seconds. So how do we know that's actually going to work? Well, fortunately, our demo is helping us out in this case. What we're going to do is on line 19 and 20, we're actually going to go and retrieve that value. Now we're going to set the value in Redis and then immediately read it again. So what we're doing is on line 19 saying we're going to retrieve the value immediately. And then on line 20, we're going to use an r.get and we're going to pass in that key and we're going to use .decode because we have an SSL encoded value. So we need to decode it so that we can read it. And then we're going to print the value. So what we should see is this value will expire. So we're going to write the value and then we're going to read the value right away. It hasn't expired yet, so we should absolutely be able to see the value. Now we know that it's going to expire in 5 seconds. So the next thing that we're going to do is on line 22 and 23 is we're going to wait. So we're going to actually wait for 6 seconds. Now once we wait that period of time, it's going to pause as we're on the console. after we've waited that period of time, well, then that key should expire. Now notice that time is underlined, and that's because we don't yet have the actual import for that. So what we'll need to do is at the top of the screen, where we have our import of Redis, you need to make sure that you import time as well. And then that way we'll be able to actually perform that sleep. Okay, so then after that 6 seconds, we know that that key value should have expired. So we're going to scroll down, and on line 26, 27, and 28, we're going to go and try to retrieve that value again. So this time we're saying r.get, and we're passing in the same key. If it truly has expired, then what we should see is nothing. So we're going to see what we get after waiting the 6 seconds and seeing that that key has expired. Now that's automatic expiry. It's called a time to live, or TTL. What we want to do now is we want to imagine a scenario like the product price has changed, where we want to invalidate the cache immediately. We don't want to wait for an expiry. We want it to expire right now. So what we're going to do is we're going to create another value. This time we're going to have r.set, and we're going to pass demo:"invalidate, and we're going to pass in some old value just for the sake of this demo. We're going to retrieve the value just to show that it is in fact in Redis. And then we're going to expire it or invalidate it immediately. And to do that, we can simply call r.delete, which basically means remove it from Redis. So rather than expiring it or doing some other fancy thing with it, we can simply remove it from Redis, which means that anybody that's going to try to go get the value for it isn't going to be able to get a value. And we'll prove that on line 40, where we're going to try to retrieve the data that we just deleted. All right, so let's see all this in action. So I'm going to expand the terminal at the bottom of the screen, and I'm going to type Python, and then the name of the file. And again, don't worry, I'll provide this file with the demo. So let's go ahead and execute the command. Now remember, there should be a 6-second wait that happens. So we see setting a value, and we actually have been able to retrieve the value. We're waiting the 6 seconds, then we're trying to retrieve the value again, and this time we get none. There is no value in the system. Then we set a value for invalidation. We retrieve that value, which was called old value, if you recall. Then we invalidate the key, which basically just means removing it. Then we try to retrieve the key after that removal, and once again, it says none. We didn't have to wait, it's just immediately gone. So there you have it. In this demo, we set expiration on cached values and invalidated selected keys to demonstrate how Redis manages freshness through both automatic and manual control. Great job! In this demo, we're going to review key expiration, eviction, and deletion signals for a controlled missing key scenario in Azure Managed Redis. So this will help you understand why a key disappears, whether it expired naturally, was evicted due to memory pressure, or was explicitly deleted by an application. By walking through each signal, you can learn how Redis reports these events and how to interpret them when debugging cache behavior. So imagine an application unexpectedly receives a missing key. You need to determine whether the key expired because its TTL ran out, or was evicted because Redis needed more memory, or was deleted intentionally. So this demo is going to show how to reproduce each condition and observe the signals that Redis provides. All right, so let's get started. Now on my screen, I have Visual Studio Code, and I'm taking a look at a simple Python script. And don't worry, I'll provide that script with the demo. Now at the top of the code, we're once again establishing a connection to Redis. We provide the host, the password, and the port. And importantly, the password is the access key that Azure Managed Redis creates. On line 10, we establish the actual connection, and we put the connection into a variable named R. So anything that we do with Redis from now on is going to be using the R variable. All right, now let's scroll down. Now what we have is we're going to be creating a few variables. So we have on line 18, on line 21, and on line 24, 3 set actions. Now the first set action on line 18 creates a simple key, and that key is demo:"expire. Its value doesn't matter, but it does say expires soon, and then we pass in a parameter for an expiry. That expiry is 3 seconds. So we're creating a key in Redis, and we're saying 3 seconds from now, it's going to expire. On line 21, we create another simple key value pair, and its actual key is demo::evict. It doesn't have an expiry. It's just a key that we're going to use for the purposes of this demo. And likewise, on line 24, we're creating another simple key value pair, again with no expiry, and it has a key of demo::delete. Then on lines 27, 28, and 29, what we're going to do is read back those 3 values. So expire, evict, and delete will all be printed to the screen. And because it's happening virtually immediately, we do expect the demo expire even though it has an expiry of 3 seconds to still exist. And so what we expect is for that value to appear on the screen. Then on line 32, we perform a simple sleep command. So on line 18, we know that we're expiring within 3 seconds. We've already established that. So on line 32, we're going to sleep for 4 seconds, which means that after that period of sleeping, we know that our expiry should have actually happened, and so that key shouldn't exist anymore. So on line 35, we're going to print that out. We're going to print r.get demo::expired. So now that it has expired, we actually expect to see a value of none. There is no value there. Effectively, we're getting back null. Then we're actually going to perform some other commands. So we're going to delete our demo::delete key. Now this is different from an eviction. It's an actual deletion. So we're going to delete the value and then immediately attempt to read it again. Now importantly, that means that when we delete from cache, what we expect to happen is that it's gone from cache. It doesn't linger. It means that I immediately am unable to get it again. So what we would expect is on line 39, after having deleted the key, we want to actually be able to get back a null value, meaning that we don't get any value at all. So this should say none. Now what we want to do is simulate an eviction. So what we're going to do is we're going to just dump a whole bunch of temporary keys into our Redis cache. So this is obviously not an ideal way to do things, but we're going to create 50,000 temporary keys. And ideally what this is going to happen is it's going to push the memory of Azure Redis beyond what it can have. And so what it's going to do is evict some of the keys that we have now. So our eviction key, demo::evict, should get pushed out due to memory pressure. And so if we try to do a get on it, then we should get none. And that's exactly what we want to see on the screen. Now, this does obviously matter in terms of what Azure itself can handle. Perhaps it can handle 50,000 keys. So we'll be able to see whether or not the actual eviction really happens. But let's go ahead and run this anyways and see what we get. So what I'm going to do is expand the terminal down at the bottom of the screen. And then I'm going to run Python and then, of course, the file. And once again, don't worry, I will provide the file with the demo. So once again, just to recap, what we expect to see is the creation of 3 keys. We'll see those 3 keys on the screen. Then we want to wait 4 seconds for one of those keys to expire. We'll try to read that key and we should get none. Then we want to delete a key and then read it right away, and what we should get is none. Then we want to throw a whole bunch of keys into Azure, and what we should hopefully get is a memory pressure situation, which is going to push out our last key. So let's go ahead and execute and see what happens. So we're setting the 3 keys, we're retrieving the values, and in fact we got them. So now we can see that it's filling memory. So while it's doing that, we can see all the things that have happened. So we saw the expire, expiring soon. We saw the evict, eviction candidate. We saw the delete, to be deleted. So those 3 keys were created. We waited 4 seconds. Then we checked the expired key, and sure enough, we got none, which is what we expected. Then we deleted the delete key, and then we checked its value after deletion, and we got none, which is exactly what we expected. So now we're in the process of simulating eviction by filling the memory with those 50,000 keys. So now obviously this is going to be a slow process because we're just creating so many keys. And like I said, this isn't a standard scenario. It's not something that would happen on a typical basis, certainly not in a sequential manner like we're doing here. But you can imagine that you have many different clients that are all connecting all at the same time, and they're all creating their own cache for their specific situations. And if you had 50,000 users and you're caching their profiles, for example, then you would be creating 50,000 keys, and that would potentially cause some memory pressure, like what we're simulating here. So instead, what we're doing in this case is we're saying that one application is creating all 50,000 keys, so it's all happening sequentially versus asynchronously, which is what would happen with 50,000 users. So let's give it a second to complete. Now, if the process does start taking a long time, you can sit and wait for it to complete. But there is another way that we can determine whether or not it's working before it's even completed running. What we can do is we can actually navigate to the Azure Managed Redis in Azure Portal. So what I'm going to do is I'm going to flip over to the Azure Portal, and I'm going to actually connect directly to my Azure Managed Redis. Now what I've done is I've navigated to the metrics section, and then we can look at the metric for evicted keys. Now while this won't tell us specifically which key has been evicted, we can see that keys are starting to become evicted. And as that count increases, it's going to show us that there might be something up. Now, if we correlate that with memory pressures, then we can start to see that as a result of memory pressure, keys are starting to become evicted. And if we go back to our code, what we would expect to see after our key becomes evicted is that when we try to access it, we're going to get that same none that we did with a regular expiry or a simple deleted. So there you have it. In this demo, we reviewed key expiration, eviction, and deletion signals for a controlled missing key scenario and learned how each condition leads to missing cached values. Great job! In this demo, we're going to look at how to create a Redis vector index for embeddings and metadata so you can see how Redis stores vectors, how RediSearch indexes them, and how applications can run similarity queries with filters. This is a really powerful pattern for retrieval augmented generation, or RAG, and semantic search because Redis keeps vectors and metadata close together, enabling fast lookups with low latency. So a good use case for this demo is when an application stores embeddings for documents or product descriptions and needs to retrieve the closest matches based on a query vector. Adding metadata like category or tenant helps filter results so the application only receives relevant items. By reviewing the index, you can understand how Redis organizes this data and how vector search works. All right, so let's get started. Now I have Visual Studio Code open on my screen, and we're taking a look at a simple Python file. And don't worry, I'll provide this Python with the demo. All right, now the first thing that we want to do is establish a connection to Redis. So on lines 6, 7, and 8, I provide the host, which is the Azure Managed Redis host name. Then we provide the password, which is an access key in this case, and then the port. And Azure is going to provide all that information for you right on the overview screen. Now the next thing that we do is on line 11, we're establishing a connection to Redis. There's a couple of different ways that you can do that, whether that's the Redis cluster or strict Redis. So what I'm doing is I'm establishing a connection to the Redis cluster. I pass in the host, the port, and the password, and then a couple of other parameters. Then we can actually start getting to work. So now that we have a connection to Redis, which is going to be using the R variable, which means that anytime I say R dot for the rest of the code, it means that we're talking with Redis. So let's go ahead and establish some commands. Now the first thing that we want to do is create what's called a vector index. So for that, we're going to call redis.execute command, and we're going to provide some information. So like I said, this is creating a RediSearch index, and its name is going to be idx_docs. And it uses on hash, which means that each document is stored as a Redis hash. Then we pass prefix 1 doc, and then we have a semicolon on that, and that tells RediSearch to index keys that start with doc:. Then we can actually provide some schema details. So we provide category tag and embedding vector. Category tag stores metadata for filtering, and embedding vector flat defines a vector field that's used for flat index type. We also provide some other information like type float and dim4, which needs to match the embedding format, meaning that the vector contains floats and it has 4 dimensions. And then we have distance metric of L2, which means that Redis will compute Euclidean distances when it's creating this cache. Then as we scroll down, we can see that we're going to create some sample documents in Redis. So basically we're creating some 4 simple sample documents. And it is important to note that embeddings need to be stored as raw bytes, which is why NumPy converts them to that. So we can see that down on line 43, 44, and 45. Then we actually get into the actual querying. So we create a query vector. This is pretending to be a user. This is the query that the user has provided, turned into a query vector. Then on line 51, we execute another command, which is a vector search. So we're using our index, and we're performing the search based on the query vector, and we're using the KNN clause to find the closest matches. So the script runs a search for the 2 nearest neighbors, and we can see that by using a return to and a sort by the embedding score. So that means that it's sorting by the similarity distance. In fact, ReadySearch automatically computes the distance metric. Also, metadata filters can be added for things like the category being equal to books and things like that. In fact, combining metadata and vectors often keeps retrieval relevant and a little bit faster. Flat index is simple and works well for small to medium datasets, and HNSW indexing is also available but typically used for larger workloads. So Redis vector search is fast because everything runs in memory. So it's a little bit better than database style searches where you're actually performing all of this in the database. Now we can actually search within Redis where everything is done in memory, so it should be a lot faster. Then at the end, we can actually print out the results. Now, in order to run this command, you're going to need to have a very specific implementation of Redis in Azure. It means you have to have ReadySearch enabled, you have to have a certain tier turned on, and once you do have those things turned on, you'll be able to execute these commands. The important part is ft-search, and if we scroll back up, there's the other command for the ft-create. These are specific actual methods that are contained within Azure's Redis. So if you don't have certain things installed, which you would require certain tiers to be able to install, then these commands won't work. So we have to talk about what would be capable with having these tiers available. So once you have that tier available and you're able to execute these commands, it's going to work very, very simply. It's going to create an index, and it's going to be a flat vector index. And if we scroll back down, we're going to perform a ft search, which is going to use that index and the KNN, just like we talked about before. And this will perform simple vector searches using the distance metric, and Redis takes care of all of that for you in memory, a heck of a lot faster than doing it directly in a database. So there you have it. In this demo, we took a look at how Redis vector index can be applied for embeddings and metadata to understand how features like ReadySearch can organize vectors and support similarity queries. Great job! In this demo, we're going to talk about how to run vector similarity queries and inspect nearest neighbor results with metadata, so you can see how Redis returns both semantic matches and contextual fields together. Now, this pattern is essential for retrieval augmented generation, or RAG, product search, and any workload where embeddings alone just aren't enough. You might also need metadata to understand what each match represents. So imagine a scenario where you have an application that stores embeddings for documents, and you want to retrieve the closest matches along with their categories or tags. Well, without metadata, the application wouldn't know how to interpret the results. So by running a vector query and inspecting the returned fields, you can see how Redis combines similarity scoring with structured information. So for this demo, we're going to take a look at a Python script and how it would connect to an Azure Managed Redis, how you could insert some sample embeddings and some metadata, how to create a Redis search index, and then how to run a nearest neighbor query. Now, in order to be able to run some of these things, you'll need a specific tier of Azure and a specific tier of Azure Managed Redis, which is not something that I have installed, but we can still walk through the process and how it works. Because at the end of the day, all that really matters is how your queries are structured and the indexes that you create, not necessarily the running results. All right, so let's get started. Now on my screen, I have Visual Studio Code. And in that Visual Studio Code, I have a specific Python script. And don't worry, I'll provide this script with the demo. So the first thing that we're going to do at the very top is we're going to connect to Redis. So for that, we need a host, we need a password, and we need a port. So I provided the information that's given to me with Azure Managed Redis. The password in this particular case is an access key. Now, the next thing that I do on line 10 is I actually use the host, the password, and the port, and I connect to Redis. I put the result of that connection into a variable named R. So from now on, in this code, anytime I want to talk to Redis, I'm going to use the R variable. And in fact, right away on line 19, we're finally actually talking to Redis. And the first thing that we want to do is create an index. Now, in our previous demo, we actually already walked through how to create an index, but we're going to do that again, and we're going to do it in a slightly different way this time. Now, how do we know we're creating an index, and how do we know that it's a Redis search index? Well, we know that because on line 20, we're using a special syntax called ft.create. Now, if you have Redis search installed with your Azure Managed Redis and you have the right tier, you will have access to ft.create. Then you have to pass in certain information to ft.create so that it can actually create an appropriate index. So what we're going to do is we're going to call that index idx_items. And then we're using the on hash, which just basically means it's creating a hash-based index. And then we're doing it based on a prefix. And that prefix is item:. So what this means is that we're going to be creating an index on everything that's in Redis as long as it has a prefix of item:. Then the next thing that we're going to do is we're going to talk about what's in that index. So we're going to say that there's two things in the index. One is the category and the other one is the embedding itself. The category is a simple tag. The embedding is a vector. And we're going to say that it's a flat vector. That vector contains float32 values and that the number of dimensions is 4, meaning that it's going to have 4 dimensions, all of type float32. We're also going to say that it's going to use a distance metric of L2. Now, this is important because what it means is it's saying this is how we're going to do the comparisons. This is how we're going to calculate the similarity score. Once this command is executed, you will have a flat index in Redis. And that's good. It means that you'll be able to now perform various queries. So what this code does is it actually shows you how you could run that query. So the first thing that we would do is we'd actually insert some items into Redis. So we have a key, and we have a category, and we have the embeddings. So again, if we take a look at the index, well, what is the index requiring? Well, the index requires the category and the embedding. So we're going to insert some sample items into Redis. And what are we inserting? We're inserting a category and the vector, the embedding. And this is important. Now, notice that they also have item:1, item:2, and remember that this index is all going to use the item: prefix. So if we had another item in here, let's say, and in fact we'll pretend, let's say that it's doc and it has an ID 5 for some reason. Now, even though it has the electronics category, and even though it has an embedding that is virtually identical, in fact, it is identical to item 4, because it has a prefix of doc, it would not be included in the index. Now we can scroll down and we get to line 41, and all line 41 is doing is it's actually inserting all of those sample items into Redis so that they become available. On line 45, we create a query vector. So this is pretending to be what the user is asking for. And then the last thing that we're going to do on line 48 is we're going to execute a search. So this is the execution of Redis search. And that's important because we're using the ft search command. Now the FT search command, once again, it's an embedded command, assuming that you have Redis search enabled and assuming that you have the appropriate tiers of Azure Redis installed, you will be able to use the FT search command. You will tell it which index to use, which is IDX items. It's the index that we just created above, and then we specify information about the query that we want. So with the KNN, we're saying that we want to actually perform a nearest neighbor search. We pass in our query vector, which is what the user has sent us as their request. We're going to sort by the embedding score, which is something that's automatically calculated based on our index. And we're going to say that we want to return only 2 items. We're also saying that we want to return the category and embedding value. And then after that, we would print the results, and it would be that simple. So let's just do a real quick recap. At the end of the day, all that matters is 2 pieces of information in this file. One is the creation of an index, and that index actually maps the embedding. And the other is the running of the search. And the search utilizes that embedding in order to return data. Now, in terms of having the extra metadata, we are saying that our index does include a category, which means that when we run the search, we can also pass category information, and that will allow us to get an even better and even faster search. But at the end of the day, there you have it. In this demo, we looked at how we can create a vector similarity query and inspect nearest neighbor results with metadata to understand how Redis returns both semantic searches and contextual fields all together. Great job! In this demo, we're going to walk through an AI pattern that combines semantic cache behavior with vector similarity search, so you can see how applications tend to avoid unnecessary model calls while still retrieving high-quality context when needed. Now, this pattern is increasingly common in modern AI systems because it blends fast cache responses with deeper retrieval when the cache can't satisfy the request. So imagine you have an internal help desk assistant. When an employee asks a question, the system first checks a semantic cache to see whether a meaningfully similar question has already been answered. If the cache hits, then the system simply returns the cached answer instantly. Only if the cache misses will the system actually run a vector similarity search to retrieve relevant documents. It can then use those results to then generate a fresh answer and store that answer in the cache for future reuse. So the idea is only call your model, only call your databases if you really need to. If you've already got the answer in cache, just give them the answer that you have in cache. It's a lot faster, and it's going to have less burden on your system. So for this demo, we're going to walk through a similar example written in Python. It's going to include a tiny semantic cache. It's going to have a Redis vector index, and it's going to show you how you would run a similarity search when the cache misses, and then show how the combined pattern works end to end. So on my screen, I have Visual Studio Code, and I have the aforementioned Python script. And don't worry, as usual, I will provide this script with the demo. All right, so the script that we have is a little bit longer than our last couple of demos, but it does start off the same. The first thing that we're going to do is we're going to make a connection to Redis. So on lines 5, 6, and 7, we define the host, the password, and the port, the password being an access key. And then on line 10, we establish the actual connection to Redis, which includes the host, port, and password, and it puts the result in a variable named R. Now, the next thing that we're going to do is we're actually going to create a few functions. So we have a get from cache function, and then we have a store in cache function. Now, why do we need these functions? Well, that's going to make our life a little bit easier. The get from cache function allows us to pass a query, and then it's going to perform a simple request. It's going to check to see if our cache contains a given key, and if it is found, then it's going to return our semantic cache key. If it isn't found, it's going to return none. Our store in cache puts the query into our semantic cache. Now, the semantic cache is a local variable. It's a simple dictionary that's just used for this demo. You can use Redis, you can use other tools, you can even use Cosmos DB. It doesn't matter. At the end of the day, we're saying, based on a query, If we've already answered that specific query, we're going to return an answer. All right, the next thing that we're going to do is we're going to create a vector index in Redis. So in our last couple of demos, we actually created those indexes, so this isn't anything new. We're using our simple ft.create. We're creating an index called idx-help. We're going to index anything with the doc prefix, and we're going to have some metadata along with our embedding. So in this case, we're going to have our category metadata as well as the actual embedding, which has 4 dimensions that are float32 type. Now, if we scroll down, we can see that in this particular Python script, we're also creating some sample data. They all have that doc prefix, and in terms of category, we have passwords, we have travel, and then we have some random embeddings. Then on line 52, a simple for loop where we insert all of that into Redis. Then we have another function that we're creating called runQuery. Now runQuery is going to take a query as well as a query vector. Now these are basically the bits of information that our user is going to give us. So we're simulating the user sending us some requests. Then we're going to check to see if there's anything in the cache that matches that user query. If we do get something back, then we can say it's a cache hit, and we return the fact that there's a cache hit, and we return the cached value. If, however, there is a cache miss, then what we need to do is we need to actually perform the real query. So we can see that on line 64, we execute another command, which, just like our previous 2 demos, features the ft.search. So this is going to search our index of index help. It's going to use KNN, which means nearest neighbor, and it's going to pass in the actual user vector. And that's going to return the closest result, and it's going to return the category as well. So that means that we're going to get back that value. Now, what do we do with that value? Well, now if we go down to the bottom of this run query function, you'll see that we get our answer, and that we then store it in the cache. So we say now that we have the answer, we're going to store based on that query the answer. And then we're going to log the fact, or rather display the fact that there was a cache miss, but we do have our answer. So let's recap. What is this going to do? It's going to run query, and what's going to happen is it's going to check to see if the answer is already in cache for that specific query. If it is, it simply returns the cache. If it's not, then it's going to run the real query and put the result into cache, which means that if it runs again, this time the answer will be in cache and will avoid all of the extra stuff that's actually going and running the real query. So you can imagine that there's a real model happening in here or downstream that we now completely avoid because we have our real cached value. So on line 79 and 80, we actually run the query. So in this case, we say, here's my query, how do I reset my password? And another query that says, how can I change my password? Which are functionally very, very similar. So what would happen is we would get back a cache miss the first time, because of course we've never run this query before. And then the second time, we might get a cache hit because they are functionally the same, and we get back the same answer. And that would reduce the load on everything behind the scenes in terms of actual model runs and everything, because we were able to get everything out of cache. Now, as we noted in our previous 2 demos, if you have the appropriate tiering for Azure Redis, then you will be able to implement Redis search and you'd be able to actually run this command. I don't have that tier, so I can't. But if we did run this, the first query would, as we said, produce a cache miss, and the second query would produce a cache hit because it's semantically similar. And again, this pattern reduces model cost by avoiding all the repeated calls to the actual models or to the behind-the-scenes database. Vector searches provide deeper retrieval only when the cache can't help. So by combining all of these patterns, we get fast responses and high relevance. So there you have it. In this demo, we walked through a simple AI pattern that combines semantic cache behavior with vector similarity search to reduce model cost while still retrieving high-quality context whenever it might be needed. Great job! In this demo, we're going to send some sample AI work messages to a service bus queue and then receive them back again with a simple client. This pattern is foundational for AI pipelines that rely on asynchronous processing. Maybe you're queuing embedding jobs, or model generation tasks, or retrieval operations. So by walking through both sending and receiving, you'll see exactly how applications communicate through Service Bus and how messages flow reliably through the system. Now, a simple use case for this demo is an AI workflow where front-end services can queue some work items, like generate a summary, embed a document, or run classifications, and then a background worker processes those requests. So Service Bus ensures that messages are durable, ordered, and retried if needed. All right, so let's get started. Now, I have Visual Studio Code open on my screen, and I have a Python file that works with a service bus. And don't worry, I'll provide this Python file with the demo. Now, behind the scenes, it is understood that you have a service bus already. So on lines 4 and 5 of this code, I provide the connection details for that service bus. I give it a connection string, and I tell it which queue I'm interested in. Then on line 8, we actually establish the connection to the service bus. So we pass in the connection string, and we pass in the fact that we want logging to be enabled. So now what we can do is, now that we have a connection and we have it in a variable named client, we can start the sending and receiving process. So what we want to do is we want to send some messages. Then what we're going to want to do is receive those messages back. So let's take a look at the two main parts of this code. The first part, starting on line number 10 and 11 here, is the creation of the messages we want to send. And if we scroll down, you'll see on lines 22 and 23 that we're receiving those messages again. So let's walk through how this code works. So we'll start with sending the messages. On line 11, we say that we want to send a message to the queue. So we use the client that we've established a connection for, and we say that we want a sender. What we do with that sender is send messages. Now notice that this is included in a with. Now what that means is that we get a sender, we perform some operations, and then when we're done with that sender, it's going to completely remove the sender from memory. So it's not just going to linger around. So then what we do is on line 12, we're just going to say on the command line that we're about to send some messages. Then on line 13, we create an array of the messages that we want to send. So we're going to send 3 messages. One is that we want to embed document A. Next is we want to summarize document B. And then we want to classify document C. So these would be the various requests from your users. They're all coming in all at once, and what we want to do is we want to send all of those messages to the queue as we get them. So we're basically simulating 3 messages all coming in all at the same time. So we create a service bus message. So it's a simple string that just represents the message. Then on line 18, we iterate through that array. And we say for each of the messages that is in the message array, we're going to use our sender that we created on line 11, and we're going to send the message. And then we're going to print out that we did in fact send the message, and we'll say which one we sent. Okay, so that block starting on line 11 actually sends out 3 messages. Fantastic. And we should see some things on the command line that says we've sent them. So now that they're sent, what we want to do is we want to receive them back again. Now, Service Bus is event-driven, so what we need to do is we need to configure what's called a receiver. So now if I scroll down on line 23, we have another with block, and we're going to get a receiver. So we're going to tell it which queue we want to receive messages from, and that, of course, is the demo queue that we established at the beginning of this whole Python block. Then we're going to say we're ready to receive some messages. We'll just print that out to the command line. And then we're going to say, all right, for each message that we receive with a max count of 3, let's go ahead and print them onto the screen. So what this means is that we're going to receive messages, and as we receive them, we're going to print them out to the screen. And that's exactly what we want. So Ideally, what we're going to see when we run this script is that we send 3 messages and then we receive 3 messages. So let's give it a try. So I'm going to expand the terminal down at the bottom of the screen, and then I'm going to run the file. So we'll type Python space, and then the name of the file, which in our case is servicebusdemo.py. And once again, don't worry, I'll provide this file with the demo. So let's go ahead and run it. All right, so now we're seeing some items on the screen, and it's everything that we expected to see. So we see that we're going to send some messages, and then we see the 3 messages that we sent, the embed, the summarize, and the classify. And then we say, all right, we're ready to receive messages. And what do we get back? The embed, the summarize, and the classify, which is precisely what we expected to get. Now, this pattern is ideal for AI workloads that need asynchronous processing. Applications will scale out receivers to process a bunch of messages in parallel, where of course right now we're doing everything in a serial way with only one processor, but we could have many processors. And Service Bus supports dead lettering for messages that can't be processed for whatever reason as well. At the end of the day, however, there you have it. In this demo, we did send some sample AI work messages to a Service Bus queue, and we were able to receive them with a simple client to demonstrate reliable asynchronous processing. Great job! In this demo, we're going to publish messages to a Service Bus topic and then inspect how subscriptions receive different copies or filtered sets. This pattern is super important for fan-out messaging in AI systems. One published message can trigger multiple downstream workflows, each with its own filtering rules. Now, by walking through topic publishing and subscription behavior, you're going to see exactly how Service Bus distributes messages and how filters shape what each subscriber receives. So now a good use case for this demo is an AI pipeline where a single process document event needs to trigger multiple independent actions. One subscription might handle embedding, and another might handle summarization, and yet another might handle classification. Filters help to make sure that each subscription only receives messages that are relevant to its role. All right, now let's get started. Now I have some Python code open on my screen, and don't worry, as usual, I'll provide this Python code with the demo. Now what we want to do in this demo is we want to connect to a topic, and then we want to subscribe, or at least show what it would be like to subscribe and only get the information that we want. So at the top of the screen, we create a connection string, and then we have our topic name, which is where the data needs to go to, and then we have 2 subscription names. One is for embedding, and one is for summary. Now, I'm going to actually show how the topic and these subscriptions are set up in just a moment, but for right now, let's take a look at the code. On line 10, we establish a connection using that connection string, which is totally fine. So we have a client object that we're going to use for the rest of the script. Now if we scroll down, we can see that we're sending some messages. So in line 13, we have a with block, which is going to give us a sender. So we're using the topic name. Now the topic is named demo_topic. That's going to be important in a moment. Then what happens is once we have that sender, we create an array of messages, 3 messages, which we're going to look at in a second. And then on line 20, we use a simple for loop to iterate through those messages and send them to the topic. So you can imagine all kinds of things that are happening in the system, and they're all sending messages to the service bus. But it's not sending it to a queue this time, it's sending it to a topic. It's still a service bus message, but it's going to a topic, which means that there could be any number of subscribers to that topic. So it's like publishing an event. Now let's take a look at these events. What we have is a service bus message, which has a simple message, but it also has some additional application properties. And every one of them, you'll notice, has a property called type, which has a value. So 2 of these messages are type embed, and one of them is type summary. Now this is going to be very important in a moment. So remember, we have embed and we have summary as types. Now what we're going to do is we're going to pretend that we have a subscriber. So these would typically be 2 completely different applications, not sharing the same script, but we're going to show everything in the same script to make things a little easier for us. Now if we scroll down, we'll notice that there are 2 blocks, and they're both precisely identical with one exception. one is going to receive messages about embeddings, and the other one is going to receive messages about summaries. So what happens is we once again create a receiver, just like we did in our previous demo. We say which topic we want to receive information from, and we say which subscription we're going to use. So one of them is using the embed subscription, and the other one is using the summary subscription. After that, they'll simply display the messages that they got. So for the embed subscription, we're going to hopefully display all of the embedding subscription messages. And then same thing with the summary. We're going to show all of the summary subscription messages. All right, so let's go back once again to the messages that we're sending. Now remember, we're sending it with a type of either embed or summary. So now what I'm going to do is I'm going to flip over to the Azure portal. Perfect. Now I've navigated specifically to a service bus, and this is my SB demo bus, and it is the one that we're connected to with that connection string. Now within this service bus, we have a singular topic called demo topic. So this is the topic that we're sending messages to. Now if I click on demo topic, I'm going to see information about that topic. That's fantastic. Now if I scroll down to the bottom of the overview page, you'll notice that there's two subscriptions. One is called Demo Embed, and the other is Demo Summary. And that's exactly the two subscriptions that we're connected to. Fantastic. So far, everything is lining up well. So what I'm going to do is I'm going to click on one of them, and this is going to give me information about that subscription. Now on the overview page for this, I can scroll all the way down to the bottom, and we'll notice that there are filters. Now take a look at one of the filters that we have. It's called Type Filter. Now if I click on this filter and scroll a little bit more and take a look at the block that's appeared on the right-hand side of the screen, you'll notice that there's a filter that says type equal embed. Now this is a simple SQL-like expression. And basically what this is saying is that we only want to get messages sent through this subscription if the type property is set to the value of embed. Now let's go back to the code. And remember that we have type and a value of embed, which theoretically means that if we go back to the Azure portal, in order to use the demo embed topic subscription, we need to be able to send values through that have type embed. What this means is that that specific demo topic subscription is still going to get all the messages, including the summary, but it's going to filter out everything that doesn't have type equal embed, which means that specific topic is going to get all three of these messages. But theoretically, my embed subscription output should only show me the ones that have the type of embed. So it's going to be as if though I only get those two. And likewise, the same thing for summary. It only is going to care about the ones that have type of summary. So let's go ahead and see this script in action. I'm going to scroll up here and just expand the terminal section so that we can see it a bit more. And then what I'm going to do is I'm going to type Python. And then I'm going to execute the Service Bus demo file. And once again, don't worry, I'll provide this file with the demo. Now if I execute this, what I should see is the three messages get sent to the topic, and then I should see the subscription values come back for each of the subscriptions. So for my embed subscription, I should only see the two embed messages, and for my summarize subscription, I should only see my one summary type message. So let's go ahead and execute and see what happens. So we've executed the command. We can see that we've published the three messages. And then for my embedding subscription, I've only received the two embed subscription messages. And for my one summary subscription, I've only received the one message. So there you have it. In this demo, we published messages to a topic, and we inspected how subscriptions receive different copies or filtered sets to support fan-out AI workflows. Great job! In this demo, we're going to force and review a dead-lettered message and explain the recovery or remediation path so you can see exactly how Service Bus handles messages that can't be processed normally. Dead lettering is a critical safety valve in AI pipelines. When a message repeatedly fails, or exceeds its TTL, or violates validation rules, Service Bus will move it to the dead letter queue, or DL queue, instead of losing it. By inspecting the dead letter queue and walking through recovery, you're going to understand how to safely replay or remediate failed work items. So imagine an AI worker that's processing embedding jobs. If a message contains malformed data, or the worker crashes repeatedly, the message eventually lands in the DL queue. Reviewing the dead letter reason helps to identify whether the issue is with the payload, the handler, or the system. And then, once it's fixed, the message can be replayed or discarded. Alright, so let's get started. Now I have Visual Studio Code open on my screen, and what I want to do is I want to walk through a failure script. And don't worry, I will provide this script with the demo. Now, as usual, on lines 4 and 5, I'm providing some connection details. This includes the connection string to my service bus and a name of a queue. Then what I want to do is I want to establish a connection. So the connection is fairly standard. What we want to do is we want to create a variable called client, and then we want to provide the actual connection. So we can do something like service bus client, and then .from connection string, and then we can pass in the connection string details, which would be constring equals, and then of course our connection string, and then we can say whether or not we want to have logging turned on. So let's say we want to have logging enable, and then we'll say true. So what this will allow us to do is create a client, and then we can use that client for the rest of the script. Alright, so that's what we do. On line 10, we then use the client to send a message to a queue. Now, importantly, we want to send a message that's going to be failed. So what we're doing is we're just sending a pretend message that has a bad payload with an application property of fail. Now, this doesn't make it fail. We're just sending a message that we're saying is going to be a failure type message. It's a test message. So what we should see is that we've sent the message, and that's all good. Now what we would want to do is we want to receive the message, just like we've done in our previous demos. So we're going to use a with block. We're going to get a receiver for a queue. We're going to pass in our queue name, and then we're going to iterate through all the messages that we get from the queue. Now what we want to do, though, is that when we get our message, what we want to do is we want to dead letter it. So we're still going to be sending and receiving the message, just like we did every single other time so far in this course. Nothing has changed about that. The message still comes through. But what we want to do in this case is pretend that the message is bad, and then we want to dead letter it right now. So what we're going to do is we're going to use our receiver, and then we're going to say we want to dead letter this message. And we're going to pass in the message, and then we're going to give it the reason. So we're going to say the reason is that processing failed, and then we're going to give it a human readable description, and we're just going to say that we're simulating a failure. Okay, great. So at this point we sent, we received, and as part of the receiving, we're sending it off to the DL queue. Okay, that's great. So how do we get it from the DL queue? Well, for that, we're going to scroll down, and we're going to see another section. Now, interestingly, this is going to look exactly like our other receiver. We still have a with block. We're still saying that we want a queue receiver. We're still passing our queue name, but we're getting a sub queue in this case. And the sub queue is a dead letter queue. So every queue that you have in Service Bus has a sibling queue, which is the dead letter queue. So that sibling, or a sub queue in this particular case, can simply be accessed by adding dead letter queue as a subqueue. So we can still subscribe to it just like we do any other queue, except that this time it's going to be specifically the dead letter queue. So then what we do is we iterate through all the messages in the dead letter queue, and what we're going to do is we're going to say, here's the message that we got, here's the reason it was dead lettered, and here's the description that was given. Then what we're also going to do is we're going to complete it. Now this is an important step on line 38. We're saying, all right, we recognize that this message is in the dead letter queue, but after we've read it, we want to complete it, which means effectively remove it from the dead letter queue. All right, so let's see all of this in action. Now to see it in action, all we really need to do is expand the terminal down at the bottom of the screen so we can see a little bit better, and then we're going to run the Python script. So we're going to type Python and then servicebusdemo.py. And again, don't worry, I'll provide this with the demo. So let's go ahead and execute it. Perfect. So what we're seeing in this case is that we're sending a message that will be dead lettered. So it's our simple bad payload message, which we accept. And then what we do is we receive that message. So we receive this message normally. So we see that we've received bad payload, fantastic. And then we're forcing dead letter. So we're moving the message to the DL queue. Now at this point, once again, the send and receive has worked perfectly fine. What we're doing is we're saying we're going to pretend that there's something wrong with this message. So we're going to move it to the dead letter queue. So then we have a reading from the dead letter queue, and sure enough, we get that there was a bad payload, and then we're getting the reason and the description. Now, the reason we're seeing none for reason and description is due to a limitation in the library that I'm using for Service Bus. However, rest assured that the code is accurate, where you're looking for the message application properties for dead letter reason and dead letter error description. That would give you the reason and the description that we passed in to the dead letter queue so that you understand why this message failed and ended up in the dead letter queue. So as a developer or an operator, this gives us access to the remediation path. We understand the dead letter reason, we're able to fix the underlying issue, whether it's a bad payload, something wrong with the handler or the system, and then we're able to replay the message by sending it back to the main queue if we want to. So there you have it. In this demo, we forced and reviewed a dead letter message and explained the recovery or remediation path so you can safely diagnose and replay failed work items. Great job! In this demo, we're going to create and review a custom event grid topic. We're going to publish an event to it and then inspect the event payload as it arrives in a subscriber. This pattern is foundational for AI systems that rely on event-driven orchestration. Things like document processing pipelines, embedding workflows, or model-triggered automation. By walking through topic creation, event publishing, and payload inspection, you'll see exactly how Event Grid moves structured events through your system. So imagine you have an AI workflow that needs to react to new documents being uploaded. A custom topic can receive a document-ready event, and subscribers, like a function that generates embeddings or a service that performs classification, can process the event independently. Inspecting the payload makes sure that the subscriber receives the correct metadata. All right, so let's get started. Now I have Visual Studio Code open on my screen. Now in another screen, I have the actual topic in Azure open. So we're going to look at that in a second too. So what we want to do first is take a look at the Python script. And don't worry, I'll provide this script with the demo. Now, the first thing that we're going to notice at the top of the script is our topic endpoint and our topic key. These are going to be required in order to talk to Event Grid in Azure. So we're going to provide an endpoint to our specific Event Grid, and then we're going to provide a key. Now, this is going to be a key that is specific to your Event Grid, and it can be cycled, which means that this key should change from time to time. Never hard-code it in the file as I have here. Then we're going to provide some headers that's going to be useful for when we actually go to submit the key. So of course that has our key in it, and it has a content type, which says the data we're going to send you is going to be JSON. All right, so the purpose of creating an event grid is so that we can send events. Now events that go to an event grid have to be formatted a specific way. They have to follow the Azure Event Grid event format. So if we take a look at an event, which we start creating on line 14, we can see the structure of that event. It is a regular JSON document, but importantly, it has to be sent as an array because we might send multiple events all at once. In our case, we're going to have an array of 1. So we can see the square brackets, which denotes that this is an array. Then we use the squiggly brackets, which means that we're creating an event object. So this JSON object has an ID, which just needs to be a unique ID, which we create here. It has to have a type, which is something that you can define, and then it has to have a subject, which is something that you define. So far in this course, we have talked about event types and subjects, so here we can see it in action. The subject is the resource that has been affected. In our case, it's document A in some demo resource. The event type is basically saying what the action was, a create or a delete. In this case, we've created our own custom event type called document ready. So perhaps something has been processing documents and it is now saying, I have finished processing it, so I'm going to say the document is ready. And the subject is which document is ready. Then we provide the time of the event, which is basically just date time now in my particular case. And then we provide a payload, which provides any downstream services to have sufficient information to be able to go look up whatever data it needs. In this case, we provide the document ID, we provide a category, and a brief description. We also specify the version of the payload. So if in the future we wanted our payload to be different, we might have a different data version for that payload, but this one would always be version 1.0. That way, any downstream processors would know that if I get version 1.0, it is definitely going to have these properties. All right, so then if we scroll down, we can see on line 28 that we are publishing the event to the event grid topic. So we say requests.post, and then we post the actual event topic. And then what we're going to do is we're going to give it the headers and the actual event as a JSON dump. So we're saying, here's the topic we want to post to. Here are the headers, which basically says that it has my key and that I'm going to be sending you JSON. And here's my data, which is in fact JSON, and it is our event object. Then we get back a status, and that status says, did it succeed to post to the event grid? And then we get back a response, which, if it's successful, should actually be an empty response. All right, now like I said, let's flip over to the Azure portal. Now I'm going to flip over to the Azure portal, and we're going to see right away that we have the event grid topic that we're talking about. So this is the SB demo EGCT, which basically just means event grid custom topic. And we have our topic endpoint. This is the same value that we're putting into our script. Then if we take a look at the settings, we can see other information like the access keys which I'm using. We can take a look at entities, which are the event subscriptions. Now there's currently no subscription, but what I could do is I could create another subscriber in here. Now what this means is that anytime something is posted to the event grid topic, anybody that's subscribed will get that message. Now we're not going to do that in this particular demo, but you can understand how that works. We post to the event grid topic. Anybody who's subscribed is going to get the information. That simple. All right, let's first go and see if we can actually post our message. So down at the bottom of the screen of Visual Studio, I'm going to expand the terminal, and then I'm going to run Python, and I'm going to pass the event grid demo.py. And again, don't worry, I'll provide that file with the demo. So what we should get here is that we're creating the event, and then we're posting the event. What we hope to receive is that the event grid topic is going to say, I have received your message, and then it should give me a 200 and then have no response text, because any success won't have any response text. So let's go ahead and execute. Now it says it's publishing the event, and sure enough, we get a status of 200 and a response that is blank, meaning that it's all done and everything went successfully. So as you can see, Event Grid is very lightweight. It has a reactive orchestration that is downstream of actually publishing any event to it. And it also is important to note that Event Grid guarantees at least once delivery, which means that now that the message is in the Event Grid topic, anybody that's subscribed will get that topic. So there you have it. In this demo, we created a custom Event Grid topic and we published an event. And we also inspected that event payload to understand how structured events flow through subscribers. Great job. In this demo, we're going to expand on our previous demo and talk about filters in an Event Grid subscription. And we're going to take a look at how we can implement that using the Azure portal. So what we're going to do here is we're going to take a look at our Python script, which has been enhanced to show different types of filters, or rather different types of events that we can subscribe to. So imagine you have an AI pipeline where there's different subscribers that handle different types of events. So for example, one subscriber might process demo.documentReady events to generate embeddings, just like we had in our previous demo. but another subscriber might handle demo.ImageReady events for classification. Filters can help make sure that each subscriber only receives the events that are relevant to its workflow. All right, so let's get started. Now I have Visual Studio Code open in my screen, and just like our previous demo, we're going to walk through what this Python script does. But then we're going to end up in the Azure portal, and we're going to take a look at how we can then use that to apply filters when we're creating subscriptions. Okay, so in the Python script, we're creating a few variables. We have our topic endpoint and our key, just like we had in our previous demo. And we have headers, which basically puts the key into a header and specifies that what we're going to send is JSON. Then we scroll down, and you might recall in our previous demo that we created an event object, which was actually an array of events. And then we actually specified that as JSON. This time, we're doing exactly the same thing, only we're putting it inside a publish function. That way, we can call this event thing multiple times. So what we're going to do is we're going to call this function with an event type and a subscription. Otherwise, the event creation is the same as we had in our previous demo. It has an ID, it has the event type, which we're going to pass in, it has a subject, which we're also going to pass in, and then the rest of the data is more or less the same. In this case, our data payload has info and a subject, but we don't need to worry about the payload for right now. What matters is the event type. That's the thing that we're going to care the most about. So if we scroll down, we can then see that there's two calls to publish. One publishes an event type of demo.documentReady, and another publishes an event type of demo.ImageReady. These both post the same type of event to the same event grid topic. What matters, however, is the subscribers. So we might have multiple subscribers to the event grid topic, and what we want to make sure is that each subscriber only gets events that it cares about. So we might have two downstream processors, and one of them is for documents and another one is for images. Well, we don't want to pass the document type into the image processor, just like we don't want to pass the image type into the document processor. So we need to make sure that our subscriptions are filtered appropriately. So let's see that in action. So to do that, we're going to flip over to the Azure portal in my browser. Perfect. Now in the Azure portal, I've navigated to the event grid topic that we're using in our Python script. What we want to do is we want to take a look at how we would create a subscriber so that we only get events that matter to us. So in the left-hand menu, there's a section called Entities. So let's expand that. Now, underneath Entities, we only have one selection, which is Event Subscriptions. So we're going to pick on that one. Now, once we do that, we can see a list of all the subscriptions associated with this topic. Now, as it's a brand new topic, there are no subscriptions yet. So let's see what it would take to create a subscription. So for that, at the very top of the screen, we're going to click Event Subscription Add. And this is going to bring us to the Create Event Subscription wizard, which is going to guide us through the process of creating a subscription. Now, the first thing we would need to do is give our subscription a name. So let's say it was something like demo-image-processor. So this is going to be our image processor subscription. Great. Now what it needs is what kind of schema are you using? Now you can say that we're using your own custom input schema, but in our case, we're going to be using the standard event grid schema. And if we go back to our code, that's precisely what we're using. As an ID, an event type, a subject, and an event time. Generally speaking, that is the simple event grid schema. Now what we can do is we can give a quick filter to our event subscription. So it's asking, what kind of an event type do we need? Well, again, if we go back to our code, we can see that our event types are demo.documentReady and demo.ImageReady. Well, what we have is an image processor subscription. So what I can do is I can copy that text, head back to the portal, and I can click on Add Event Type and simply paste that text. And what that means is that the subscription I'm creating here will only ever process events that have an event type of demo.imageReady. So anything that comes through that is anything else is simply going to be ignored by this subscription. Only the image-ready ones are going to be sent to the users of this subscription. Then we go through the rest of the typical subscription creation, including selecting the endpoint type. Now this is who is going to be the consumer of this subscription. So we can set an Azure function, we can set a service bus queue or topic, a webhook if we want to. Now, obviously, we don't necessarily want to go through the process of creating all this for the purposes of this demo. Suffice it to say that at this point, all we really care about is the filtering. Now, you'll notice that there's another tab at the top called Filters as well. If I click on that, what we can do is we can specify some additional filters. We can filter on the subject, we can add some advanced query type filters as well. So our filters don't have to be exclusive to just the event type. We can also specify other filters as well. So you can imagine if we go back to the code and take a look at our subject, we can see demo/doc.a. You can imagine that maybe we have other types of resource here. Perhaps it's demo/ and we have thumbnails/image.a. And then perhaps we have another event that we would want to publish that isn't thumbnails. Maybe it's full_size. And what we would want to do, even though those are the same event type, is maybe we want to say, I only want to process the full size images because the purpose of this processor is to create thumbnails. So maybe we would add some subject filtering and we would say it has to begin with demo/full size. And if it does, then we know that we're good to process this. If it's anything else, we're going to ignore it, etc. We create a subscription, then we create another app that uses that subscription, and it will only ever receive that specific event. So there you have it. In this demo, we talked about how to add filters to an event grid subscription, and then how that would match with both subject filtering and event type filtering. Great job. In this demo, we're going to take a look at delivery attempt behavior and failure settings for an event grid subscription so that you can see exactly how event grid retries events and when it stops retrying and how failure routing works. This is one of the most important operational safety topics in event-driven AI systems because it determines whether events are delivered successfully, retried predictably, or moved into dead letter destinations for later inspection. So imagine you have an AI workflow where a subscriber, like an Azure function, processes document-ready events. If the subscriber is down or slow or returns errors, then Event Grid will retry delivery based on its configured policy. And understanding these retry rules helps you to diagnose delivery failures and make sure that events aren't silently dropped. All right, so let's get started. Now, I have the Azure portal open on my screen, and what I've actually done is I've navigated to an event grid topic. What we want to do is take a look at a subscription. So in the left-hand menu, let's open up the Entities section, and then we're going to click on Event Subscriptions. And this is going to list all the subscriptions that we have in the system. Now, in our previous demo, we talked about creating a demo image processor subscription. And so what I've done is I've finished that process but just made a dummy thing. It doesn't actually route to anything useful, but it allows us to see what a subscription would look like. So what I'm going to do is I'm going to click on that subscription, and now I'm going to see all the details about that subscription. Now what we care about is what happens about delivery and retries. Well, for that we need to take a look at the tabs in the middle of the screen. So what we're seeing at the top is the topic. This is where the messages come from. If we scroll all the way down to the bottom, we're going to see where the messages go to. So they're coming from our topic and they're going to some service bus queue. So what we care about is what happens if there's failures. So what we can do is we can take a look at the Additional Features tab as well as the Delivery Properties tab. But we're going to focus primarily on the Additional Features tab. The Additional Features tab shows us how we're delivering these messages. If we scroll down, we can see that there's a section for retry policies. How many attempts are we going to try? And we can see that we actually have 30 attempts. But we also have an event time to live, which is how long is it going to live in the queue. So it's going to retry 30 times, trying to send to that queue that we have configured as the output. But If it tries and tries and tries, and then one day later it still hasn't finished trying, it does have a maximum life, which means that after one day of being in our topic, it's going to get thrown out. Now, 30 might seem too high. It is the default, but you can change that however you want. But it is important to note that Event Grid guarantees at least once delivery, so it is going to try at least one time. Now, if we scroll down, what we can do is we can also take a look at dead lettering. So let's say it tries, and then it tries, and it tries, and it tries all 30 times, but it still fails. Now, at that point, what can you do with that information? Well, as it's configured right now for my subscription, what would happen is that the message would simply go away. It's as if it never existed at all. But what we can do is we can enable dead lettering. And if we enable dead lettering, what that means is that the message will go into a dead letter where we can inspect that message and see what might went wrong. So when we enable dead lettering, what we have to do is select where we're going to post that message. See, an event grid and event subscriptions within that event grid can't store any messages. So it's going to keep it in memory and try to send it. But once it fails enough times, whether it's because the time to live is too long or it's reached its max event delivery attempts, it's going to go away. So if we want to keep it for an extended period of time in a dead letter queue, you have to specify where you want it to go. So in this case, it would be a storage blob container. So you'd have to select your container, and then you have to give yourself permissions to be able to do that. So I'm going to turn that back off for now. Now, the other thing that's important about the DL queue, or the dead letter queue, is that it is optional. As you can see, we can turn it on or off, but it is strongly recommended for AI workflows. Basically, again, dead lettering happens when the maximum retry attempts are exhausted, the event TTL expires, or the subscriber explicitly rejects the event. Now, the next thing that we can do, which is very interesting, and there are specific use cases for it, is that the event subscription itself can have an expiration time. What this means is that you can programmatically create subscriptions to the topic, and you can do that for a period of time. And after that period of time, the subscription will be deleted. This basically means that you can create temporary subscriptions to your topic. So if we enable the expiration time, you can set the date and the specific time at which this subscription will be deleted. So this can be useful in scenarios where you want to temporarily create a subscription to a topic. Generally, this is done for troubleshooting purposes where you want to see the messages that are coming into the topic. And in order to prevent affecting any of the other systems that you have out there right now that are subscribed, you create your own subscriptions. So you get all the messages, you see what's going on, you're able to do some troubleshooting and some diagnostics, and then after a period of time, that subscription simply goes away as if it never existed at all. So you're able to do this on production systems without affecting any of your production processors, which can be extremely valuable. So of course, I'm going to turn mine off as well. Now, the last thing that I want to talk about is delivery properties. If I click on that tab, what we can do is we can actually enhance the message that we get. So what happens is that a message comes into the topic, our subscription is able to take that topic because it meets all the filters and other types of criteria, and then it's going to flow through to the service bus in this case, whatever you have as your output. What you're able to do is you're able to add some dynamic header information to the message as well. So what you can say is you can know that since it's come through this subscription, you can actually pass some additional detail automatically without actually affecting upstream services. So they don't have to put anything into the message. You can, as part of your subscription, add additional items to the message itself so that when it goes to the downstream processor, whether that's a function or in this case a service bus queue, it's going to have some extra information in it automatically. Now, with all this in mind, now you're able to fix any subscriber endpoint error that you might get. You're able to see what's in the dead letter queue if you enable it. You're able to create a temporary subscription, which is going to allow you to inspect all the messages that are coming through. You're able to add some additional information as your delivery properties as they come through. And all this is going to allow you to determine if the problem is upstream, if the problem is with the payload, or if the problem is with a downstream processor. So there you have it. This demo showed how retries work, how failures can be captured, and how remediation restores healthy processing. Great job! In this demo, we're going to create a simple HTTP-triggered Python function that validates input and returns a structured response. So we're going to walk through a simple script that shows how a lightweight Azure function can act as a predictable API boundary. It receives a request, it checks that the caller provides the right fields, and sends back a clean, well-shaped JSON response. Now this pattern can be perfect for developers who need a safe and reliable entry point for AI or non-AI workloads. Now, a good use case for this demo is a small application that simply needs to check whether a caller provided a name or an ID or any other parameter before performing any downstream work. So instead of letting invalid requests reach deeper logic, the function stops bad input early and returns a clear message explaining what went wrong. So when the input field is valid, the function can then echo back a structured response that clients can parse consistently. All right, so let's get started. Now I have VS Code open on my screen, and what we're going to do is we're going to create a brand new Python function. So down at the bottom of the screen, I have the terminal open, and I'm going to expand that so that we can see a little bit more of what I'm doing. So the first thing that I'm going to do is I'm going to use the func command to create a brand new function project. So you'll need to have that CLI installed on your machine. This is called Azure Functions Core Tools. All right, so we're going to type func space init space, and then we're going to name our function app. So the function app, just for the sake of this demo, we'll call it demo API, and then we specify the runtime. So in this case, we're going to say it's Python. So now what we can do is execute that command, and it's going to create a brand new function app using Python. And it's telling us what version of Python that it's using, and it tells us all the files that it created. Then on the left-hand part of the screen, we can see that there's a brand new directory called Demo API. And if I expand that, it has all the files that it was talking about. All right, so now that we have the function app, we need to create a function within that app. You can have many functions in a function app. So I'm going to clear the screen, and then we're going to issue another command. This time it's func space new, and then we need to name the function we want to create. Now, before we can do that, I actually need to be in the directory where our function app exists. So the first thing I actually have to do is cd and then demo API so that I'm in the right directory. Now we can clear, and now we type func space new. Now we give the name of our function, which for me is -- name, and we'll call it validate input, just like is being suggested on my screen. And then we can specify a template. Now there's lots of different kinds of templates that you can use, like queue triggers, and you can have timers, and in our case, of course, we want an HTTP trigger. That's the example that we gave. So I'm just going to allow the command that was suggested to me on the screen to be used. Now we can execute that, and it's going to go and start creating the validate input function. Now it's going to ask, what kind of authentication do you want? Now, for this particular case, I'm just going to say, let's use anonymous so that it makes things a lot easier for us. So I'll execute that, and now it says it's done. So now I'm going to clear the screen again, and I'm actually going to take that terminal and make it smaller. Now we can actually take a look at the code that was generated. So in the left-hand menu, we can see the function_app.py. Now if I open that up, we'll see the actual function app and all the functions within it. Now there's one function called validate input, and that's the one that we created. Fantastic. Now if we scroll through, we can see that by default, we actually do have some input validation, which is exactly what we want it to do. If we scroll down, we can see that it's looking to create a name variable. And the first thing it tries to do is get it from the parameters of this HTTP triggered function. So what would that be? Well, imagine you had some sort of URL that looked like what I'm about to type on the screen. So let's say it was https example.org/ and then whatever the route might be, my route. And what it would be looking for is question mark name equals, and that's the parameter that it's looking for. So it's looking to see, is there a name parameter? Now, if there is not a name parameter, which is what the next line says, so if we don't have a name, then what we're going to try to do is we're going to try to get it effectively from the body. So what we do is we get the body itself first, and then we'll see that there's an except and an else. And we're going to get to this except in a second. In the else, it says, okay, if there is a body, then try to extract the name value from the body. Okay, great. Now what happens if there is no body? So there's no parameter and there's no body. So therefore, we don't have a name value. Now, what would happen in that case is we would get a value error when it tries to get a value from the body. Now, in this case, we're saying pass. That just means that we're going to allow the function to continue. We're just going to say, obviously, there's no name. And now, we're going to get back to that in a second. Let's say, happy path, there is a name. What would happen is that we would hit line 21 that says, okay, great, we got a name. So now I'm going to echo it back to you. Hello, whatever your name is, this HTTP trigger function worked. Then we get to the else. So if there was no name after all of that, then it's going to return a regular response that says, hey, great job calling me, now pass in a name. And it returns a status of 200. Now we have a couple of different options here because what we want to do is we want to handle errors a little bit differently. Instead of saying something like, great, this is how this function works, maybe we want to throw an error. So what we could do is we could take this else command and we could actually put it inside the exception on line 17. So instead of pass, we could simply paste it there. And then what would happen is we would then make sure that we have the right spacing so that Python doesn't get angry. Then we could say something like the status code is 400. And then we could say a name is required. Now at this point, what that would mean is that we're trying to get the name from the parameters. Then if it doesn't get it, we're going to try to get it from the body. If it can't get it, then we would return a 400 code. Now this value error only happens if I can't parse the body as JSON. So we could actually have a different error that says the body is not proper JSON and return a 400. Then what we could do down here is instead of saying, hey, everything's good, we could return a 400. And this is where we would say, you must provide a name. Now at this point, what that means is if we were able to parse the body properly, but still didn't get a name value, then we would return a 400. So at this point, if we have a name, we're returning hello name. But if we don't have a name, we're returning a 400 code, which is telling the user you need to provide that value. So right there, we have standard input validation. So there you have it. In this demo, we created a simple HTTP triggered Python function that validates input and returns a structured response. Great job. In this demo, we're going to configure an output binding to persist results from a function. Now this pattern is pretty useful anytime your function produces an artifact, like an AI result, a processed record, or a transform payload, and you want to store it reliably without adding complex plumbing code. Now output bindings give you a simple, declarative way to write data, and SDK calls can also give you full control when you need custom logic. So imagine an AI workflow where a function receives a request, performs a small transformation, and then saves the result to Azure Storage or some downstream system to pick it up. Now, persisting results helps to make sure that every processed item has a durable record, which is really important for auditability and later analysis. All right, so let's get started. Now, I have Visual Studio Code open on my screen. Now, in our previous two demos, we created an Azure function app written in Python, and then we created a couple of functions. In fact, if I click on function app py, we'll see our functions in action. In fact, we have one function at the very top called validate input. And if we scroll down, there was another function for Service Bus queue trigger. So let's take a look at our HTTP trigger. Now, in this particular case, let's imagine that what we're doing in this HTTP triggered function is that we're performing an action, and then we want the result of that action to be output to some other system. like a service bus queue itself. So how would we achieve this? Now the key part here is actually the decorators above our function. You notice that we have one decorator that says app.route. Now this is defining the route to use this HTTP trigger. Now, output bindings can be done in a number of different ways, but one of the simplest ways is to use another decorator. So what we can do is right below the route and still above the actual definition of the function, we can say @ symbol, and then app dot, and then what we'll do is we can provide whatever type of binding we want. So let's just say that what this function is going to do is it's going to create an object, and then we just need to store it in a blob store. That's the simplest thing that we can do here. So what we would do is we would say blob underscore output. And at this point, we have created an output binding. But now we need to give it some information. Where exactly is it going to store it? So what we can do is we can use the circle brackets here, and then we can provide some information. So what we're going to do is we're going to provide what's called an argument name, and we're going to get to that in a second. So we're going to say arg underscore name equals, and then in quotes, output blob. Then we'll make sure that we have a comma so we can put the next parameter, and the next parameter is the path. So path equals, and then what we can do is we can say where inside our blob store do we want this to be. So this might be validated dash inputs. Let's say that's the folder that we want. And then in squiggly brackets, we're going to say rand dash GUID. And then .json. Now this creates a unique file name for every single one of our outputs. We'll put another comma, and then we need to provide a connection, just like we did in our previous demo in order to talk to the service bus. This time we need to provide a connection in order to talk to the blob storage. Now this can actually be the same connection string. Now remember, this does need to be the connection app setting key. So if we go back to local settings.json, I can copy that service bus connection, or perhaps I have a special one for storage connection. And then we could copy that and make sure that we would provide that key later, or at least the value, and then we can put that into the connection. Now at that point, we have the actual blob output defined. So now if our function produces an output, it's going to end up in blob storage. So how do we produce an output? Well, what we would do is somewhere in the code, we would actually produce that output. So let's say it's down where we have our name. The user's provided a name. Great, fantastic. Now we want to put that into blob store. So what I could do is I could create a new variable called blob underscore data, just for the sake of naming a variable. And then we can give it an actual object. So let's say it has a name key, and that value is the name. Then we can say that there is a validated @, and then we could provide some sort of date time. And then what we can do is we can give a status. Basically, we can create an object that has any type of data that we want. Okay, so once we have the actual data, and I'm going to remove the date just to keep things simple, then we can actually output it. Now remember that we have our output blob here. So what we want to do is we want to make sure that we're actually outputting the blob. So to do that, we're going to go down and we're going to type the following code. Output blob.set, and then we can provide json.dumps, because what our object is simply a JSON block, and we're going to say blob underscore data. And at this point, we're going to output the output blob. Now notice that there is an issue with this, but this is actually just something that's local to my machine specifically because I haven't actually installed that thing yet. So don't worry about that. But the main point here is that we have output blob. Now if we scroll back up, remember I said let's remember about that arg name. And notice that in my case, the arg name is output blob. So those two bits have to match. Now what's going to happen is that the decorator has handled the configuration. And now what we've done is we've provided a path so that the actual blob value is going to end up in a validated inputs directory. We have our output blob, which has been injected into the function arguments so that we can use it. And then the output blob.set means that we're passing our string data, which is actually a JSON object, out into our storage account. So we don't have to do any of the actual writing to the storage account. What's happening is that that decorator, that specific output binding, is going to do all of that work for us. All we have to do is say where we want to store the data and then define the data. And Azure will take care of the rest. Now, if you don't want to use an output binding, you can use the SDK directly. There are ways to do that. What you would need to do, of course, is you'd need to import the SDK, and then you can create what's called a client. The client would give you a connection to the storage account or whatever it is that you want to connect to. And then you would create what's called a blob client if you're connecting to a blob store. And that would actually give you a connection to the actual blob you want to write. And then you upload the data. So in that particular case, what you're doing is you are the one that's performing all the connections and all the management of the blob itself. Whereas with an output binding, what you're doing is you're allowing Azure to take care of all of that for you. Now, when do you use one versus the other? Well, an output binding is very useful when you have one output that's almost assuredly going to happen. Whereas the SDK is much more valuable if you want more control or if there's many different things that you're going to write to many different blob stores. But in any case, there you have it. In this demo, we configured an output binding to persist results from a function. Great job! In this demo, we're going to look at how to use an Azure SDK from a function to retrieve or write supporting AI workflow data. This pattern is super common when your function needs to pull reference information, like model configuration, user metadata, or stored documents, or persist new AI-generated results. SDKs give you full control over how you read and write data, which is especially helpful when your workflow requires dynamic paths, conditional logic, or structured storage patterns. So imagine an AI pipeline where a function receives a request to process text, retrieves a configuration file from blob storage, performs a transformation, and then writes the results back to storage. This makes sure that every step of the workflow has access to the supporting data that it needs, and that outputs are stored consistently for downstream systems. All right, now let's get started. Now I have Visual Studio Code open on my screen, and if I open up the function app.py file, we'll notice that there is a function called validate input. Now this is a function that we've used throughout this course. What it is an HTTP triggered function, and it accepts an input, or rather it looks for an input, and then it provides an output binding, which means that it's taking data that it collects and writes it to an output automatically. Now, nowhere in this are we using the actual Azure SDKs that are involved in talking to a blob storage account. So right now we're taking advantage of the built-in bindings. Now what we want to do though is we want to use the Azure Storage SDK so that we have more control. So let's take a look at how we can do that. Now the first thing that we would need to make sure is that we have a connection string to our storage account. So in local settings.json, you'll notice that I have a couple of connection strings, one for a service bus and one for a storage connection. Now, of course, I don't actually have any real data in there. That's sort of outside the scope of this demo, but you can get the connection strings from your storage account and place them into this settings file. Now, that will help with local development, but in the production settings, of course, you have to put that into the app settings of the app service itself, because local settings.json doesn't end up in the production environment. At any rate, let's go back to the function app.py. Now let's say, now that we have that connection string, we want to talk to that storage account in order to write a blob to it. Now, the first thing that we have to do is we need to make sure that we have the connection to the blob client. So I'm going to scroll up, and you'll notice that we have import Azure Functions as func. Now what we can also do is we can say from azure.storage.blob, and then we can use blob client. Now you need to make sure that you install that pip, and once you do, you're going to have access to blob client. Now with blob client, we're going to be able to perform some actions, and this is the SDK. So what kind of action can we do with blob client? Well, we can do a couple of things. One, we can write data, but we can also read data. So you'll notice in our validate input that we're getting a name. The user is passing in some name value. Now let's say that we use that name to go collect some data. So we can scroll down, and on line 30 we have if name, meaning the user has provided a name. And then previously we were creating a blob data object that we were outputting using our output binding. Now let's say actually what I want to do is I want to use that name object to go find a blob. And let's say it's a configuration blob. So what I can do is I can say config underscore blob, that's my variable, equals, and then we would use blob client, which is our SDK. Now what we need to do is we actually need to create a connection to that blob. So we would say dot from underscore connection underscore string, and then in the regular brackets, we're going to pass in the con, which would be our connection string, and I'll show you how to get that in a second. Then container underscore name, and we would provide the name of our container. So let's say it's demo underscore container. And then we would actually have our blob name. And let's say the blob name is what was passed in under name. So we can say it's equal to name. Now the connection is our actual connection string. So there's lots of different ways that you can get that. And one of the easiest ways to do that is to say con equals os.getEnv for get environment variable. And then if we go back to local settings, remember that we have an environment variable called storage connection. So we'll take that string and we'll put it in there. Now OS is another import, so we'd have to go all the way to the top and we'd have to say import OS. And that would give us access to the environment variables, and you can see now that that would work. So we have our connection string, then we go and get the item that the user has asked for by name. Great, so now we have read a blob. So now let's say we do a whole bunch of things with our blob. Now the next thing that we want to do is we want to write a blob. So previously we saw that we can do that. We can say blob data equals, and then we provide some JSON object. Let's say that at some point we provided some data. So instead of name, we pass in some data block. Whatever processing we've done, we can now create an output object. Now instead of using our output binding, well, we can use another blob. So at this point though, we need another connection. So this time what we're going to do is we're going to copy and paste our config blob, and what we're going to do is we're going to paste it underneath our blob data, and this is going to be our result blob. So actually let's call it output blob. And once again, it's from a connection string. We're using the same connection. We're going to use the same container, but this time the blob name is something like result.json. Then what we can do is we can take that blob. So let's say we're going to output underscore blob and dot upload underscore blob, and then we would pass in the same thing that we did before to the output blob binding, JSON dumps blob data. So we're going to actually give it the actual blob content as JSON. Then we would remove the output binding because we wouldn't need it anymore. We can go all the way to the top and we can remove our output binding even from here. That ends up going away. And now we're going and getting our configuration blob. We're creating our blob data, and we're outputting a result blob. Now, one of the things that I didn't show you as relates to our config blob is what we have is we actually have a reference to a blob. We don't have its content. If you did need its content, then you need to download it. So let's say we have our config underscore, and we'll call it text. And then we can say config blob dot, and then whatever it is that we want. So in this case, we want to download it. So it would be download underscore blob, and then we would just read all of the content. So we can say read all, and then we might need to decode it and make sure that it's written in UTF-8. Now at this point, what you can see is that we have a blob reference, which is our config blob. Then we got its content, and then we do some magical work on the inside here. Then we create an output blob, or our blob data. Then we have a reference to an output blob location, and then we simply upload that blob. And at that point, we're completely done. So we've done all the work that the input and output bindings do, but we have full control over how that actually happens. So there you have it. In this demo, we used an Azure SDK from a function to retrieve and to write supporting AI workflow data using blobs. Great job!